Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, as you all must be knowing, we are done with the first chapter of class 11 chemistry, that was a mole concept. And today we shall be starting with the second chapter of class 11th chemistry, that is the atomic structure. Again, one of the most important chapters of your chemistry, from which every year almost 2 to 3 questions are asked, right? And this particular chapter, we shall be completing exactly in 2 sessions. The first session is today, and the second session is going to be on Saturday, right? So, my dear students, in the first part of the atomic structure, in this session, in the today's session, what all topics exactly we shall be covering? Let me, first of all, tell you about all the topics which we shall be covering in the today's session, and I would want you guys to watch this session till the end, right? See, guys. We shall be starting this particular chapter with the first topic, that is the cathode ray experiment. This is going to be our first topic. Once we are done with the cathode ray experiment, right after that we shall be discussing about the Millikan's oil drop experiment. Right after that we shall be discussing about the anode ray experiment. After we are done with the anode ray experiment, we shall be discussing about the discovery of neutrons. Discovery of neutrons. After the discovery of neutrons, we shall be directly going into the atomic models, right? And we shall start with the Thomson's atomic model. Thomson's atomic model. After the Thomson's atomic model, we shall be discussing about the Rutherford's alpha particle scattering experiment. And after that, we shall be discussing about the Rutherford's nuclear model. And once we are done with this, right after that, we shall be discussing about the distance of closest approach. Distance of closest approach. And after doing the distance of closest approach, we shall be directly jumping into the Planck's quantum theory. And once we are done with the Planck's quantum theory, after that, right after that, we shall be discussing about the photoelectric effect. Photoelectric effect. And once we are done with the photoelectric effect, right after that, we shall be starting with the Bohr's model. After Bohr's model, it's going to be the hydrogen spectrum. Hydrogen spectrum. And after hydrogen spectrum, I shall be discussing the de Broglie's hypothesis with you. These are going to be the topics which we shall be discussing in the today's session. And this forms the part 1 of your atomic structure. And in the next part, which will happen day after tomorrow, right? In that part, we shall be discussing about the Heisenberg's uncertainty principle. And after that, the quantum mechanical model, which involves your quantum numbers, electronic configurations, shapes of orbitals. That will be the part 2 of this particular chapter, right? And my dear students, before starting this particular session, first of all those NEET 2025 students, who wanted to be the part of our batch, not on YouTube, on Unacademy platform. For all of you, we are starting the batch, which is the Phoenix Pro batch, particularly designed for NEET 2025 aspirants, as well as 2026 aspirants can join in to this particular batch. Well, my dear students, the batch is starting on 26th of this July, right? 26th of July, we are starting the batch. In this particular batch, your complete syllabus will be done and dusted in till December. And after that, there are 2 months which are dedicated for the revision, right? So whole syllabus of physics, chemistry, biology will be done till December end. And after that, 2 months are dedicatedly kept for the revision purpose. Okay, and my dear students, this is the last live batch which we are starting for the NEET 2025 as well as 2026 aspirants. The batch is starting on 26th of this particular month. And the best part in this particular batch will be every chapter will be started from the basics, right? All the theory, all the problem patterns which can be there in the chapter, every single thing will be discussed in detail, right? There will be tests. I mean, you will be writing the tests on every alternate Sundays. We shall be providing you the tests, right? You'll be having the access to the SRG group, special rankers group, from where Unacademy every year gets all in the single digit, double digit ranks. So you'll be having the access to that particular group as well. Okay, there will be one-on-one mentorship sessions with the educators, as well as one-on-one mentorship sessions with the previous NEET rankers, which have already gotten the single digit, double digit ranks in the earlier NEET examinations, right? Well, if you're joining into this particular batch, you're not supposed to follow any book. The study material, the DPP, which you guys are getting in this particular batch, that is more than sufficient, right? That is more than sufficient. You're not supposed to consult any other book apart from the study material and the DPPs, which we shall be providing you in this particular batch. And one more important thing, you shall be getting the access to the All India Test Series as well, right? Wherein you can compete with all the students across the country so that you can get to know about your ranks, etc. Right? The batch is exactly starting on 26th of this particular month. And this is something which I told you already. And my dear students, the best part is your complete Unacademy NEET English team is going to train you in this particular batch. Well, this batch, right now, you're not getting at 5499. You are getting this particular batch right now at 4999 only. The link is there in the description box of the video, right? Click on that link. Perfect. Get enrolled into the Phoenix Pro batch, which is starting on 26th of this particular month, which is for all the NEET 2025 as well as NEET 2026 aspirants. And my dear students, as I told you, these are the educators. HSP sir, me, Yavar sir, Ambika ma'am, we are going to train you particularly, right? In all the subjects of physics, chemistry, biology, we shall be completing your syllabus, doing the revisions, and you are going to be under our guidance throughout these 9 months till you write the NEET 2025 examination, right? So all those students who want to be the part of the batch, but have not got enrolled yet, right after this particular session, I would want every one of you to join into this particular batch. The link is there in the description box of the video. You just have to click on the link, right? Click on the link. There you'll find two options, either to go for plus subscription or the iconic subscription. What is the difference between the two? In plus subscription, you get the study material in the form of DPPs, and in the iconic subscription, you get the study material in the form of the booklets, and those booklets will be delivered to your houses, right? So join into this particular batch right after watching this particular session of the Atomic Structure Part 1, because this batch is definitely going to be helpful for all the students, right? Okay, so let's get going then. Let's get started with our Atomic Structure Part 1. Okay, so people, the first topic which we are going to start, as I told you, everything will be started from the basics, right? So I'll be exactly starting from the basics itself. So the first topic which we are going to cover right now, that is going to be your cathode ray experiment. That is going to be your cathode ray experiment. So first of all, who performed exactly this particular experiment? This cathode ray experiment, which I'm going to teach you right now, it was performed by J.J. Thomson. It was performed by J.J. Thomson. And let me tell you, it was performed in 1897, right? Mark the date as well. And my dear students, with the help of this particular experiment, what exactly was discovered? With the help of this particular experiment, electron was exactly discovered, right? So with the help of this cathode ray experiment performed by J.J. Thomson, right, in 1897, what we discovered exactly? We discovered electron. Now the point is how this electron was discovered, what exactly was observed, what exactly was concluded, right? So step by step, we'll see the things. So my dear students, in this cathode ray experiment, what exactly was done? Let me tell you, a narrow glass tube was taken. Imagine this is one narrow glass tube. This is a narrow glass tube which was about 60 centimeters long. a narrow glass tube which was about 60 centimeters long was taken, right? Now, my dear students, over here in this glass tube, in this narrow glass tube, a vacuum pump was also fixed. What was the need of this vacuum pump? This vacuum pump was used to control the pressure of the gas inside this particular container. This is a particular container. This is a narrow glass tube which is about 60 centimeters long. And in this narrow glass tube, what you will find? You will find a vacuum pump which is fitted to this particular tube. What is the use of this vacuum pump? My dear students, the gas which I'm going to keep inside this container, the gas which I'm going to keep inside this narrow tube, to control the pressure, to increase or decrease the pressure of that gas inside the tube, a vacuum pump was used over here, right? And my dear students, which gas we are going to take over here? Let me tell you, it is the H2 gas which we are going to take in this particular container, in this particular narrow tube, right? And at the same time, I'll be using two metal strips. This is strip number 1. This is metal strip 2. And let me tell you, these metal strips which I'm using over here, these metal strips I'm connecting with the high voltage battery. These metal strips I'm connecting with the high voltage battery. This is a very, very high voltage battery. It is a very, very high voltage battery which I have taken over here. Now, my dear students, that metal strip which is connected with the negative terminal of the battery, that metal strip which will be connected with the negative terminal of the battery, that will be having the negative charge on it. Similarly, that metal strip which is connected with the positive terminal of the battery, that will be definitely having positive charge on it, right? And this negatively charged metal strip over here, I'll be calling this as cathode. And this positively charged metal strip over here, I'll be calling this as anode. I'll be calling this particular metal strip carrying the positive charge, I'll be calling this as anode. And my dear students, which gas was taken over here in this container? It was H2 gas which was taken for the experiment, right? Now, first of all, this particular tube which was taken for the experiment, this particular tube is what you call as Crookes tube. This particular tube which was taken for the experiment, this is something which you call as Crookes tube. Now, my dear students, what exactly were the observations? What exactly were the observations made by J.J. Thomson while carrying out this particular experiment? What he exactly did? He took H2 gas in this particular chamber, H2 gas in this particular glass tube, right? He used a high voltage battery. My dear students, when the voltage of the battery was kept 10 raised power 4 volts. When the voltage of the battery was kept 10 raised power 4 volts. When 10 raised power 4 volt battery was introduced. And when the pressure of the gas was kept very low, there were some observations. There were some observations which were made by J.J. Thomson. And what were exactly the observations? Try to understand. Before letting you know the observations, let me tell you, this particular side of the glass tube, it was coated with zinc sulfide. So this particular surface of this glass tube, it was coated with zinc sulfide. Why was it coated with zinc sulfide? My dear students, there is a property of zinc sulfide basically. And what is the property of the zinc sulfide? Let me tell you, for example, if this is a plate which is coated with zinc sulfide, my dear students, whenever any particle which has got certain mass, which is moving with velocity v, whenever any particle strikes this zinc sulfide, screen, the point where the particle strikes, at that point, you'll find a bright spot. For example, there is one particle which has got certain mass. It is going to strike the zinc sulfide screen. The point where the particle strikes, a bright spot will be created. Similarly, one more particle over here, striking the zinc sulfide, a bright spot is getting created. So there is a property of this zinc sulfide. What is the property? My dear students, whenever any particle having any mass strikes the zinc sulfide screen, a bright spot gets created on the zinc sulfide screen. Okay, so this particular side was coated with zinc sulfide. Point number one. Point number two, when the battery was turned on, when the voltage of the battery was used as 10 raised power 4 volts, when the pressure of the gas in the vessel, when the pressure of the gas in the container, when the pressure of the gas in the glass tube was kept very, very, very low, at that point of time, few observations were made by Thomson. And what were the observations? My dear students, what Thomson saw, Thomson observed some bright spots getting created on this particular screen. Thomson observed that some bright spots were observed on this particular screen. My dear students, if bright spots are getting observed on this particular screen, what can you conclude from that? What can you conclude? What Thomson concluded? Thomson concluded that there must be some invisible rays. There must be some invisible rays which seems to be coming from the cathode. There must be some invisible rays which seems to be coming from the cathode. And those invisible rays must be striking the zinc sulfide screen. And the point where the rays will be striking the zinc sulfide screen, there only bright spots would be getting created. Right? So when the battery was turned on, when the voltage of the battery was kept 10 raised power 4 volts, when the pressure of the gas was kept very, very, very low, what happened? What happened? Some bright spots were observed on this zinc sulfide screen, which is only possible if some invisible rays are coming from cathode, right? They must be striking this zinc sulfide screen, and they must be creating bright spots on this zinc sulfide screen, right? So my dear students, point number one, the invisible rays, which seems to be, I'm using the term seems to be, right? I have no idea from where exactly they are generated. I have no idea right now. Okay. So these are some invisible rays which seems to be coming from the cathode. The invisible rays which seems to be coming from the cathode. Right? These invisible rays were called as cathode rays. So first of all, this is how your cathode rays were discovered. Perfect. Now, after the discovery of these cathode rays, it was important to understand the properties of these cathode rays, right? It was important to understand the properties of cathode rays, right? What these cathode rays are made up of, right? All these things now we are going to discuss basically. Okay, so first of all, the introduction of cathode rays is done. This is how your cathode rays were introduced. This is how your cathode rays were discovered. Now it was the time to check the properties of these cathode rays. Now, my dear students, a lot of things were done. To understand the properties of the cathode rays. Okay. The first point was whether these cathode rays, which seems to be coming from the cathode, whether these cathode rays travel in straight lines, whether they follow the parabolic path, hyperbolic path. What was the path exactly? What was the trajectory of these cathode rays? This was the first point of discussion. And my dear students, in order to check whether the cathode rays were traveling in straight lines, whether they were following the parabolic path, etc., etc., what exactly was done? Let me tell you, an object was introduced here. An object was kept here. An object. This is the object. Right? And just behind the object, a screen was kept. A screen, right? Just behind the object, I would say, just behind the object, a screen was kept. And my dear students, on this particular screen, what you will find? On this particular screen, what did he exactly find out? Let's try to understand. This is the object, and this is the screen basically over here. Now, when he kept the object here, and just behind the object, there was a screen placed, and again he kept the battery on, he turned the battery on, he gave the voltage of 10 raised power 4 volts, right? He kept the pressure of the gas very low. What he exactly observed? He observed a sharp image of the object was getting created on this screen. On this particular screen, a sharp image of this particular object was getting created. When is it possible? When is it possible? My dear students, if I ask you when a sharp image of the object will be getting created on the screen, it is only possible if these cathode rays, which seems to be coming from the cathode, if they travel in the straight lines. So the first conclusion which was made by Thomson, what was that? That is your cathode rays, they travel in straight lines. They travel in straight lines. Point number one. Now, after getting to know that the cathode rays, they travel in straight line, now it was important to understand of what particles these cathode rays are made up of. Are these cathode rays made up of particles which have got some mass, which has got some charge, right? Now the second point of discussion is what these cathode rays exactly are made up of. Okay, the first point is your cathode rays, they travel in straight lines. That was point number one, right? Point number two, your cathode rays are made up of what? Now it was the point of discussion. So what Thomson exactly did, he kept, let me tell you, he kept a light paddle wheel over here. A light paddle wheel was kept here. A light paddle wheel was kept over here, right? Imagine this is the stand on which a light paddle wheel was kept, right? And this paddle wheel, it was made up of a very light element, that is mica, right? This paddle wheel was made up of mica. Now, my dear students, when he kept the light paddle wheel over here, what he exactly observed? He again turned the battery on, again kept the pressure of the gas very low. What he observed? He observed this paddle wheel started to rotate. When is that possible? When this paddle wheel will go to rotate? My dear students, I would say this paddle wheel will only rotate if some particles of certain mass are striking this, right? Perfect. When some particles carrying certain mass will be striking this paddle wheel, right? Those particles which are striking this paddle wheel, they'll be imparting momentum to this paddle wheel, which makes this paddle wheel to rotate. So what he concluded from here? When he kept a light paddle wheel made up of mica inside this discharge tube, what he observed? He observed this paddle wheel started to rotate, and he concluded the cathode rays which seems to be coming from the cathode, they are definitely made up of some material particles which carry certain mass. And those particles are basically striking this paddle wheel and making this paddle wheel to rotate. Right, my dear students? So the next point is your cathode rays. Your cathode rays are made up of what? Your cathode rays are made up of material particles. Your cathode rays are made up of some material particles which have got some mass. So one more thing was concluded. First conclusion was the cathode rays are made up of what? The cathode rays are made up of material particles. And the material particles of which cathode rays are made up of, let me tell you, those material particles carry certain mass. They have got some mass as well, right? Now, my dear students, after getting to know that the cathode rays are made up of material particles, now it was important to understand the material particles of which cathode rays are made up of, whether those material particles carry certain charge or not. It was important. You must be knowing one thing. You would have studied it as well. Imagine this is a magnet. For example, right? This magnet will be having some magnetic field associated with it, right? This magnet will be definitely having some magnetic field associated with it. My dear students, you must be knowing when a charged particle passes through the magnetic field, it deviates its path basically. Its path gets deviated. My dear students, this particle, it was supposed to go in a straight line, but in presence of magnetic field, it will deviate its path. Its path will get changed, right? Its trajectory will get changed in presence of magnetic field. Now, what Thomson exactly did? He kept a magnet over here. he kept a magnet over here. If magnet was placed over here, that means this particular magnet will be having definitely some magnetic field associated with it, right? It will be having some magnetic field associated with it. And my dear students, what he observed, when he again turned the battery on, when he gave the potential of 10 raised power 4 volts, when the pressure of the gas was kept very low, he observed these cathode rays, which were supposed to travel in the straight lines, these cathode rays were being deflected, right? He observed these cathode rays were being deflected. And this time I would say, this part of the zinc sulfide was glowing. This part of the zinc sulfide was glowing. What does that mean? That means the cathode rays are striking the zinc sulfide over here at the bottom, which is only possible if these rays, if they have deviated their path and they are striking the zinc sulfide screen at the bottom. When is it possible? When is it possible, my dear students? It is possible only if the cathode rays are made up of some material particles. Those material particles will be carrying certain charge as well, right? They'll be carrying certain charge as well. That's why these cathode rays were being deflected from their original paths, right? So what was the conclusion from here? The conclusion was the material particles. The conclusion was like this. Just a second, guys. Let me tell you few more properties. The material particles of which these cathode rays were made up of. The material particles of which these cathode rays are made up of carry certain charge. Right? Now there was one more thing which was to be understood. Since we got to know that the material particles of which these cathode rays are made up of, they carry certain charge. Now it was important to understand whether the charge carried by the material particles, whether that charge was positive or negative. How did he check that? What he exactly did, he took two metal strips again. And these metal strips were connected with some different battery, some other battery. These metal strips, they were connected with some different battery, some external battery. Imagine this particular metal strip, it is connected with the positive terminal of the external battery. So this metal strip will be getting positive charge. And this metal strip, imagine this is connected with the negative terminal of the battery. So it will be getting negative charge. And my dear students, what he observed, when he again kept the voltage of this battery as 10 raised power 4 volts, so when the pressure of the gas again was kept very low, he observed these cathode rays were being deflected towards the positively charged plate. Now tell me, when is that possible? When these cathode rays will start deflecting towards the positively charged plate? Since you know, unlikes attract. So I would say these cathode rays, they are basically made up of those material particles which carry the negative charge. That's why these cathode rays, they are deflected towards the positively charged plate. As simple as that. So my dear students, what he observed, he concluded basically the material particles of which cathode rays are made up of carry certain charge. I would say carry negative charge. Carry negative charge. And let me tell you, and these negatively charged particles, of which your cathode rays are made up of, these negatively charged particles were termed as negatrons, right? So initially it was not electron, initially it was the negatron, right? After the discovery of, right, when this experiment was carried out, what Thomson observed? He observed some of the invisible rays which seems to be coming from the cathode. They were made up of some material particles which have got certain mass, which have got negative charge, and those negatively charged particles of which your cathode rays are exactly made up of, he called them as negatrons. And later on, the name negatrons was changed to electron. The name negatron was changed into electron. And who changed the name? There was one more scientist whose name was Stoney. Stoney was the scientist basically who changed the name from negatron to electron, right? Did you get to know how this electron exactly was discovered? Exactly, negatron sounds cooler, right? I know. My dear students, is it clear till here? Did you get to know how this electron was exactly discovered? Yeah? Perfect. Perfect, guys, perfect. Now, from this particular experiment, few more conclusions were made. Point number one. It was observed that when these cathode rays, when they strike a heavy metal like tungsten, it was observed that when these cathode rays, when they strike a heavy element like tungsten, X-rays were produced. This was one more conclusion. This was one more observation basically. So let me write it over here. When cathode rays strike with the heavy element, like tungsten, X-rays were produced. X-rays were produced. This was one more observation and conclusion made by Thomson, right? Okay. Now, my dear students, at the same time, it was observed that these cathode rays, they produce heating effect. Right? So basically, when these cathode rays were made to fall a metal strip, were made to fall on the metal strip, it was observed that that metal strip was getting time. Its temperature was raising with time, which is only possible if these cathode rays, they produce a heating effect. Right? Perfect. I hope all these things are absolutely clear till here. So my dear students, let me conclude. Conclusion is like this. So first of all, a Crookes tube was taken which was approximately 60 centimeters long, right? And in this particular Crookes tube, H2 gas was introduced. Okay. A vacuum pump was used to control the pressure of the gas inside this container. 2 metal strips were used, right? One connected with the negative terminal of the battery, one connected with the positive terminal of the battery. Negatively charged plate was called as your cathode, positively charged was called as anode, right? When the battery was turned on, when the voltage of the battery was kept approximately 10 raised power 4 volts, some invisible rays, they seems to be coming from the cathode and striking the zinc sulfide screen, at which bright spots were getting created. And he called these invisible rays as what? He called these invisible rays as the cathode rays. Now these cathode rays, they are made up of some material particles which carry certain mass, which have got the negative charge, and the negatively charged particles of which these cathode rays are made up of, he called them as negatrons. And later on, these negatrons were called as electrons. And who changed the name? It was the Stoney who changed the name from negatrons to electrons, right? And these cathode rays, when they strike the heavy metal like tungsten, X-rays were produced, right? And my dear students, at the same time, when you make these cathode rays to fall on the metal plate, what happened to the temperature of the metal plate? Temperature of the metal plate, it kept on increasing, right? Which is possible only if these cathode rays, if they show heating effect. I hope this particular thing is clear till here, right? I hope all these things are absolutely clear till here. Right, my dear students? Now try to understand few more things. Just have a look. My dear students, one more conclusion was made from here. What was the conclusion? Since after the discovery of cathode rays, it was important to know exactly what is the source of these cathode rays, from where these cathode rays are coming, right? And if you ask me from where these cathode rays are coming, my dear students, the answer is very simple. Which gas did I keep inside this particular chamber? It was H2 gas. So basically, in this particular chamber, you have got H2 molecules. So these are H2 molecules basically. These are H2 molecules basically inside this glass tube. Now, dear students, when the voltage was kept high, when the pressure is kept low, what happens to these gas molecules? These gas molecules ionize. These gas molecules ionize. Since you must be knowing, if you have got one hydrogen atom, it contains one electron, one proton, right? When this hydrogen atom ionizes, right? That means when one electron is taken out of hydrogen, it gets converted into H positive. But you have got hydrogen molecule here, you have got H2 molecule over here. So can I say due to ionization, this H2 molecule would have lost 2 electrons and would have got converted into 2 times H positive. Agreed? Do you agree with this? So basically the H2 gas molecules which were there in the container, since you are keeping the voltage of the battery very high, you are keeping the pressure of the gas very low, what happens to the gas inside the container? It ionizes. It loses electrons. So basically inside this chamber, you won't find H2 molecules. Those H2 molecules have got ionized. They have got converted into what? They have got converted into H positives. And with H positives, you have got millions of electrons as well here. Right? Now, my dear students, try to understand. In this particular chamber, what do we have? Can I say in this particular chamber, due to the ionization of the gas, can I say there are positively charged and negatively charged ions? There are positively charged and negatively charged ions and negatively charged electrons here in this particular chamber. Absolutely. Right? Since this particular electrode, this particular plate, it carries the positive charge. If it carries the positive charge, can I say this positively charged plate, it is going to attract all the electrons which are there in the chamber. It is going to attract all the electrons towards itself. Right? Perfect. It is going to attract all the electrons towards itself. And when all the electrons are moving towards this positively charged plate, can I say these electrons will be moving in the streamlines basically? They'll be moving in the streamlines. And those streamlines, those rays which are made up of these electrons, which are moving towards this positively charged plate, those rays only are called as your cathode rays. So if I ask you from now onwards, if I ask you whether cathode rays are originated from cathode, no, they are originated from the gas which is there in the container. Right? When the gas gets ionized, it gives the electrons, and those electrons basically they start moving. Yeah? Perfect. So one important point, your cathode rays, they originate from the gas which is there in this particular chamber. I hope this particular point is also clear to you. Okay, so I will say cathode rays do not originate. They do not originate from cathode. They do not originate from cathode, but from the ionization, of the gas in the tube. Perfect. I believe this is also clear to you. Now, my dear students, one more important thing. Since you know now cathode rays which are made up of these negatively charged particles, if you ask me, how do we calculate the velocity with which these cathode rays move? Right? How do we exactly get to know the velocity with which these cathode rays exactly move? Right? Now, let me tell you how the velocity of cathode rays was exactly calculated. Since, my dear students, these are the cathode rays basically which are traveling, right? Now, with what velocity these cathode rays are traveling basically? How exactly this was checked? How exactly this was calculated? For that purpose, let me teach you a bit of physics, which I'm sure you all must be knowing. My dear students, imagine that this is the positively charged plate and this is the negatively charged plate. Imagine these are the two plates which are connected to the external battery, right? Imagine this particular plate is connected with the positive terminal. This particular plate is connected with the negative terminal. That is the reason why this got positive, why this got negative. Now, for example, this is the electron. This is the electron, for example, carrying the negative charge. If the electron starts moving, so first of all, between these plates, what will be there? Can I say between these plates, there will be electric field lines, right? There'll be electric field lines between these two plates. Absolutely. So there is electric field basically between these plates. And my dear students, when this negatively charged particle, it passes through this particular field, what happens basically? I say this positively charged plate is going to attract this negatively charged electron towards itself. So electron will deviate its path. It will start going towards the positively charged plate. So can I basically say it like this? When the electron is traveling in this electric field, can I say the electron has to go forward basically. It has to go forward. But in this direction, the electron is experiencing a force which you call as electrical force, right? Electron, it basically has to go straight. But due to electric field, it deviates its path. Why is that? Because when the electron enters the electric field, the electron is supposed to go this way. But at the same time, this particular electron, it experiences force in this direction, right? It was supposed to go like this, but there is one more force pulling it towards itself. That's why it deviates its path due to electric field. Perfect. Now, for example, imagine if I put a magnet also here. I'm placing a magnet in such a way that the electron, when it passes, right? It experiences one more force, downward force. Due to this downward force, the electron has to go in this direction. It has to deviate in this direction. Perfect. My dear students, understand one thing. In presence of electric field, the path of the electron should be like this. In presence of magnetic field, the electron path should be like this. So basically, when the electron is simultaneously entering into electric and magnetic field, I'll say this electron is experiencing two forces. Electron has to go in this direction, but simultaneously electron is experiencing two forces. One is electrical force in upward direction, one is magnetic force in downward direction, right? Now you tell me one thing. Since I'm telling you the electron is entering simultaneously in both the fields. Due to electric field, electron is experiencing a force in upward direction. Due to magnetic field, the electron is experiencing a force in downward direction. My dear students, imagine if electric force is more than that of magnetic force, the electron will go up, right? If magnetic force is more than that of electric force, the electron, it will deviate downwards. But if we exactly balance the two forces, if we exactly balance these two forces, can you just tell me in the chats, will the electron get deviated from its path? The electron is moving in this direction, right? When electron reaches here, it is experiencing two forces. One is upward direction, one in downward direction. One electrical force, one magnetic force. If you balance these two forces, if by chance electrical force and magnetic force on the electron becomes equal, will the electron deviate? The electron will not deviate. The electron will not deviate at all, right? So my dear students, what exactly was done? The electric field and the magnetic field simultaneously were placed inside this particular container, right? Perfect. Due to which the electron of which cathode rays are made up of. Cathode rays are made of electrons, right? The electrons, they experience two forces. Imagine one in upward direction, one in downward direction. And those two forces were balanced. And when these two forces were balanced, I would say electron passed undeviated. Now you tell me, why did electron pass undeviated? Because electrical force and magnetic force on the electron, they cancelled. What is electric force all about? It is the charge on the electron multiplied by electric field, right? Perfect. What is magnetic force? Charge multiplied by velocity with which electron moves multiplied by B, right? Magnetic field intensity B. Perfect. Now, my dear students, if I ask you whether this Q gets cancelled, absolutely. So V comes out to be equal to E divided by B. Now, if you ask me what this V is the velocity with which electron moves. V is the velocity with which your cathode rays move. Perfect. B is your magnetic field, E is your electric field. Electric field strength, magnetic field strength. Okay. Perfect. So, what did we calculate from here? We are getting the velocity with which the electron moves. we are getting the velocity with which the cathode ray moves. It is coming out to be equal to E divided by B. What is this E and B? E is the electric field which was generated by those two plates. What is B? B is the magnetic field which was generated by the magnet, right? What did we do? What did we do? Basically, we changed. We kept on changing electric field and magnetic field in such a way that the magnetic force experienced by the electron becomes equal to the electric force experienced by the electron, right? So basically, these two values we already knew, right? Because we were the ones, because Thomson was the one who was exactly changing the electric and magnetic field in such a way that magnetic force and electric force becomes equal, right? And electron then pass undeviated. Perfect. So these two values already he knew. If you know electric field strength, if you know the magnetic field strength, can't you calculate velocity with which the electron moves? And it was observed that the speed, the velocity with which the electron moves, the speed with which the cathode rays moves, it was observed that it is equal to 1/10 of the velocity of light. Right? So your cathode rays, they were moving with the speed 1/10 of the velocity of light. This is one more important conclusion. My dear students, after getting to know the speed with which the cathode rays move, the speed with which these electrons, of which cathode rays are made up of, the speed with which they move, after getting to know this, there was one very important conclusion. What was that? That was calculation of specific charge. Calculation of specific charge. What is specific charge? Specific charge is called as E divided by M ratio. It was important to know the E divided by M ratio. And this E divided by M ratio was calculated with the help of this cathode ray experiment tube only. Now, what is this E by M? E is the charge on electron. Since we have only discovered the electron, we do not know what is the charge. What is the magnitude of charge on electron? We do not know exactly the mass of electron. But now you are going to get to know the E by M ratio. Combinedly, how E by M ratio of electron was calculated. Let me tell you that. Did we already calculate the velocity with which electron moves? Absolutely. The velocity with which electron moves was already calculated. That was equal to E divided by B, I believe, right? Electric field strength, magnetic field strength. This is already something which we calculated, right? V was equal to E divided by B. This was already calculated. This was already calculated. Now, it was the time to calculate charge divided by mass ratio of the electron, and how this charge by mass ratio of the electron was calculated. Try to understand this a bit more in detail. See guys, for example, this is your cathode, which was inside the discharge tube carrying negative charge. This is your anode carrying positive charge, and these two are basically connected with the external battery. You know it. Connected with the external battery. Perfect. Imagine that the voltage of this particular battery is V. Imagine that the voltage of this particular battery is V. If the voltage of this particular battery is V, that means the potential difference between these two electrodes. The potential difference between these two electrodes. That will be V. Agreed? That will be V. Now tell me one thing, guys. Imagine, just to make you understand, imagine I've got electron over here with me. Imagine that I've got electron with me. First of all, tell me, this is a positively charged plate, this is a negative charged plate. Can I say there'll be field lines? There will be electric field lines, right? So electric field is between these two plates. Absolutely. Now, if you have got electron, let's say this is the electron in my hand. For example, I'm placing electron here. I'm not leaving the electron yet. I'm placing the electron here. And I'm holding the electron. Can I say this electron in this field will be experiencing a force towards this positively charged plate? Absolutely. The electron is experiencing a force right now, right? And if I by chance leave this electron, it will move towards the positively charged plate. Yes? So let's say you're keeping electron here. When you keep the electron here, and imagine, it is hypothetical. Imagine you're holding this electron. The electron will be experiencing a force in this direction. This plate will try to attract the electron towards itself. And my dear students, I'm holding the electron, but the electron would want to go towards the positively charged plate. But I'm holding the electron. That means this electron has got some potential energy right now. If I suddenly leave it, this potential energy will start getting converted into kinetic energy, right? I'm writing it over here. if the electron, okay, if the electron, or you can write in general, if the charged particle, if the charged particle is placed under a potential difference, under the potential difference of V volts. If a charged particle is placed under the potential difference of V volts, what will happen? What will happen? Can I say the potential energy of the charged particle will start getting converted into its kinetic energy, right? Perfect. What is potential energy exactly equal to? Do you know potential energy is equal to charge on the electron multiplied by potential difference between the plates, right? Q multiplied by V, that's your potential energy. Kinetic energy, half of mv square. This is the velocity of electron, this is the mass of electron, right? Perfect, guys. Now tell me one simple thing. If I would want to eliminate V square from here, they say V square will be 2 times Q, capital V, divided by M. What is the small v and capital V? Small v is the velocity with which the electron is moving. What is capital V? It is the potential difference between these two plates. It is the voltage of this particular battery, right? Now V already you know, it's E by B. So V square will be equal to E square by B square. So E square divided by B square is equal to 2 times Q, capital V, divided by M. Perfect, my dear students. Perfect. What is Q? Q is the charge on electron. What is M? M is the mass of electron. Charge on electron is represented by E, right? So if I ask you, what will be the E by M value? E divided by M will be equal to E square divided by 2 B square multiplied by capital V. Do you agree with this? E by M came out to be equal to E square divided by 2 B square multiplied by V. My dear students, already we know the E value, already we know the B value, and this voltage, this potential difference, we already know. Perfect. So all the values over here we already know. So can I say E divided by M value? We can easily calculate from here, right? E divided by M value, we can easily calculate from here. And how much it will come out to be? It will come out to be 1.76 into 10 raised to 11 coulomb per kg, right? So my dear students, with the help of this particular calculation, E divided by M ratio, specific charge of the electron, E by M ratio of the electron was calculated, and it was found out to be 1.76 into 10 raised to 11 coulomb per kg. Right? Right, people? So this is how your E by M ratio was calculated. Charge on electron was not calculated yet. Mass of electron was not calculated, but the ratio of charge and mass of electron was already calculated with the help of this particular experiment. Yeah? Now, my dear students, which gas did I take? H2 gas. Now, the experiment was repeated again with the help of one more gas. When the experiment was repeated by taking one more gas, E by M ratio was coming out to be same. When one more gas was taken, experiment was again repeated. E by M ratio was coming out to be same. Right? Because what exactly happens? All the gases will give away the same electrons during ionization, and those electrons will move. Perfect. So my dear students, let me tell you, this experiment, it was carried out many a times, and E by M ratio of electrons was coming out to be same. So what was concluded from here? It was concluded that the E by M ratio of cathode rays, I would say, the E by M ratio of cathode rays is independent. It is independent of the nature of the gas taken. It was the independent of the nature of the gas taken. And it was independent of the material of electrodes which were used. It was independent of the material of the electrodes which were used. Okay? So I hope you got to know exactly how E by M ratio of the electron was calculated, right? And my dear students, since E by M ratio was calculated, no doubt, E by M ratio was calculated. E by M ratio of electron was calculated, but the charge on electron was not calculated yet. The mass of the electron was not calculated yet individually, right? Now, it was the time to calculate the exact charge present on the electron. And how exactly they calculate the charge on the electron? With the help of Millikan's oil drop experiment. Someone is asking, what is hydrogen spectrum? Bro, I did not reach the hydrogen spectrum yet. Just wait, hydrogen spectrum will be done in the second session. Okay, I'm just teaching you the basics right now. Because if your basics will be clear, this chapter entirely will be clear. Hydrogen spectrum, everything will be done in detail. Just wait for it. This is just the basics. Okay. So my dear students, E by M ratio was calculated with the help of cathode ray experiment. Now the charge present on the electron was calculated with the help of Millikan's oil drop experiment. Right? Now what this Millikan's oil drop experiment exactly is all about? With the help of Millikan's oil drop experiment, how the charge of electron was calculated. Let's get to know about that. But before knowing about that, you should know a term called as terminal velocity. Have you ever heard about terminal velocity? Do you know what terminal velocity is all about? In physics, paper 2, class 11th. Have you heard about terminal velocity? Say yes or no in the chats. Everyone. Say yes or no in the chats. Do you know about terminal velocity? I'm asking you. See, let me give you a slight idea about the terminal velocity. Then only I will be able to teach you the Millikan's oil drop experiment. Then I'll exactly show you how charge on electron was calculated. Have a look, people. Try to understand this. See, for example, I have got an object. This is the object. Its mass is m, right? Its mass is m. Let's say over here it's the ground surface. This is the ground surface. Perfect. And I have got the object over here whose mass is m. Imagine I'm holding this particular object. So what is the speed of this object right now? Its initial speed, its initial velocity is 0 because you're holding it, right? Now, my dear students, when you drop it, what's going to happen? When you drop it, this object will start coming down. This object will fall, for example, this particular trajectory and will start coming downwards. Now, my dear students, when the object reaches a point here, for example, when the object reaches this particular point, when the object is here, can you let me know how many forces are experienced by this object right now at this particular point of time? Due to gravity, it's going to be mg. This is one force due to gravity, right? Since there is air as well, in the atmosphere. I'll say when the object will be going downwards, this particular object will be experiencing a viscous drag as well due to air. Viscous drag as well, right? It will be experiencing viscous drag as well. It will be experiencing viscous force as well. When the object will be going downwards, first of all, at some point of time in between, it will be experiencing two forces, mg downwards and viscous drag or viscous force whose direction will be opposite to the direction of motion. If the direction of motion is downwards, so the viscous force will be upwards. Perfect. When this object will keep on going down, there will be a point at which the viscous force and weight and force due to gravity, they would have got equal. When the object is coming downwards, at some point of time, you'll observe viscous force and mg getting equal. And when the viscous force and mg gets equal, at that point of time, the net force on the electron becomes 0. Sorry, net force on this object becomes 0. This force and this force, at some point of time, if they are equalized, what happens? That means the net force experienced by this object will be 0. And my dear students, when net force experienced by the object will be 0, after that, I would say the object will start moving with the uniform speed. And that uniform speed with which the object moves, when both the forces becomes equal, when the net force on the object becomes 0, that uniform speed which the object attains when the net force on the object becomes 0, that uniform speed is something which you call as terminal velocity, terminal speed. Did you get the idea of what terminal speed is all about? Yes? Right, people? Yeah? Did you get the idea of what this terminal velocity is all about? It is the uniform speed with which the object moves when the net force on the object becomes 0. As simple as that. Now we will try to understand. Now I'm going to make you understand, since you got to know what this terminal speed, terminal velocity is all about. Now it's time to check how the charge on the electron was found. Okay. So my dear students, what exactly I'll be doing? Have a look. I'll be taking a cube over here. Try to understand. This is the cube which I've taken over here. This is the cube. Okay. Now, first of all, I'm dividing this cube into two equal parts. I'm dividing this cube into two equal parts. Perfect. Not just two equal parts. I mean, I'm dividing this cube into two parts, right? I'm dividing this cube into two parts. Okay. Now, my dear students, this particular part with which you are dividing this cube, I'm going to keep a hole at the middle of it. There is a hole at the middle of it. This is the hole at the middle of it. Right? Now. Let me tell you over here in the upper chamber, what I'm fixing here? I'm fixing an atomizer. What is the use of this atomizer? My dear students, with the help of this atomizer, we are going to spray the oil droplets in the upper half of the cube, in the upper chamber of the cube. So these are the oil droplets in the upper chamber of the cube. Okay. These are the oil droplets in the upper chamber of the cube. Now, my dear students, let me tell you one thing. Whenever you keep oil droplet in the vicinity of electrons, whenever you keep oil droplet in the vicinity of the electrons, let me tell you, these oil droplets, this particular oil droplet, it's going to attract these electrons towards itself. I would say these electrons will be adsorbed. The electrons will be accumulated on the surface of the oil droplet, right? When you keep oil droplet in the vicinity of the electrons, I'll say the oil droplet will attract the electrons towards itself, due to which all these electrons will get accumulated on the oil droplet. Now, my dear students, if the electrons are accumulated on the oil droplet, can I say oil droplet carries now the negative charge? Yes, it carries the negative charge. Yes, it carries the negative charge, right? Now we will try to understand few important things. What exactly we are going to do? In this bottom chamber, we are keeping the hydrogen gas molecules. These are your hydrogen gas molecules which are present in this chamber. These are your H2 gas molecules. Now, my dear students, in this bottom chamber, there are H2 gas molecules. So what exactly we'll be doing? We'll be providing some X-rays, and these X-rays, they will be incident on these gas molecules. We'll make sure what just happened to the light. Can you all see me? Is it clear? Can I teach like this with the... What happened to the light? I don't know. Just a second, people. What do we do? Light ही चली गई. But can you see the board? I believe yes. Hope it does not go away. Just a second, guys. Just a second. Be like this. I don't know what happened. Okay, let's go now. Let's go. I hope it remains the same. Okay, guys. So this bottom part of the cube, it contains what? It contains H2 gas molecules. Now you are making X-rays. You are making X-rays to strike these hydrogen gas molecules. And let me tell you, when these X-rays, when they strike the hydrogen gas molecules will ionize. And you know, when hydrogen gas molecules ionize, they lead to the formation of H positives and electrons. So can I say in this bottom chamber, what you will find? You will find electrons, and with the electrons, you will find H positive ions as well. So there will be a lot of electrons present here. And from where these electrons have come? These electrons have come from the ionization of H2 gas. Okay. Now, my dear students, understand. One is asking, sir, when will you take equilibrium? Equilibrium I've already taught on this channel. Go to the playlist, find equilibrium there. Okay. All right. Now, my dear students, what is going to happen? See, in this particular chamber, there are oil droplets. In this particular chamber, there are electrons. Now, there will be a scenario. There will be a scenario when one of the oil droplet will pass through this particular hole and will start coming downwards. Right? Will start coming downwards. A scenario will be there when one of the oil droplet will pass through this particular hole, will come in this particular chamber containing electrons. Now imagine one of the oil droplet has come, it has reached here. My dear students, when oil droplet reaches this particular chamber of the cube, can I say this oil droplet is going to attract these electrons towards itself? Due to which, what's going to happen? Due to which, what's going to happen? I'll say these electrons will be accumulated on this oil droplet, and this particular oil droplet now carries a negative charge. Right? Now I am showing this particular oil droplet right here. Try to understand. This particular oil droplet is going downwards. It's going downwards. Right? It's going downwards. Perfect. Now, my dear students, if this particular oil droplet is going downwards, can you tell me how many forces are experienced by this particular oil droplet here? How many forces are experienced by this oil droplet? This will be mg since it's going downwards. So mg, and opposite to its motion, there will be viscous force. Can I say when the oil droplet will continuously keep on coming down? Can I say a scenario will come? A scenario will come when Fv becomes equal to mg. When this viscous force becomes equal to what? Becomes equal to mg. Perfect. At that point of time, what about the net force? Net force on this oil droplet becomes 0. And when the net force on the oil droplet becomes 0, after that this oil droplet will start moving with the uniform speed. And that uniform speed is what you call as terminal speed. And that terminal speed I'm representing with the nu 1 or V1. What is V1? It is the terminal speed attained by the oil droplet. Right? I hope this is clear. So my dear students, can I say, I'll write over here. In absence of electric field, a scenario came at which viscous force became equal to mg. Right? How do you exactly calculate viscous force? Viscous force is calculated by the formula. I hope you have studied the Stokes law in physics, right? Viscous force is equal to 6 pi neta r v. 6 is constant, pi is constant. This neta is called as coefficient of viscosity. R is the radius of the oil droplet, and this V1 is the terminal velocity with which this oil droplet is moving in absence of electric field. And this particular term is equal to mg. This particular term is equal to mg. Right? Now, my dear students, try to understand. What is this m? M is the mass of oil droplet. M is the mass of oil droplet. So, can we just do one thing? Instead of mass of oil droplet, since density is equal to mass by volume, so instead of mass of oil droplet, can I write density of oil droplet, density of oil multiplied by density is equal to mass by volume, multiplied by volume of oil droplet, right? Multiplied by what? Multiplied by G. Perfect. And my dear students, just try to understand. Density of oil droplet multiplied by volume of oil droplet. Oil droplet is spherical in shape. Its volume is 4 by 3 pi r cube, right? 4 by 3 pi r cube, right? Density multiplied by volume multiplied by G. So can I say one of the R and one of the R gets cancelled out? Absolutely, right? So what can we conclude from here? This particular pi gets cancelled out. So can I calculate the value of R square from here? The value of R square. The value of R square will be equal to 3, 3, 6 are 18. 3, 3, 6 are 18. So this 18, pi got cancelled. This is 18 neta V1 divided by 3, 6, 18 neta V1 divided by what? Divided by density of oil multiplied by 4, and what is there? Multiplied by G. Perfect. So can't you calculate R from here? R will be equal. This will be 9 by 2. So under root of 9 divided by 2, this is neta, this is V1 divided by density of oil droplet multiplied by G. Well, first of all, a question can be asked from here. How do you calculate the radius of the oil droplet? How do we calculate the radius of the oil droplet? So my dear students, the radius of the oil droplet is calculated. Radius of the oil droplet is calculated over here. Now, why did I calculate this radius? Because there is a logic for it. What do I need to calculate actually? I need to calculate the charge present on the oil droplet. In absence, I have not applied any electric field yet. I'm not applied any electric field yet. In absence of electric field, I calculated the radius of the oil droplet. Perfect. Radius of the oil droplet. If you know the coefficient of viscosity, if you know the terminal speed with which the oil droplet moves, if you know the density of oil, G value you know, you can easily calculate the radius of oil droplet. Point number one. Point number two. What actually I'm supposed to calculate? I'm actually supposed to calculate the charge present on the oil droplet. And how exactly you're going to calculate that? Try to understand. Now, my dear students, if we just do one thing, if we connect this particular plate of the cube and this particular plate of the cube, these two plates of the cube, I'm connecting with the external battery. Let's say this is positive, this is negative. Perfect. When I connect them with the external battery, this is positive, this is negative. So this plate is connected with the positive terminal. So this particular plate, it carries the positive charge. This particular plate now carries the positive charge. And this particular plate carries the negative charge. Perfect. Now, my dear students, in presence of electric field, try to understand now. In presence of electric field, what is going to happen? In presence of electric field, what is going to happen? Try to understand. First of all, when the oil droplet comes down, it grabs the electrons. Oil droplet becomes negative charged, right? Now, my dear students, if this oil droplet is negative charge and this particular plate now is positive charge, can I say this plate is going to attract this oil droplet towards itself? Absolutely. This plate is going to attract this oil droplet towards itself. Perfect. So basically, this particular oil droplet in presence of electric field, the oil droplet which carries the negative charge, it is going downwards. So downward force is mg. And this particular plate is attracting it towards itself. So there is electric force. There is electric force experienced by this oil droplet. At the same time, just tell me one thing. If you keep on increasing the voltage of the battery, electric field between these two plates will keep on increasing. And if electric field between these plates keeps on increasing, I'll say this upward force will keep on increasing. There will be a time. If I continuously keep on increasing the voltage, the field between the plates will keep on increasing. There will be a time this FA, since it continuously keeps on increasing, due to increase in electric force, I would say there will be a scenario when this oil droplet starts going upwards. Right? This oil droplet starts going upwards at some point of time. And when the oil droplet starts going upwards, the motion is upwards. Opposite to the motion, there is viscous drag. Now the viscous drag will be downwards. Right? When the oil droplet is going upwards, how many forces are experienced by this oil droplet now? 3 forces. One is electrical force, one is mg, one is viscous force. Can I say a scenario will come when this oil droplet will keep on going upwards? Can I say a scenario will come at which the upward, downward forces would have got equalized? At that particular point of time, what will be the net force? What will be the net force on the oil droplet? That will be 0. Right? The net force on the oil droplet will be 0. And the oil droplet now will be going upwards with a constant speed. And that constant speed is what you call as terminal speed. Right? Let's assume that terminal speed right now is V2. What is V2? It is the terminal speed attained by this oil droplet going upwards in presence of electric field. So in presence of electric field, I must say Fe will be equal to viscous force now plus mg. Right? Clear? Clear, guys? Now, what is Fe? It is the electrical force, which is charge multiplied by electric field, is equal. Viscous force is going to be 6 pi neta r. Should I write V1 or V2? I'll write V2. Perfect. In presence of electric field. Plus what? Plus mg. Already you know mg, it's a constant. mg, it's a constant. M is constant, G is constant. mg will be equal to 6 pi neta r V1. So this is 6 pi neta r V1. Perfect. Now, my dear students, if you can write something like this, QE is equal to 6 pi neta r is common. So it's going to be nu1 plus V2. What is V1 plus V2? What is V1? V1 is the terminal velocity attained by the oil droplet in absence of electric field. V2 is the terminal velocity attained by the oil droplet in presence of electric field. V1 is the terminal velocity attained by the oil droplet when it was going downwards. V2 is the terminal velocity attained by the oil droplet when it's going upwards. Clear? Clear, my dear students? So Q from here will be equal to 6 pi neta R V1 plus V2 divided by what? Divided by E. My dear students, look at all the parameters which are involved in this equation. Look at all the parameters which are involved in this particular equation. You have got a constant, coefficient of viscosity. Value already we know. Radius of the oil droplet, we already have calculated it. V1, we already know. V2, we already know. Electric field strength between these two plates with the help of this particular battery, we already know. So can't we calculate Q from here? What is Q? Q is the charge on oil droplet. And you know charge on oil droplet is due to the electrons which are present on the oil droplet. My dear students, it was observed the minimum charge present on the oil droplet was, its magnitude was 1.6 into 10 raised power minus 19 coulomb. This was the minimum charge present on the oil droplet. And the minimum charge present on the oil droplet was, sign is minus because it's electron, right? It was this much. When the same experiment was carried out one more time, the charge on the oil droplet came out to be 2 times this value. When the same experiment was carried out one more time, the charge on the oil droplet came out to be 3 times this value. Similarly, 4 times, 5 times. So it was believed that after performing this particular experiment many a times, it was believed that charge present on the object will be the integral value of this particular value. It will be the integral value of this particular value over here. This particular value, you call it as E. And it was finally believed that the charge present on any object is always the integral multiple of E. Perfect. Quantization of charge, you would have heard. Charge remains quantized. It will be the integral multiple. I hope this particular thing is clear. So you got to know how charge on oil droplet was calculated. You got to know the radius, etc., etc. So take care of these two statements. First statement. From this experiment, he calculated the minimum charge present in the oil droplet was this much. Only the magnitude wise I'm saying. And any particle, if charged, will have the charge which is equal to the integral multiple of this particular value. Right? So Q came out to be N times E over here. What is E? E is this particular thing. I hope this is clear to everyone. So, with the help of the Millikan's oil drop experiment, the charge on electron was calculated. And you got to know how exactly. Hope all these concepts are clear. Now, my dear students, if all these concepts are clear, can we solve this question? Look at the question carefully. Can we solve this question? Look at the question. Read the question carefully. Read this question carefully. As per this particular question, in an oil droplet experiment, the terminal velocity of oil droplet was this much in absence of electric field. So basically V1 is given 1 meter per second in absence of electric field and 2 meter per second upwards in presence of electric field. So V2 is given 2 meter per second in presence of electric field, right? Electric field of strength. Electric field strength is 6.75 into 10 raised power 6 pi volt per meter, right? Electric field strength. Density of oil droplet is also given. Density of oil droplet is given as 1 gram per ml. And coefficient of viscosity, neta, is given 2 into 10 raised power minus 5, right? Well, long back there was one question asked in NEET in physics. What are the dimensions of coefficient of viscosity? Can you let me know in the chats? Long back, I think in 2014 or 13, something around that. What are the dimensions of coefficient of viscosity? You can calculate it from the result. F is equal to 6 pi neta RV, right? I think it used to be M1L minus 1 T minus 1, something around that. I think so. Anyways, have a look. So neta is given. So what are we supposed to calculate? First, we are supposed to calculate the radius of oil droplet. Radius of oil droplet. Do we know the result? Do we know the result to calculate radius? R is equal to, R is equal to, R is equal to. How do we get the R value? Right now we got the R value, right? R is 9 by 2. R is under root of 9 by 2. Neta. Neta is something we know. V1 something we know. Density of oil we know. Gravity, acceleration due to gravity. This is something we know. So you can calculate R. Second is, what was second thing? So radius of oil droplet you can easily calculate. What about the second thing? The charge on the oil droplet. Charge on the oil droplet you can calculate with the help of this particular result. 6 constant, pi constant, neta you know. Radius you have calculated. Radius you have calculated. V1, V2 is given. Electric field strength is given. So from here you can calculate the charge present on the oil droplet as well. Is this particular thing clear to you people? Let me know once in the chats quickly. Yes? Is it clear to you? So this is how your cathode ray experiment was done. E by M ratio was calculated and then charge on the electron through the Millikan's oil drop experiment was calculated. Now, you must have heard about the anode ray experiment as well. Have you heard about anode ray experiment? Similar type of experiment was carried out. Anode ray experiment. Anode ray experiment. It was a different scientist who did this particular experiment. What was the name of that scientist? It was Goldstein. It was Goldstein, right? And with the help of this particular experiment, what was discovered? It was proton. Proton was discovered. That means your anode rays were discovered. Anode rays were discovered. Now you must be thinking how these anode rays were discovered. In a similar way, the way we discovered the electrons, in the similar way, we are going to discover the protons as well. Let's have a look how exactly. See guys, try to understand. The same tube I'll be taking, the same glass tube I'm taking, right, which is 60 centimeters long, you know it. You call this particular tube as the Crookes tube. Now I'll be comparatively fast, okay? You know all these things. Now over here, what do we have? We have got a vacuum pump. Why do we need this vacuum pump? To control the gas inside this particular chamber. Which gas do we use in the beginning? H2 gas, right? H2 gas. Imagine this is one of the metal strip. This is one more metal strip. Now, my dear students, one of the metal strip, you are going to connect with the negative terminal, positive, negative, positive. And over here, this positively charged. This particular strip is connected with the positive terminal of the battery. So, negatively terminal means this carries negative, this carries positive. Now, my dear students, this side of this particular glass, the other side of the glass, it is coated with zinc sulfide. It is coated with zinc sulfide. And you know the property of zinc sulfide. If any particle strikes it, glow will be there, right? Glow will be there. Perfect, people. This is something which we already know. Now, which gas is there in the container? It's H2 gas in the container. It's H2 gas in the container. My dear students, try to understand few important things now. Since already you have taken H2 gas. Now, this is a high voltage battery. When you provide the voltage of 10 raised power 4 volts, when the pressure of the gas is very, very, very low, when the pressure of the gas is very, very, very low, what is going to happen? Can I say the gas in the container, it will ionize? Absolutely, it would have ionized. Due to which, there will be positively charged ions over here. And at the same time, there will be electrons as well. There will be electrons as well due to the ionization of the gas. We know it already. We know it already, right? Yes. Now, my dear students, try to understand. Only one different thing I'm doing over here. This particular cathode which I'm using over here, I'm keeping some holes in this cathode. Some holes are kept over here. And this particular cathode, I'll be calling as perforated cathode. This is your perforated cathode. And this is your normal anode. This is your normal anode. Now, my dear students, when the battery was turned on, when the voltage of the battery was given as 10 raised power 4 volts, what did Goldstein observe? He observed some bright spots got created just behind these holes, right? He observed that some bright spots got created just between these holes on the zinc sulfide screen. My dear students, what he concluded from there? What he concluded? He concluded there are some invisible rays. There are some invisible rays which seems to be coming from the anode, crossing these holes, and striking the zinc sulfide. That's the reason why these bright spots are created. And these invisible rays, which seems to be coming from the anode, right? He called these invisible rays as the anode rays. So, the invisible rays which seems to be coming from the anode were called as anode rays. My dear students, and these anode rays are also called as canal rays. Why? Because when they pass through the perforated tube, when they pass through the perforated electrode, they traveled like the water in a canal travels, like a streamline. Okay? You call them as the canal rays as well. Perfect. So this is how these canal rays, these anode rays were discovered. Now, my dear students, after the discovery of these anode rays, it was again important to observe, to check the properties of these anode rays. Now, it was the time to go for the properties of these anode rays. The same things were repeated. Let me show it to you directly now. The same things were repeated. Let me show it to you directly. My dear students, same things were repeated. First thing, anode rays, they travel along a straight line path because they cast shadow of the object placed in between their path. The same thing which was done there. For example, if you place an object over here, this is the object, imagine. This is the object. And behind the object, you are placing a screen. Or the screen is already placed over here. Zinc sulfide screen. Now, my dear students, this object which you are placing over here, when you turn the battery on, when you keep the voltage of the battery 10 raised to 4 volts, when you decrease the pressure of the gas, what was observed? It was observed that a sharp image of the object was created here. Which is only possible if these anode rays, if they travel in straight lines. Right? So first conclusion was done. Your anode rays, they travel in the straight lines. Point number one. Point number two, the same scenario, my dear students. Point number two. When a light paddle wheel, was kept over here, this light paddle wheel started to rotate, right? Which is only possible if the anode rays are made up of some material particles carrying certain mass, right? So this was the second conclusion. Anode rays, they rotate a light paddle wheel when placed in their path. This shows that anode rays are made up of some material particles which carry certain mass, right? Now, since it was checked that anode rays travel in straight lines, they are made up of some material particles carrying certain mass. Now, it was important to check whether they have got some charge or not. So for that purpose, a magnet was introduced. And in presence of that magnetic field, I would say anode rays, they deflected their path, which is only possible if anode rays are made up of some material particles and those material particles carry certain charge. Right? So it was believed that your anode rays, they are made up of material particles and those material particles are charged. Now the point was, which charge was present on the material particle? For that, again, two plates were used, one carrying positive, one carrying negative. And these anode rays, they moved towards a negatively charged plate, right? Which is evident. Now it is evident the anode rays are made up of some material particles which have got some mass, which carry some charge. And since these anode rays are moving towards the negatively charged plate, your cathode rays, they were moving towards the positively charged plate. Here, the anode rays are moving towards the negatively charged plate. From that, you can conclude your anode rays are made up of some positively charged particles. So it was believed that your anode rays are made up of the positively charged particles. Perfect. Perfect, guys. And after that, these positively charged particles of which these anode rays were made up of, these positively charged particles were called as protons. Perfect. So I believe all these things are clear. These anode rays of which these positively charged, these anode rays are made up of some particles. Those particles carry certain charge. They have got some mass. They carry the positive charge, and these positively charged particles were called as protons. Right. So if I ask you what these protons exactly are, since you know hydrogen gas in the beginning it got ionized, right? Hydrogen gas in the beginning got ionized. So you got positively charged ions over here, right? And negatively charged ions, negatively charged electrons over here. Now, which positively charged ions these were? Since you had taken H2 gas, so these were your H positive ions. So these were basically the H positive ions. Which were moving towards the what? Towards this zinc sulfide. And those H positive ions were striking this surface and creating the bright spots. And this positively charged ion is basically what you call as proton. Right? So basically your anode rays, they are made up of what? They are made up of positively charged ions. And when you keep the gas as H2, that positively charged ion is basically H positive. And this H positive is something which you call as proton. What is H positive exactly? From hydrogen. In hydrogen, there is one electron, one proton. If you take one electron out, it becomes H positive. In H positive, there is no electron basically, right? It is H positive. This H positive is something which you call as proton. Perfect. Now tell me one thing. Now the point is how the velocity of these anode rays was calculated. The similar way, my dear students. The similar way. Anode rays, they were simultaneously passed in electric and magnetic field, right? Due to which these anode rays, the anode ray, what it experienced two forces. One was electric force, one is magnetic force. And those forces were balanced. FE and FB was balanced. FE was Q multiplied by E, and FB was Q multiplied by V multiplied by V. Q got cancelled. So velocity with which the anode rays move, that was calculated with this particular result. Right? That was calculated with this particular result. Velocity with which the anode rays move is equal to electric field divided by magnetic field. Perfect. Same scenario which we already did in case of cathode rays. In the similar way, the velocity with which the anode ray moves, it was also calculated. Perfect. It was also calculated. Perfect. I believe it's clear to everyone. Now, it was the time to calculate E by M ratio. How you guys are going to calculate the E by M ratio? My dear students, if a charged particle is introduced in some potential difference, its potential energy starts getting converted into kinetic energy. Already told. Potential energy is Q multiplied by V. Kinetic energy is half of mv square. Right? So V square is simply going to be equal to 2 times Q. V divided by M. V square is going to be E square upon B square. So E square upon B square is equal to 2 times Q. V divided by M. What is Q? Q is the charge on the proton. M is the mass of proton. So Q by M. Q I'm representing with E. So it is basically E by M. So E by M will be equal to what? It will be equal to E square divided by 2 times V square multiplied by capital V. Right? Now already this electric field strength, you already know. Right? Perfect. Perfect, guys. Or V is the potential difference between these two rods, you already know. Magnetic field strength, you already know. So E by M ratio of the anode rays was calculated. E by M ratio of proton was calculated. By knowing, since all these values were familiar, right? All these values were familiar. If you put all these values in this result, you'll easily calculate E by M ratio. And E by M ratio, with the help of this E by M ratio of anode rays was exactly calculated. Right, people? Okay? Is it clear? Is it clear? This was the calculation done, which I showed you. And let me tell you, E by M ratio of anode rays It was found out to be this much, 9.58 in 10 raised power 7 coulomb per kg. Right? This was the E by M ratio of what? This was the E by M ratio of your anode rays containing when H2 gas was basically in the container. Now you tell me one thing. Since you took H2 gas in the beginning, perfect, and in case of H2 gas, it got ionized into H positive and electron. Those H positives then moved, formed the anode rays. Those H positives formed the anode rays basically. Right? That's something which is understood. That's something which is understood. And when the gas was H positive, E by M ratio came out to be this much. I guess students, if you change the gas, will the positively charged ion be same or different? Let me know. If you change the gas, will the positively charged ion in the container be same or different? When you change the gas, that gas ionizes. Perfect. The positively charged ion will be different. If the positively charged ion is different, will the E by M ratio of anode ray, will it come out to be same or different? It will come out to be different. E by M ratio will come out to be different. Listen carefully what I'm saying. Initially, I kept H2 gas. And that H2 gas that got ionized as H positive and electron. Electrons started moving in one direction. H positive ions started moving in one more direction. Electrons gave rise to cathode rays, right? And the positively charged H positives, they gave rise to anode rays. Perfect. So when you are using H2 gas, your anode rays at that point of time are made up of H positive ions. Now imagine you have used the H2 gas. Your anode rays, they are right now made up of H positive ions, right? And the E by M ratio, when you are using H2 gas, is coming out to be this much. Now, you're changing the gas. If you're changing the gas, what will happen to the positively charged ions? If you change the gas, will the positive charged ions be H positives in the container? No. It depends on the gas which you have taken. Right? It depends on the gas which you have taken. So on changing the gas, these positively charged ions in the container will change. Right? So that means at that point of time, your anode rays won't be made up of H positives. They'll be made up of those cations which are coming from the gas. So on changing the gas, will the E by M ratio of anode rays be same or different? It will be different. Because this is the E by M, this is the E by M. When your anode rays are made up of H positive ions. If you change the gas, your anode rays, they will be made up of some other positively charged ions. So E by M ratio of those other positively charged ions will be different. So tell me whether E by M ratio of anode rays, whether it depends on the nature of the gas taken or not. Tell me that. Whether it depends on the nature of the gas taken or not. Yes, it does. Okay. So do remember the nature of anode rays. That is if I talk about E by M ratio of anode rays, it depends on the nature of the gas taken, number one. Number two, it depends on the material of which electrode is made up of. That too. Okay, that too. Now, since you have calculated E by M ratio of anode rays, now it was the time to calculate. It was the time to calculate what? To calculate some other things. Just a second. Just a second, guys. Just a second. It was the time, since E by M ratio of electron was calculated, right? Charge on electron was also calculated. Perfect. If E by M ratio of electron you know, charge on electron you know, mass of electron can be easily calculated. Right? I'm talking about cathode rays. E by M ratio of electron you already know. The charge present on electron you have already calculated with the help of Millikan's oil drop experiment. So mass of electron can be calculated. In the similar way, mass of proton can be also calculated. Imagine that you have taken H2 gas in the container. So your anode rays are right now made up of H positive ions. And for this H positive E by M ratio, we already know. How much is that? E by M ratio is equal to this much. Right? Now, charge on proton is 1.6 in 10 raised power minus 19 divided by mass of proton is equal to this much. So from here, your mass of proton was calculated. Perfect. So mass of proton came out to be 1.67 into 10 raised power minus 27 kg. So E by M ratio for particles constituting the anode rays, it depends on what? It depends on the nature of gas taken. Because if you change the gas, this cation keeps on changing, right? This cation keeps on changing. I believe this is clear to everyone. Perfect, guys. Now there are some conclusions at the end which you have to remember, and I want you guys to remember these conclusions. See, let me quickly recap things. So first of all, cathode ray experiment was done through which electrons were discovered. From the same experiment, E by M ratio of electron was calculated. Through Millikan's oil drop experiment, charge on electron was calculated. E by M ratio we know for the electron. Charge we have calculated. So mass of electron was calculated then, right? Similarly, in case of anode rays, anode rays when the gas is H2. Perfect. Anode rays when the gas is H2. First, E by M ratio of anode rays was calculated. Number one. Number two, charge of the protons which form the anode rays, it was calculated. After that, mass of proton was calculated. Perfect. And all these things are written over here. Mass of electron came out to be this much, right? Charge on electron. Perfect. Mass of proton, right? This particular result is important. Mass of proton is 1837 times mass of electron. Charge of proton is 1.6 into 10 raised power minus 19 coulombs. Perfect. So do remember these 3-4 points over here. These are important. Perfect, guys. Is this clear to everyone? Any doubt till here? Any doubt till here? Tell me in the chats quickly. Tell me in the chats quickly. Now, there was discovery of neutron as well. How neutron was discovered? It is a very simple thing. This is something which you are not supposed to go into the details, right? See, guys. Neutron was discovered by Chadwick, first of all. He performed some scattering experiment in which he bombarded some light elements like beryllium and boron with the fast moving alpha particles. Now, first of all, what are alpha particles exactly? Right? What are alpha particles exactly? See, for example, you take helium atom. Atomic number 2, mass number 4. In helium atom, you have got 2 electrons. If you take these 2 electrons out, it will get converted into He di positive, right? So this He di positive is something which I call as helium nuclei. This is something which I call as helium nucleus because it does not contain any electron now. Initially, it had 2 electrons. Now you have taken those 2 electrons out. Now no electron in He di positive. So this helium nucleus now, it is only helium nucleus, right? This is nucleus of helium and there are no electrons. So this helium nucleus. This helium nucleus is something which you call as alpha particle. Now, let me tell you, when these alpha particles, when this helium nuclei, when these alpha particles were bombarded on what? On beryllium and boron, some new particles were introduced. Some new particles were introduced, right? And those particles which were neutral, which did not carry any positive charge or negative charge. Those new particles which were neutral, which did not carry any positive charge or negative charge, whose mass was almost equal to the mass of proton, these neutral particles, whose mass was almost equal to the mass of proton, were termed as neutrons. So basically, when beryllium was bombarded with alpha particle, carbon was produced, and with carbon, this new particle was produced, was emitted basically, right? And this new particle, it did not carry any charge. Its mass was found out to be almost same as that of mass of proton, and this neutral particle was called as basically neutron. In the similar way, when alpha particle is striked on what? On boron, you get nitrogen, and with nitrogen, a particle is basically emitted. This is the same particle basically. This is the same particle which does not carry any charge, right? Which does not carry any charge, and its mass is almost same as that of mass of proton. So you call this as basically neutron. So that's only thing which you need to remember about neutron, nothing else, right? So all these things are really important, guys. Again, I'm telling mass of electron you need to remember, charge on electron, mass of proton you need to remember. Mass of proton is 1837 times the mass of electron. Mass of neutron is this much. The charge on neutron is 0. It's neutral. Perfect. Perfect, people. I hope it's clear till here. Now, after the discovery of these subatomic particles, lot of models, lot of atomic models were given, right? And almost all were rejected basically. The first model related to the atom was your Thomson's model. I believe you already know this. This was also called as watermelon model. Now, what did it say basically? This is the simplest among all, right? I said this you should have studied on your own. Anyways, in 1904, Thomson proposed that the atom is a positively charged sphere. The atom is the positively charged sphere in which electrons are uniformly distributed, as the result of which atom is electrically neutral. So basically this Thomson's model, how it looks like. As per Thomson's model, the atom looks like a watermelon. The atom looks like a watermelon. This red colored part is the positively charged, is the positive charge. This red colored part is the positive charge. And in this positive charge, the electrons are uniformly distributed, as a result of which the total positive charge and the total negative charge in the atom is equal. Therefore, atom is electrically neutral as per this particular model. As per this particular model, right? You call this as watermelon model, plum pudding model, right? Perfect. So my dear students, again I'm telling you, Thomson proposed that your atom, it looks like what? It looks like a watermelon. The red colored part is the positively charged sphere, right? The red colored part is the positive charge, right? In which electrons are your seeds. They are uniformly distributed basically. They are uniformly distributed, as a result of which the total positive and total negative charge is equal. Hence, atom is electrically neutral as per Thomson. So what was the drawback of this particular model? My dear students, it could not satisfactorily explain the stability of that. What does that mean? That means, see, these seeds are basically the negatively charged. These are the electrons. He could not explain these negative, they can ripple. When they ripple, due to the repulsions, energy of the atom increases. If the energy of the atom increases, stability decreases, right? If the energy of the atom increases, stability decreases. So he could not explain that part. Why these electrons which are embedded over here, why they do not ripple, right? Why energy of the atom does not increase, why the stability of the atom does not decrease. He could not explain that. And apart from that, one more thing. He could not explain the scattering experiment done by the Rutherford. Now the point is, what is scattering experiment? Let's get to know what the scattering experiment exactly is all about. My dear students, Rutherford, he did one very simple experiment, right? He did one experiment through which we are going to introduce one more term over here. That is nucleus. Let's have a look. What Rutherford exactly did. My dear students, Rutherford, he took a lead block. He took a lead block over here. This is the lead block which was taken by Rutherford. And in this particular lead block, an alpha particle emitter was kept. An alpha particle emitters are your basically radioactive elements. So basically a radioactive element like polonium was taken in this lead block. Perfect. Now what is going to happen? This is the alpha particle emitter. It's going to emit the alpha particles. These are your alpha particles. And you already know what these alpha particles are. Perfect. So these are the alpha particles which are emitted by this alpha particle emitter. Now, my dear students, over here, I'm going to keep a gold foil. Right? But just to make you understand it in a better way, imagine you're keeping a gold atom over here. This is a gold atom, for example, right? And behind this gold atom, you're keeping a circular screen. And this particular circular screen is coated with zinc sulfide. Imagine it is coated with zinc sulfide. This particular screen is coated with what? It is coated with zinc sulfide, right? It is coated with zinc sulfide. And you know the property of zinc sulfide already? Now, for example, we will try to understand one simple thing. These alpha particles which are coming out from this alpha particle emitter, right? They are made to strike. They are made to strike towards this gold foil, towards this gold atom. And there were some observations. Which Rutherford concluded, right? What were the observations basically? He saw some of the alpha particles, very few alpha particles were getting deviated by very small angles, right? He saw some of the alpha particles, very few alpha particles, they were getting deviated through small angles. He saw majority of the alpha particles, right? He saw majority of the alpha particles cross the gold atom without showing any deviation. And how exactly he saw that? He saw only this part of the screen glowing and this part of the screen glowing. He saw these two parts of the screen glowing basically, right? In the middle, the screen was not glowing. In the middle, the screen was not glowing, right? So first of all, what all things he observed? He observed majority of the lines, they were passing the gold atom undeviated, right? A very few alpha particles, they were getting deviated by very small angle. And one of the alpha particle, 1 in 20,000 alpha particles, 1 in 20,000 alpha particles, they deviated at an angle of 180 degree. That means 1 alpha particle out of 20,000, right? It got deviated, right? It reflected back. It went, it came back to the same path. So it showed the angle of 180. It got deviated back at an angle of 180. Now, from these observations, what were the conclusions made by Rutherford? Now, I believe you can easily say the conclusions. The first observation was majority of the alpha particles, they passed undeviated. Very few alpha particles, they got deviated at very small angles. 1 in 20,000, it got reflected back at an angle of 180 degree. Now, people, what can you conclude from here? What can you conclude from here? The first conclusion. Most of the alpha particles, they passed undeviated. Therefore, he concluded the most of the region of the atom, that is empty. Most region of the atom is empty. That's why most of the alpha particles are passing undeviated. They do not deviate at all. Point number 1. Point number 2. Few alpha particles were deviated through small angles. And he concluded atom contains positive and negative charge in equal amounts. So the atom as a whole is electrically neutral. What does that mean? Since very few alpha particles were deviated, how an alpha particle will get deviated? Imagine this is the alpha particle. It's moving, for example. How it is moving in this particular direction. Now, how come it will get deviated from its path? If on the way it finds some charged particles, let's say negatively charged particle is here, one more positively charged particle is here. Imagine the alpha particle is moving in this direction, right? On the way, this alpha particle, it finds negative charge and positive charge. And you see this negative charge will try to attract it towards itself. This positive charge will repel the alpha particle, right? Since very few alpha particles, they got deviated at some angles, very few alpha particles, they changed its path. Now, what can you conclude from here? You can conclude atom contains some charges, right? Atom contains some charges which are basically opposite charges. Perfect. And they are equal in amount, due to which atom is electrically neutral. The most important thing over here, what is that? Is this particular conclusion. A very few, 1 out of 20,000 alpha particles. 1 out of 20,000 alpha particles deviated at an angle of 180. So what could he conclude from there? If 1 of 20,000 alpha particles, it got reflected back at an angle of 180 degree, he concluded the whole positive charge of an atom, it is concentrated in a very small region, and that small region he called as a nucleus. If you try to understand this, look here. I told you this part, it did not glow. That means just over here, there will be some huge mass which is concentrated here, right? There will be some huge mass which is concentrated here. So Rutherford said the whole mass of the atom is concentrated at the center. The whole mass and the entire positive charge. It is concentrated at the center, due to which the alpha particle, which carries the positive charge, it's coming closer, and as soon as it comes closer, it is experiencing repulsions from this nucleus, which carries the positive charge, right? And the stage comes when it gets reflected back. And this particular small region in which the whole mass and the entire positive charge is supposed to be concentrated, right? Is supposed to be concentrated. This particular small region is something which you call as nucleus. So the major discovery of your Rutherford's alpha particle scattering experiment was the discovery of nucleus. Is this particular point clear to you? Is this particular point clear to you? Right? Since one of the alpha particle, it got deviated at an angle of 180. That means alpha particle is getting deviated. So as soon as the alpha particle comes closer, it will be experiencing some repulsions. As soon it comes more closer, more repulsions. More repulsions means it gets reflected back. And why the alpha particle will be getting repelled? Because the atom should contain the entire positive charge at the center. And that positively charged nucleus basically, that will be repelling the alpha particle which carries a positive charge, right? Due to which it gets reflected back. Is this clear, people? Let me know once in the chats. Perfect. So I hope you got to know the conclusions made by Rutherford. So my dear students, few more things. After the alpha particle scattering experiment, after the conclusions which were made by Rutherford, right? Rutherford gave one model related to the atom, which he called as Rutherford's nuclear model. And as far as this particular model is concerned, whole positive charge in the atom is concentrated in a very small volume, and this small volume was called as nucleus. Point number one. Size of the nucleus. Size of the nucleus is very small as compared to size of atom, right? In general, if the radius of atom is 10 raised power minus 10 meters, then the radius of nucleus will be 10 raised power minus 15 meters. This is something which he said, right? And my dear students, one result which Rutherford gave to calculate the radius of the nucleus, he said radius of the nucleus is equal to R naught, A raised power 1 by 3 centimeters. This R naught was a constant whose value lies from here to here. And if for calculation purposes, R naught value will be taken as 1.33 into 10 raised power minus 13 centimeters. Sorry. So R naught value for calculation purposes will be taken as this much. What is A? A is the mass number of the atom, right? Whose radius of nucleus is to be calculated. For carbon, A value will be 12. Right? For nitrogen, A value will be 14. So A is just the mass number, nothing else. Right? A is just the mass number. So this is the result by means of which you can calculate the radius of the nucleus. R is equal to R naught, A raised power 1 by 3. Let's say you want to calculate the size, you want to calculate the radius of the nucleus of carbon. That means A value has to be 12. R naught value will take as 1.33 into 10 raised power 1.33 into 10 raised power minus 13 centimeters. And at the end, you will get the radius in centimeters. So this result you have to remember at the same time. So few more points related to Rutherford's nuclear model. As far as the Rutherford's nuclear model is concerned, electrons are revolving at very high speeds around the nucleus in different concentric circular paths. And these concentric circular paths are called as orbits. So as per Rutherford, if this is the nucleus of the atom, the electrons will continuously keep on revolving around the nucleus in circular paths, right? And these concentric circular paths in which the electron keeps on revolving continuously, these concentric circular paths were termed as the orbits. They were termed as the orbits. Perfect. Now you must be thinking, what were the limitations of this Rutherford's model, right? What were its limitations? My dear students, there is a scientist called as Maxwell. What Maxwell suggested, according to Maxwell, whenever a charged particle undergoes acceleration, it emits radiations. Radiation is energy basically. So it emits energy. So if I talk about what Rutherford said this is the nucleus. And for example, these are the electrons revolving around the nucleus in circular paths, right? These are the electrons revolving around the nucleus in circular paths. If I ask you something like this, imagine the electron is here, right? Imagine the electron is here. What will be the direction of this particular electron? Draw the tangent. This is the direction of electron. When the electron reaches here, this is the direction. It reaches here, this is the direction. This is the direction. As the electron revolves, is the direction of electron continuously changing? The direction of electron is continuously changing. If the direction changes, what does that mean? That means velocity changes due to change in direction. And change in velocity leads to acceleration. So can I say this particular electron right now is getting accelerated. Its direction is continuously changing. It is getting accelerated. And when a charged particle undergoes acceleration, as per Maxwell, it emits radiations in the form of energy. It emits radiation. Radiation is the form of energy, basically. So if this electron is being accelerated, it will be continuously emitting energy. If the electron is continuously emitting energy, the energy of electron should continuously keep on decreasing, right? The energy of electron should continuously keep on decreasing, right? So the radius of the orbit should continuously keep on decreasing, and eventually the electron should fall into the nucleus, right? But the electron does not fall in the nucleus. Rutherford could not explain this particular point as well. He could not explain why electron does not fall into the nucleus. Perfect? He could not explain that. So this was the first limitation. Perfect? This was the limitation. The second limitation was he could not explain the line spectra of hydrogen. What is line spectra of hydrogen? You will get to know that in the upcoming session. Not now. Okay? Just remember it as such. Remember it as such. Now, my dear students, there is one more important thing. There is one more important thing. Have you heard about distance of closest approach? Distance of closest approach. What this distance of closest approach is all about? See, it's a very simple thing. There is nothing here as well. Okay? See, guys. See, guys. Imagine that you have got the atom and this is the nucleus of the atom. Imagine that this is the nucleus of the atom. The atomic number of the atom is, for example, Z. If the atomic number of atom is Z, that means the atom contains Z protons. If the charge on one proton is E, then the charge on Z protons is Ze, right? So this is the nucleus of the atom, right? I'm assuming that atomic number of the atom is Z. So the atom contains Z protons. If charge on one proton is E, the charge on Z protons will be Ze, right? It is Ze. Perfect. Now imagine here you have got the alpha particle. Imagine here you have got the alpha particle. Perfect. In the alpha particle, there are two protons, no electrons. One proton carries the charge E. So two protons carries the charge 2 times E. This is the charge on alpha particle, 2E plus 2E. This is the charge on the alpha particle. Now imagine this particular alpha particle is coming closer to the nucleus, right? Imagine this particular alpha particle is coming closer towards the nucleus. Now tell me, when this particular alpha particle, which carries a positive charge, if it comes closer, the distance between alpha particle and nucleus, it decreases. If the distance between alpha particle and nucleus decreases, can I say, as the alpha particle goes closer, it will be experiencing more repulsions from this particular nucleus? Absolutely, it will be experiencing more as this alpha particle keeps on going closer, closer, closer. It will keep on experiencing more repulsions due to the nucleus, right? Can I say a point will come, a time will come, a stage will come, since alpha particle is coming closer, repulsions experienced by alpha particles are increasing. I'll say kinetic energy of alpha particle is decreasing. It is decreasing, it's decreasing. There will be a scenario when this alpha particle will momentarily come at rest and will go back in the same direction. Will get deflected at an angle of 180, right? So a point will come, a time will come at which this alpha particle will momentarily comes at rest. And after that, it gets deviated back at an angle of 180. Perfect. I'm talking about that alpha particle, 1 in 20,000, which came closer. Repulsions on alpha particle is increasing from the nucleus. Kinetic energy of alpha particle is decreasing. Stage will come when this alpha particle will momentarily come at rest and will get deviated back at an angle of 180. Now, my dear students, the distance from this particular point, till the center of the nucleus, the distance from this particular point till the center of nucleus, it is represented by R0. And this R0 is something which you call as distance of closest approach. Did you get the idea of what this distance of closest approach is all about? It is the distance from this particular point at which the alpha particle momentarily comes at rest and takes a U-turn. right? The distance from there till the center of the nucleus, this is called as distance of closest approach. Now, my dear students, how do we calculate the distance of closest approach? That's the point. That is the point. How do you calculate this particular distance? See. First of all, as the electron comes closer, repulsions experienced as the alpha particle comes closer, repulsions experienced by the alpha particles are increased. The kinetic energy of the alpha particle is decreasing. It is decreasing. It's decreasing. If the kinetic energy of alpha particle is decreasing, that means potential energy of alpha particle is increasing, right? Potential energy of alpha particle is increasing. This is the point at which the kinetic energy of the kinetic energy of the alpha particle becomes 0. And I would say entire kinetic energy has got converted into the potential energy. At this particular point of time, I would say entire kinetic energy of this alpha particle has got converted into potential energy, right? What about the kinetic energy of the alpha particle? It is half of mass of alpha particle multiplied with velocity of alpha particle square. Potential energy. How do you calculate the potential energy? You must be knowing potential energy is nothing. It is K Q1 Q2 divided by R. This is how you calculate potential energy, right? So this is K. What is Q1? Q1 is, for example, the charge in the nucleus. How much is that? That is ZE multiplied by Q2. Q2 is the charge on the alpha particle. That's 2 times E divided by R. R is this particular distance. R is this particular distance, which is basically R naught. Perfect. So from this particular equation, you can say half of mass of alpha particle, velocity of alpha particle square is equal. This is going to be K Z E square divided by R naught. So from this particular equation, you can easily calculate R naught value. R naught will come out to be how much? R naught will come out to be 2 times K Z E square divided by mass of alpha particle multiplied by velocity of alpha particle ka square. So this is how you calculate the distance of closest approach. This is how you calculate the distance of closest approach. Perfect. And this K already you must be knowing, right? It is 1 upon 4 pi epsilon naught, right? Its value is 1 upon 4 pi epsilon naught, which is 9 and 10 raised power 9, something around that. So this result you have to remember. By means of this particular result, you get to know the distance of your closest approach, my dear students, right? Perfect. And from this expression, you can conclude anything. You can conclude anything. Is this part clear to you? Did you get to know how this distance of closest approach was found out? Perfect, guys. Perfect. So, my dear students, what this Planck's quantum theory exactly is all about? Try to understand, right? Step by step, I'll let you know the things. First of all, the theory which we are going to talk about, the Planck's quantum theory, let me first of all tell you, this Planck's quantum theory, it supports the particle nature of light. It supports the particle nature of light. As you all must be knowing till now, since you already must be knowing that light has got the dual nature. It has got wave nature as well as particle nature. This particular theory which we are going to discuss today, it is going to support the particle nature of light. Right? It is going to support the particle nature of light. Point number 1. Point number 2. As per Planck's quantum theory is concerned, energy is transmitted. Energy is transmitted in the form of small packets, or I can say in the form of small units. And those small packets or small units are called as quanta. What it exactly means. Try to understand what exactly I'm going to talk about. See guys, as per Planck's quantum theory is concerned, energy is basically transmitted in the form of small packets or you can say in the form of small units, and you call those small units exactly as quanta. Now, what it exactly means? What it exactly means? My dear students, for example, let's say this is some source of energy, right? Let's say this is some source of energy. The source is continuously emitting energy in the form of a radiation. Assume that this particular source, it is continuously emitting energy in the form of radiation, right? Now, as per Planck's quantum theory is concerned, energy is transmitted in the form of small packets. So, my dear students, let me tell you one simple thing. This particular source of energy, since it is emitting radiations, radiation is a form of energy basically, right? Since this particular source, it is emitting radiations. Now, those radiations, for example, let's say this is one of the radiation which I'm showing over here. My dear students, the radiations, whatever radiation it is, radiations, they consist of small packets. They consist of small packets of energy, right? And these particular small packets, I mean, one particular small packet is something which we call as quantum, right? And a lot of these small packets are what we call as quanta. Perfect. So very simple and basic thing. Whenever I'll be talking about Planck's quantum theory from now onwards, only one thing should strike my mind. What is that? Energy is transmitted in the form of small packets, right? Small units, and these small units are what we call as quanta. For example, this was the source of energy which was continuously emitting radiations. Perfect. Let me show you one of the radiation over here. Let's say this is the radiation. It consists of small units of energy. It consists of small packets of energy. One packet over here is something which you call as quantum, and a lot of packets together are what we call as quanta. Perfect. My dear students, particularly if I talk about the light radiation, So I'm writing in case of light radiations. In case of light radiations, let me tell you, in case of light radiations, these small packets of energy are what we call as, these small packets, these small units are what we call as photons. These small packets are what we call as photons, right? Sound clear nahi hai. Guys, am I perfectly audible? Let me know once in the chats with yes or no. Am I perfectly audible? Say yes or no in the chats quickly. Say yes or no in the chats quickly. Yeah? All right. So majority is saying I'm perfectly audible. I don't know what's wrong with other people. Yeah? You just check your settings or something. Okay. So basically, what I was talking about, in case of light radiations also consists of the small packets of energy. And those small packets, in case of light radiations, those are what we call as photons. Perfect. And my dear students, if light radiation consists of photons, if light radiation consists of these packets of energy, if I ask you, what is going to be the speed with which these photons are going to move? I'll say the speed with which, let me know in the chats, the speed with which photons are going to move. What is that speed? Absolutely, photons are going to move with the speed of light only. Because what is a photon? Light radiation consists of photons basically, right? So if I say light radiation is moving, that means these photons are moving with the speed equal to 3 into 10 raised per 8 meter per second, right? In vacuum. Perfect. This is something which I believe every one of you would have gotten till now. Okay. So quickly, a quick recap of what this Planck's quantum theory is all about. Then I'll talk about this a bit more in detail, right? So first of all, Planck's quantum theory, it supports the particle nature of light, number one. Number two, as per Planck's quantum theory, energy is transmitted in the form of small packets or small units, and you call those small units of energy as the quanta, right? Particularly in case of light radiations, these quantas are called as photons. right? A photon, it moves with the speed of light, which is 3 into 10 raised per 8 meter per second. I believe this is clear to everyone. Now, my dear students, try to understand. Imagine this is the source of light. Imagine this is the source of light. It is emitting light radiations. I'm assuming that the light radiations which this particular source is emitting, those light radiations are incident on me. Imagine that the light radiations which this particular source is emitting, right? These light radiations are, for example, incident on me. So I can say something like this. If light radiations are incident on me, light radiations, they consist of photons. So basically, these are the photons which are incident on me. These are the photons which are incident on me. And that photon which is incident on me, whatever energy that photon will be carrying, it is transmitting entire of its energy to me, basically. Right? As simple as that. Perfect, people? Right? Let's say over here we have got a source of light. It is continuously emitting light radiation. These light radiations are falling on me. So these are basically the photons which are falling on me. Every photon has got a particular value of energy, right? And whatever photon is incident on me, that photon is basically sharing, that photon is basically transmitting all its energy to me exactly, right? Basic thing. Now, my dear students, try to understand few more things. Try to understand few more things. See, if you ask me, what is the energy possessed by one photon? Energy possessed by a photon. Energy which one photon has, right, which I'm representing by E, is equal to. Energy possessed by one photon is equal to h nu, my dear student. E is equal to h nu. This is something which I believe every one of you would be knowing. This E stands for energy possessed by one photon. It is directly proportional to the frequency of the light, right? It is directly proportional to frequency of the light. So, if energy is directly proportional to frequency of light, if I remove the proportionality sign, I'll be getting a constant h over here. And this particular h is something which you call as Planck's constant, right? You call this h as Planck's constant. Perfect. You call this particular h as Planck's constant. And what is the value of this Planck's constant exactly? If I ask you what is the value of this Planck's constant, my dear students, it's 6.6 into 10 raised by joules second. This is the value of your Planck's constant. Now, this is the energy possessed by one photon. Let's assume there are two photons. If there are two photons, energy possessed by two photons will be 2 times h nu. Energy possessed by 3 photons will be 3 times h nu. Energy possessed by n photons. Energy possessed by n number of photons will be equal to, energy possessed by n number of photons will be equal to, it will be equal to n times h nu. Perfect. Energy possessed by n photons will be simply equal to n times h nu. I believe this is clear to everyone. Perfect. The first result, that is the energy carried by one photon. This is the energy carried by n number of photons. Right, people? Now, as you all must be knowing, frequency of light. What exactly is it's going to be all about? What about this particular result? Frequency in terms of wavelength, what is it equal to? Quickly, frequency is equal to, frequency of the light is equal to c divided by lambda. This nu represents the frequency of light. This lambda represents the wavelength of the light. So, my dear students, the result which I wrote in the beginning, can I write the same result in a different format? I'll say E is equal to h nu, or I can say E is equal to hc divided by lambda. Similarly, E is equal to n times h nu. It can be written as nhc divided by lambda. It can be written as nhc divided by lambda. This is the energy possessed by one photon. This is the energy possessed by n number of photons. Right? Now, guys, be careful with certain things. Be careful with certain things. If I ask you, what is the SI unit of energy? Absolutely, you will say SI unit of energy is going to be joule. SI unit of energy is going to be joule. What are the other units of energy which we shall be using in this chapter? If I talk about the other units of energy which I shall be using over here in this chapter, that's going to be electron volt. Electron volt is one more unit of energy which I'll be using over here. And my dear students, do remember 1 electron volt, it is equal to 1.6 into 10 raised power minus 19 joules. Do remember this particular result as well. Joule is the SI unit of energy. One more unit of energy which I'll be using here, that is going to be electron volt. Do remember 1 electron volt is equal to 1.6 into 10 raised power minus 19 joules. Okay. Now, my dear students, what all things other than these you have to remember? See, my dear students, I told you energy possessed by one photon. Energy possessed by one photon is equal to either you'll be writing h nu or you'll be writing hc divided by lambda. H is the Planck's constant whose value is 6.6 into 10 raised power minus 34. C is the velocity of the light, 3 into 10 raised power 8. My dear students, let me tell you one simple thing over here. The combined value of H multiplied by C. The combined value of H multiplied by C. H multiplied by C. Its combined value you will be taking as 12400 electron volt angstroms. But do remember, when you take the combined value of H and C as 12400 electron volt angstrom, at that point of time, you have to take lambda in angstroms. At that point of time, you have to take lambda in angstroms. Similarly, my dear students, value of H multiplied by C can be written as 1240 electron volt nanometer. But when this particular value is taken, this particular value is taken only when lambda you will be taking exactly in nanometer. When you'll be taking the value of lambda in nanometers. Perfect. This is going to solve a lot of issues while you'll be doing the calculations and all, right? So now let's get to know what kind of questions can be asked from this Planck's quantum theory, right? And what all other things are there in the Planck's quantum theory, which we shall be discussing. Right, people? Yes? I hope all these things are clear till here. Look at these particular statements. According to the theory, energy is transmitted in the form of small packets or units. You call those units as quanta. In case of light energy, these packets are called as photons. Photon travels with the speed of light in vacuum. Energy possessed by a photon. Energy possessed by a photon is directly proportional to frequency of the light. Or when you remove the proportionality sign, a constant h will come, right? H is something which you call as Planck's constant, whose value is this much. Energy possessed by n photons is E is equal to n times h nu, right? All these things are discussed. All these things are discussed. SI unit of energy is joule. One more unit which we shall be frequently using, that's electron volt. 1 electron volt is equal to this much, right? The value of Hc you'll be taking as 12400 electron volt angstroms or 1240 electron volt nanometer. This value you'll only take when lambda is taken in angstroms. This value you'll only take when lambda is taken in nanometers, right? Perfect. So all these things I believe is clear to you. Let's try to solve one basic question so that you can understand where exactly these results, these basic results are used, right? And slowly you will see, we'll scale up the things, right? We'll make the things a bit complicated. See guys, calculate the energy of 100 photons. So we have got in total 100 photons, right? If the wavelength of light is 2000 angstroms, right? So we have got a light radiation. That light radiation consists of 100 photons. The wavelength of that light radiation is 2000 angstroms. What do we have to see? We have to see energy carried by 100 photons. You already know energy carried by n number of photons is equal to n times h nu, but here I'll be writing n times hc divided by lambda because I'm given with the value of wavelength of the light, right? Perfect. Now, my dear students, what all things are given to us? Wavelength of light is given to us in angstroms, so 2000 angstroms it's given, right? Number of photons, how many photons do we have in total? We have got 100 photons. So I'll simply say energy carried by 100 photons. Energy carried by 100 photons has to be equal to, it has to be equal to what? N. Number of photons, that's 100. Multiplied by H multiplied by C. Since lambda I'm taking in angstroms, so H multiplied by C, you'll be taking as 12400 electron volt angstrom divided by what? Divided by lambda. What is the value of lambda? Lambda is simply 2000 angstroms. So this angstrom gets cancelled out. You'll be getting the value exactly in electron volts, right? So this is the energy carried by 100 photons over here. This is the energy carried by 100 photons over here. So this double zero cancel, this zero cancel. So it is going to be It's going to be 1240. 1240 divided by 2. The value comes out to be how much? This is 6, this is 2, this is 0. So 620. 620 electron volts is the answer. Right? This is the energy carried by 100 photons exact. Right? Now, my dear students, if they ask you to calculate the energy in joules, since you know this 620 electron volts, 1 electron volt is equal to 1.6 into 10 raised power minus 19. This is going to be the answer, particularly in joules, if they ask you. I believe it's clear to everyone, right? I believe it's clear to everyone. This is a very simple and basic question which I'm showing you. It is just the formula based one. Okay. Similarly, one more simple question I'm showing you. Have a look on this one. Have a look at this particular question. See exactly if you can solve this. A light source of wavelength. A light source of wavelength how much? Of wavelength 2000 angstroms. Right? Emits energy. You have got a light source which is emitting radiation whose wavelength is this much, and energy possessed by energy is equal to 0.5 joules. The number of photons emitted from the source is. It's again a very simple question. Correct? As per the question, you have got a light source which is emitting radiation whose wavelength is given. Right? Perfect. Energy is equal to 0.5 joules. We have to see how many photons basically are emitted from the source exactly. So how do you do it? My dear students, imagine this is the light radiation which the source is emitting. This is the source, for example, it is emitting the light radiation. This light radiation consists of what? It consists of photons. Imagine this light radiation consists of n number of photons. Imagine this light radiation consists of n number of photons. Right? My dear students, this particular light radiation, its wavelength is given to me, right? Its wavelength is given to me as 2000 angstroms. Perfect. At the same time, energy possessed by this particular radiation. This particular radiation, it's made up of n photons. So I'll say energy possessed by n photons. It is equal to how much? It is equal to 0.5 joules. We have to see exactly how many photons are there basically. How many photons are basically emitted by this particular source. How do you exactly do it? You know, energy possessed by n photons is equal to n times hc divided by lambda. Now, dear students, try to understand one simple thing. Energy is given to me as 0.5 joules. 0.5 joules is equal to n. H multiplied by c. I'll be taking the value as 12400 electron volt angstroms divided by. Lambda is given as how much? Lambda is given as 2000 angstroms. So can I say this angstrom gets cancelled? Absolutely. So this angstrom and this angstrom gets cancelled. Now, as you can see, don't commit this particular mistake. On left hand side, you have got joules. On right hand side, you have got electron volts. Now, you can only cross multiple things if the units on both the sides are same. But here it's joules, here it's electron volts. But you already know 1 electron volt is 1.6 into 10 raised power what? 1 electron volt is 1.6 into 10 raised power minus 19. Now the left hand side is also in joules. Now, my dear students, as you can see, you have got one equation which just contains one unknown, and that unknown is n. So n value you can easily calculate from here. Isn't it simple? Right? You have got one equation which just has got one variable n. So n value you can easily calculate from here. I believe these sort of basic equations you can easily do from now on. So, right? Now, my dear students, there is one more term here. That is power. That is the term power. How do you define the power of the source? How do you define the power of the source which is emitting radiations? Imagine we have got a source which is emitting light radiations. How do we define the power of that particular source? My dear students, it's a simple topic. How do you exactly define the power of the source? How do you exactly define the power of the source? Just a second. Okay. How do you exactly define the power of the source? Power, it is defined as energy emitted by the source divided by time taken. Power is equal to energy emitted by the source divided by time taken. Right? Energy emitted by the source divided by time taken. Now, my dear students, try to understand. I told you power of the source is equal to energy emitted by the source divided by time taken. Now, imagine the source is emitting the radiation, which consists of n number of photons, So energy possessed by the radiation will be equal to energy of n photons, which will be equal to n times h nu divided by t. Or you can write it like this, nhc divided by t, and this is lambda over here. Perfect. Now, my dear students, if I talk about power, whenever you have to calculate power exactly, power is going to be n divided by t, then it's going to be hc divided by lambda. This is the result by means of which you can easily calculate the power of the source. By means of which you'll be calculating the power of the source. Now, what is this n divided by t? What is n over here? N represents number of photons, t represents time. N by t. Combinedly, what do I call this n by t as? N by t represents the number of photons emitted per unit time. The number of photons emitted per unit time. Or this particular n by t, you'll be calling it as the rate of emission of photons. This n by t is something which you call as the rate of emission of photons. Sometimes a particular question is asked in which they'll ask you to calculate the rate of emission of photons. The rate of emission of photons. That means in that particular question, you have to calculate the value of n divided by t, right? And I believe all of you already know the SI unit of power. That's what? Right? That's what? Perfect. So, my dear students, quick recap of this particular slide. Power of the source is defined as energy emitted by the source divided by time taken, right? Energy is being emitted in the form of radiation, and energy possessed by that particular radiation, which consists of n photons, is equal to n times h nu divided by time. N times h, nu can be written as c divided by lambda. So I got one particular result to calculate the power of the source, which is n by t hc by lambda. This n by t combinedly is what we call as rate of emission of photons, right? Or you can say number of photons emitted in a unit time, right? Perfect. Now let's exactly get to know what kind of question can be asked from this. What kind of question can be asked from this power, right? It's a simple topic, right? Energy transmitted, energy emitted divided by time taken. That's it. N by t is something which you call as rate of emission of photon. My dear students, look at this particular question. See what this question exactly is all about. How many photons are emitted per second? How many photons are emitted per second? Number of photons emitted per second. Number of photons emitted per second. N by t. How many photons are emitted per second? By a 5 milliwatt laser operating at 620 nanometers. So we have got a laser which is emitting a power of 5 milliwatts, right? Which can be written as 5 multiplied by 10 raised power minus 3 watts, right? And this particular laser, it is operating at the wavelength of 620 nanometers. What do we have to calculate? You have got a laser. Which is delivering power of this much, right? The laser is operating at the wavelength of this much. And what are we supposed to calculate? We are supposed to calculate the number of photons emitted per second. So basically, we are supposed to calculate the rate of emission of photons. Can't you solve it? Isn't it a simple question now? I believe it's simple. Few minutes back only, I give you one result. Power is equal to n divided by t multiplied by hc divided by lambda. Power is equal to n divided by t multiplied by hc divided by lambda. So you have to calculate the value of n by t. So can I say n divided by t will be equal to p multiplied by lambda divided by h multiplied by c, right? This particular value. This is rate of emission of photons. This is something which I'm supposed to calculate. Now, how do I calculate it? My dear students, power is given to me. I'm taking power as per SI system. 5 into 10 raised power minus 3. Take lambda value. If power you are taking as per SI system, so lambda has to be taken in SI system as well. Lambda is 620 nanometers. So it can be written as 620 into 10 raised power minus 9 meters, right? Divided by h. H as per SI system is 6.6 into 10 raised power minus 34 joules second. Velocity C, velocity of light, which is 3 into 10 raised power 8 meter per second. So all the parameters I have taken as per SI system. It is now the matter of calculation you will be getting the number of photons emitted per second, which is something which you will be calling as the rate of emission of photons. Rate of emission of photons. So in this particular question, rate of emission of photons were asked, and you exactly calculated the rate of emission of photons, right? I believe calculation part you can do on your own. Is this particular question clear to you? Let me know once in the chats, quickly, people. Everyone, quickly. Quickly, my dear students, everyone in the chats. Everyone in the chats. Is this particular question clear? I took power as per SI system. That's why lambda I had to take as per SI system. H as per SI system. C as per SI system. Right? So at the end, you'll be getting the number of photons emitted per second, which is something which you call as rate of emission of photons. Now, my dear students, one more application of this Planck's quantum theory. What is that? One more application of this Planck's quantum theory. What is that? That is photo dissociation. That is photo dissociation. How do you exactly define photo dissociation? How do you define it? So first of all, let me tell you this photo dissociation, it is defined as breaking of chemical bond using light energy. This is something important, right? A particular type of question will be framed on photo dissociation. Let's try to understand the concept first. Then I'll make you understand what it exactly means. Okay? Have a look, people. Have a look. Let's say I've got a bond between A and B. Let's say there's a chemical bond between A and B. Okay? If I first of all ask you what is a bond? What is a bond? Bond is just the force of attraction which is holding these atoms together. A chemical bond, it is just the force of attraction which is holding these atoms together. Perfect. My dear students, if I ask you, what if I break this particular bond? What if I break this particular bond? How do I break this particular bond? Since a bond is a force of attraction between these atoms. It's a force of attraction between these atoms. Now, my dear students, I have to break this force of attraction. In order to break the force of attraction, what do I need to do? I need to supply some energy. I need to supply some energy towards this bond. Then only this force of attraction will be broken down. The energy which I'm supplying, imagine that I'm supplying this energy in the form of light radiations. Imagine that I'm supplying this energy in the form of light radiation. In the form of light radiation. So, what is going to happen? A bond will get broken down. A bond will get broken down. Breaking of a chemical bond with the help of light energy. Breaking of a chemical bond with the help of light energy is something which you call as photo dissociation. Whenever you break a bond, whenever you break a force of attraction between the atoms with the help of light radiation, you call this particular phenomenon as the photo dissociation. Now, people, what all things we have to understand from here? What all things we have to understand from here? See. My dear students, imagine a bond is between A and B, right? There's a bond between A and B. For example, I'm telling you the bond energy of this particular bond, it is X kilojoules per mole. It is X kilojoules per mole. I'm telling you the bond energy over here is equal to X kilojoules per mole. What does it mean? What does it mean? It means that in order to break 1 mole of bonds, in order to break 1 mole of bonds of this particular type, how much energy am I supplying? X kilojoules of energy I'm supplying, right? So from this particular data, from this particular thing, what I got to know? I got to know that in order to break 1 mole of bonds, in order to break 1 mole of bonds of the type AB, how much energy is required? I'll say X kilojoules of energy is required. This much energy is required. Now, my dear students, imagine that this much amount of energy, which is required to break 1 mole of bonds, Imagine this much amount of energy I'm supplying in the form of light. Imagine this much amount of energy I'm supplying in the form of light, in the form of H nu. So can I say, if I supply this much of amount in the form of light radiation, can I say the bond will get broken down? Absolutely. The bond will get broken down. Now, my dear students, try to understand one simple thing which I'm going to tell you now. See, try to understand. Try to understand. Let me erase this part here. See, I told you in order to break 1 mole of bonds, this much energy is required. Now tell me one thing. 1 mole of bonds exactly contains how many bonds? It contains Na bonds, Avogadro's number of bonds. So can I say in order to break Na bonds, X kilojoules of energy is required? So what if one bond is to be broken down? What if one bond is to be broken down? Can I say in order to break Na bonds, this much energy is required? So in order to break one bond, how much energy is required? X divided by Na kilojoules. So this much amount of energy is required to break one particular bond. And my dear students, imagine that this much amount of energy I'm supplying in the form of what? In the form of light radiation. Whose energy is h nu. So this much energy I'm supplying in the form of h nu. Perfect. Or instead of h nu, you can write hc divided by lambda. So my dear students, I'm getting an equation over here. An equation is like this. X, that is the bond energy of the bond, divided by Na. Now this is in kilojoules, right? So let's make it in joules. So 10 raised power 3 is equal to Hc divided by lambda. From this particular equation, anything can be asked, right? Or if you write the same equation in the generalized form, this X was your bond energy. So bond energy divided by Avogadro's number multiplied by 10 raised power 3. The left hand side is in joules and right hand side I'm assuming also in joules. Perfect. Right hand side I'm assuming also in joules. So from this particular equation, a particular type of question can be asked. I hope you got to know how I made this particular equation. I hope you got to know it. Let me know once in the chats if it is clear. Let me know once in the chats if it's clear, people. Let me know once in the chats quickly. Yeah? Is the concept clear? Then only I can move ahead. Right? Perfect. Look at this particular question. From this question, you can easily solve now. If you got the concept, this question you can easily solve. The question is calculate the wavelength of a photon. Calculate wavelength of a photon required to break Cl single bond Cl. Required to break Cl single bond Cl. If the bond energy of Cl single bond Cl is 1.2 kilojoules per mole. Can't you solve it now? Isn't it simple? My dear students, you have got a bond between two chlorine atoms. This is the bond. Well, bond energy value is given to us. How much? Bond energy value is given to us as 1.2 kilojoules per mole. Right? Now, my dear students, there is a photon which is incident on it. Right? Perfect. What do we have to calculate? We have to calculate wavelength of this light, wavelength of this photon. We have to calculate wavelength of this photon, which is enough to break this particular bond. How do you do it now? Say, the same procedure. I'll say, in order to break Na bonds, between two chlorine atoms, how much energy is required? 1.2 into 10 raised power 3 joules of energy is required. That means in order to break one bond between two chlorine atoms, how much energy is required? I'll say 1.2 into 10 raised power 3 divided by Na. So these many joules of energy is required to break one Cl single bond Cl. Right? Imagine this much energy you are supplying in the form of photon. Energy carried by that photon is h nu, or you can say it is hc divided by lambda. Right? hc divided by lambda. Now, my dear students, you just have to equate these two. That's all. The question is done and dusted. The equation will be like this. 1.2 into 10 raised power 3 divided by Avogadro's number, approximately 6 into 10 raised power 23. The left hand side, I'm taking in joules. So right hand side, you also have to take in joules only, right? Because I've multiplied with 10 raised power 3 over here. So H value is 6.6 into 10 raised power minus 34, right? Joules second. C, velocity with which the photon moves, which is 3 into 10 raised power 8 meter per second divided by lambda. Look at this particular equation. Can I say I got one equation which just contains one variable, that's lambda? So you can calculate lambda easily from here, right? And my dear students, the point is this lambda. What will be the units of lambda while after calculation is done? Units of lambda after this calculation is done. Since this term you have taken in joules, SI system, SI system, SI system, so lambda value will come in meters as per SI system only, right? Is that clear, people? So I believe these sort of questions you can easily solve, right? Okay, look at this particular question. One more similar type of question, and I believe you can solve it. I believe you can solve this question as well. Look at the question, people. Calculate the number of photons. Calculate the number of photons of light. Wavelength is given. Required to dissociate 1 mole of Cl2Cl2 into chlorine atoms. If the bond energy of Cl bond is 1.2 kilojoules per mole. Calculate the number of photons required to dissociate 1 mole of Cl2. So right now you do not have to dissociate one bond. You have to dissociate 1 mole of bonds. Right? You have to dissociate 1 mole of bonds. See guys, as per the question, bond energy of Cl2 is 1.2 kilojoules per mole. Try to understand what I'm going to say. Now, as per this particular data, I can say in order to break 1 mole of bonds between two chlorine atoms, in order to break 1 mole of bonds, how much energy has to be supplied? I'll say 1.2 kilojoules. Write it in joules. So 1.2 into 10 raised power 3 joules. So this much amount of energy is required to break 1 mole of bonds. And as per the question, I have to break 1 mole of bonds only. I do not have to break one bond. I have to break 1 mole of bonds, right? Assume that in order to break 1 mole of bonds, n photons are required. Assume that in order to break 1 mole of bonds, n photons are required. Now, what is the energy carried by those n photons? That's going to be NHC divided by lambda. That's going to be NHC divided by lambda. I just have to equate it. The question is done and dusted. Have a look. It's going to be 1.2 into 10 raised power 3. Left hand side is in joules. So right hand side also has to be in joules. Perfect. N represents number of photons, which I have to calculate. H value, that is 6.6 into 10 raised power minus 34 as per SI system. P value is 3 multiplied by 10 raised power 8 meter per second as per SI system. Lambda value is equal to 2000 angstroms. But you know 1 angstrom is 10 raised power minus 10 meters. Why am I using meters? Because I have taken every parameter as per SI system, right? That's how your right hand side also comes in joules only. If I take all the parameters as per SI system, right? Now again, one equation, one unknown, right? What is the unknown value here? Unknown is N. N you can easily calculate. So N gives you the number of photons. N gives you the number of photons which are required to break 1 mole of bonds over here, right? N represents number of photons which have got wavelength of 2000 angstroms, which are required to break 1 mole of bonds. Let me know once in the chats if it is super clear to everyone. Quickly, guys. Let me know once the chats quickly if it is super clear to everyone. Yeah? I mean, will you be able to solve these sort of questions? I have no idea what exactly the answer. It is just the calculation, guys. Do the calculation part. Your job. I'm not going to do that. What are you going to do then? I'll teach also. I'll do the calculation also. I'll write on the screen also. Right? You're just watching and listening to the lecture. Yeah? Perfect. Chalo. Let's get going and let's see one more important topic. What is that? That is photoelectric effect. Photoelectric effect. My dear students, what photoelectric effect is all about? I believe you would have studied this in physics as well, right? So let's get into the details of the photoelectric effect. Let's see what all things are here. See, there are few terms basically which we need to know related to photoelectric effect. One is photoelectron, one is photoelectric current, One is maximum kinetic energy of the photoelectron. One is stopping potential. One is intensity, frequency, variation of kinetic energy with something, something. It's a detailed topic, right? It's a detailed topic. So let's get to know from the basics itself what this photoelectric effect is all about. For example, people, imagine that I'm taking a tube over here. Imagine that this is a tube over here. Okay. Imagine that it's a discharge tube over here, right? There is vacuum. There is nothing inside this glass tube. There is nothing inside this glass tube. Now over here, I'm going to keep a plate, a metal plate. This is a metal plate over here. This is something which I call as photosensitive metal plate. So this plate is made up of a photosensitive metal. Now what is a photosensitive metal first of all? What is the photosensitive metal? How do we define it? What is the property of the photosensitive metal? Imagine that this plate, it is the photosensitive metal plate. Now my dear students, if some light radiations are incident on this plate, what will happen? If light radiations are incident on this plate, from the surface of the plate, electrons will be emitted. Electrons will be knocked out. Electrons will be knocked out, right? So that particular metal, from the surface of which electrons are knocked out when light radiations are incident on it, you call that plate as the photosensitive plate. So what is a photosensitive plate? It is the plate from which electrons are knocked out when light radiations fall on it. That plate is something which you call as photosensitive plate, right? Now, my dear students, over here, I've got one more plate. Okay, I've got one more plate. Now, what I'll be exactly doing, I'll be connecting these plates with a battery, for example. I'll be connecting these plates with a battery, right? This is negative, this is positive, this is negative, this is positive. Perfect. Now, first of all, this is the negative terminal of the battery. This is the positive terminal of the battery. Right? So that negative terminal which is attached to this particular plate, right? So this particular plate will be carrying negative and this particular plate will be carrying positive. Okay. Now, my dear students, what is going to happen? Imagine some light radiations are incident on this metal plate, right? When light radiations are incident on this metal plate, what will happen? From the surface of the metal plate, electrons are going to be emitted. Electrons are knocked out basically. Electrons are knocked out from the surface of the metal. This phenomenon in which the electrons are knocked out from the surface of the metal when light radiation falls on it. This particular phenomenon is what you call as photoelectric effect. This particular phenomenon is what you call as photoelectric effect, right? And my dear students, one more thing. This particular plate, what do you call this as? You call this as emission plate. You call this plate as the emission plate. And this particular plate, you call this as collector plate. Why do we call this as collector plate? It's simple. The electrons which are coming out from the surface of the metal, now these electrons will be dragged by this particular plate because this particular plate carries a positive charge, is going to attract those electrons towards itself. So these electrons will start moving in a particular direction. The electrons which are coming out from the surface of this particular metal, those electrons are now moving towards the collector plate, my dear student. So if I ask you one thing, is there only the movement of electrons, or I'll say the electrons are moving in a particular direction? First of all, the electrons which are coming out from the surface of the metal, these electrons are what you call as photoelectrons. These electrons are what you call as photoelectrons. Now, once these photoelectrons are coming out from the surface of the metal, these photoelectrons will start moving towards the collector plate, right? Due to which these photoelectrons are moving in a particular direction, and whenever charge moves in a particular direction, it leads to the generation of current, and that current which is generated over here, that current is something which you call as photocurrent. That current is something which you call as photocurrent. And this particular process, my dear students, in which the electrons are taken out from the surface of the metal, when light radiation of some frequency falls on it. This particular phenomenon is what you call as photoelectric effect, right? So in case of photoelectric effect, what happens basically? Electrons are knocked out from the surface, and those electrons are what you call as photoelectrons, which move towards the positively charged plate, which is what you call as collector plate, right? So if the electrons are moving in a particular direction, it leads to the generation of current, and that particular current which gets generated due to this particular phenomenon, that's what you call as photoelectric current or photocurrent. Is this particular point clear to you? Is this point clear to you, people? From where the light comes? We are sending the light here. We are sending the light from outside, right? From outside source. There is some light source which is present over here, which is sending light towards this particular plate, right? Nothing else. Read all these statements once. Read all these particular statements once. My dear students, this photoelectric effect, it supports the particle nature of light. Point number one. It supports the particle nature of light. Number one. Number two. When light is incident on a certain metal, electrons are emitted. These electrons are what we call as photoelectrons. The current which flows due to the motion of these photoelectrons is called as photoelectric current, or you call this as photocurrent, and this phenomenon over here is what you call as photoelectric effect, right? Now let's go a bit more into the details of it. Try to understand, my dear students, what exactly I'm going to say. Imagine this is a metal surface of some photosensitive metal. Imagine this is the surface of some photosensitive metal, right? Let's say that photosensitive metal is M. Perfect. My dear students, in this metallic plate, what do we see? In this metallic plate, you will see a lot of M positive ions, which are what you call as kernels basically, right? You will see a lot of M positive ions, and in between you see millions of electrons, right? In between them you see millions of these electrons. This is the surface of the metal plate which I'm showing. So on the metal plate, what do you see? Inside the metal plate, what do you see? You see these metal ions and the large number of electrons over here. Okay. Now, for example, if I focus on one particular electron, this is the metal surface which I'm focusing on. And I'm focusing, for example, on this particular electron. Since electron carries the negative charge, so this M positive will be attracting the electron towards itself. Even this particular M positive will be attracting this electron towards itself. So tell me one thing, whether this particular electron, whether it is present in free state or bound state. Whether this particular electron, it is present in free state or bounded state. This electron is bounded basically. On the surface of the metal, this particular electron, it's bounded, right? Yes. Now tell me one thing. Since this electron is being attracted by all these M positive ions. Perfect. Now, my dear students, tell me one thing. Since this M positive is attracting this, even this M positive is attracting this. If I want this electron to be taken out, what should I do? I have to break this force of attraction between the electron and M positives. How do I break the force of attraction? I have to send some radiation. I have to send some energy. I have to make sure some energy falls on the surface so that this force of attraction breaks. And this energy which I'm sending this energy in the form of light. Perfect. So my dear students, try to understand one thing. The light radiation which you are sending, it is breaking the force of attraction between the electron and the metal ions. Then only the electron is coming out. Let me tell you, the minimum energy which is to be needed, to take the electron out from the surface of the metal, the minimum energy which is needed to take the electron out from the surface of the metal, that minimum energy needed is something which you call as work function or threshold energy. So there's a term called as work function. There's a term called as work function, which is denoted by phi naught. So what is work function? How do you explain this work function to me? The minimum amount of energy which is required to take the electron out from the surface of the photosensitive metal, right? And that minimum amount of energy which is required, which I'm supplying in the form of photon, right? That minimum energy required is something which you call as work function, right? If I ask you, work function, what should be its value? What is work function? It is the minimum amount of energy which is required to knock out the electron from the surface. And that minimum amount of energy you are supplying in the form of photon, right? Can I say it will be equal to h nu naught? It will be equal to h nu naught, right? It will be equal to h nu naught, or nu is equal to c by lambda, or you can write it as h c divided by lambda naught. Oh, there are a lot of terms, a lot of new terms are coming here. What a lot of new terms are here? Number one, this is your work function, or you call it as a threshold energy. This nu naught, it is something which you call as threshold frequency. This is called as threshold frequency. This lambda naught is something which you call as threshold wavelength. This is called as threshold wavelength, right? Now, my dear students, if I ask you, try to define this threshold frequency. Try to define this threshold frequency. Can I say threshold frequency? It is basically the minimum frequency carried by the photon, the minimum frequency which the photon has, such that that photon is taking the electron out, right? That minimum frequency required to take the electron out, that is something which you call as threshold frequency, right? That's something which you call as threshold frequency. The minimum frequency which is required to take the electron out, that's called as threshold frequency. My dear students, if this is minimum, means this has to be maximum. So what is lambda naught? Should I define lambda naught as minimum wavelength or maximum wavelength? If this is minimum, that means this automatically becomes maximum. So what is lambda naught? It is the maximum wavelength of the photon. It is the maximum wavelength of the photon, right? Which is just taking the electron out. So I got three terminologies over here. Threshold energy, which is what you call as work function. How do you define it? The minimum energy which is required to take the electron out from the surface of the metal. Threshold energy or work function. Threshold frequency is the minimum frequency which is required, right? Minimum frequency which is required to take the electron out. Lambda naught is the maximum wavelength which is required to take the electron out from the surface of the metal. So three new terms here. Yeah? Right, people? Is it clear? So let's try to have a look on these terminologies which I have discussed with you. I did not discuss them in detail yet. We have to discuss them in detail. I'm just giving you the idea of the things. Okay? So work function, which is what you call as threshold energy. How do you define it exactly? How do you define it? It is basically the minimum energy which is required. To eject, to take the electron out from the surface of the matter. Right? And you represent this with the help of phi naught, which is either equal to h nu naught, or you can call it as hc divided by lambda. Right? Now, every metal has got a particular value of its threshold. Every metal, whatever metal surface you take, every metal surface has got a particular value of its threshold energy, right? Some metals will have more threshold energy because there will be more force of attraction between the electron and the ions. Some metals will have less threshold energy because there will be less force of attraction between the electrons and the ions. So every metal has got a particular value of the threshold energy, particular value of work function. So work function, it is basically a characteristic of what? It is the characteristic of metal basically. Work function, on what parameters it depends on? It depends on the amount of force of attraction between the electron and the metal ions. Perfect. More the attraction, more the energy needed, more the work function. Yeah? I believe it's clear. This particular thing. What is this particular thing? Threshold frequency. It is something we defined a few minutes back only. Threshold frequency, it is the minimum frequency. It is the minimum frequency which the photon has just to take the electron out. Right? Right, guys? The minimum frequency required to eject an electron out of the surface of the metal is something which you call as threshold frequency. Right? And this threshold frequency, it is represented by mu naught, which is equal to C divided by lambda naught basically. Which is equal to C divided by lambda naught. I believe this particular point is also clear. I believe this particular point is also clear. Now, similarly, guys, what about threshold wavelength? Threshold energy was minimum energy. Threshold frequency was minimum frequency. Threshold wavelength will be maximum wavelength. The maximum wavelength required to eject an electron from the surface of the metal is something which you call as threshold wavelength, right? If this is threshold frequency, it is the minimum frequency. If this is minimum frequency, this has to be maximum wavelength, right? So lambda naught here is the threshold wavelength over here. Perfect. So I believe all these things are till here clear to you. Now, my dear students, let's try to understand and analyze certain mathematics behind it. See, guys, try to understand. For example, this is the surface of the metal. Imagine that this is the surface of the metal, right? This is the surface of the metal M. Now, on the surface, what do you observe? You'll be observing M positives and millions of electrons. M positives and millions of electrons. M positives and millions of electrons you'll observe here, right? Millions of electrons you'll observe here. So, my dear students, particularly if I talk about this electron, right? This electron is attracted by this M positive as well as this M positive. Just to make you understand, this particular electron, it is attracted by this M positive as well as this M positive. Now, I want to take this electron out. If I want to take this electron out, what do I have to do? I have to break this force of attraction. Absolutely, I have to break this force of attraction, right? Let's assume that minimum. Let's assume that minimum 50 joules of energy. Let's assume that minimum 50 joules of energy is required to take this electron out. And that minimum energy which is required to take the electron out from the surface of the metal, that's what you call as work function. So this 50 joules over here, let's say this is the work function of the metal. This is the work function of the metal. Now tell me one thing. Imagine that this is the photon which is going to be incident on this particular surface. Let's say this photon carries the energy of 80 joules. This photon carries the energy of 80 joules. So this 80 joules I'll be calling as incident energy. I'll be calling this as incident energy. So how much is the incident energy carried by the photon? 80 joules. Minimum how much is required to take the electron out? 50 joules. So how much energy I'm sending? I'm sending 80 joules to the surface. Out of 80 joules, 50 joules is required. 50 joules is required to set free this electron, to take the electron out. What about the remaining energy? Remaining energy is 30 joules. This 30 joules is imparted by the electron in the form of its kinetic energy, right? This is basically going to be this 30 joules. It will be imparted to the electron in the form of its what? In the form of its kinetic energy. So basically, out of 80 joules, 50 joules are required to take the electron out. Now the electron which got out, it will be moving on the cost of this 30 joules, on the cost of this particular 30 joules, right? So can I say something like this? Can I say something like this? What was this 80 joules? This was incident energy. What was this 50 joules? It was work function. What is this 30 joules? This 30 joules is imparted to electron in the form of its kinetic energy. So this is your kinetic energy max of the electron. This is the equation, which is something you call as photoelectric equation. This equation is something which you call as photoelectric equation. So this is your photoelectric equation basically. This is your photoelectric equation. Incident energy is equal to work function plus what? Plus maximum kinetic energy possessed by the electron after the emission. Okay. Now, my dear students, you can write different formats of it. Incident energy, I'm giving in the form of photon, so this h nu. Work function is h nu naught. You can write it as such, Ke max, maximum kinetic energy which is possessed by the emitted electron. right? Instead of h nu, you can write hc divided by lambda is equal. Instead of this, you can write hc divided by lambda naught plus kinetic energy max, right? Maximum kinetic energy possessed by the photoelectron. Perfect, right? Yeah. And my dear students, at the same time, this hc divided by lambda, it can be written like this as well. hc divided by lambda naught. Maximum kinetic energy possessed by the photoelectron will be half of mass of electron and V max of an electron, a square. It can be written like this as well. So these are different formats of this particular equation, right? These are different formats of this particular equation. So in nutshell, if I need to summarize it, how would I summarize it? I don't understand. The energy which is incident on the metal surface, it is used in two parts. The energy which is incident on the metal surface, it's divided in two parts. Number one, some part of the incident energy is used to eject the electrons out of the surface of the metal in the form of work function, right? And the remaining incident energy is used to provide the kinetic energy of the ejected electrons, right? Yes? Right, people? So, due to this particular scenario, what did we get? We got one equation. Equation was your incident energy is equal to work function plus maximum kinetic energy possessed by the emitted electron, right? These are the different formats of this particular equation, right? All these formats I've already shown you. Now, my dear students, let's have a look on a few more things. Let's have a look on a few more things. Imagine that this is the photon which is incident on the surface. This photon carries the energy h nu. This photon carries the energy h nu. This photon is incident on the surface. Perfect, right? Imagine work function. Work function here is something, let's say work function here is 50 joules. Let's say work function here is 50 joules. Tell me one simple thing. What is this 50 joules? It is the minimum energy which is required to take the electron out. It is the minimum energy required to take the electron out. Imagine that h nu value is equal to, for example, 80 joules. Imagine that energy possessed by electron. Sorry, energy possessed by the photon, which is h nu. Imagine that it is equal to 80 joules. Out of 80 joules, how much is used to take the electron out? 50 joules. Remaining is 30 joules. Those 30 joules are imparted to the electron. That those 30 joules electron is going to get in the form of its maximum kinetic energy after the emission. You know it. Now tell me one thing. If I increase the frequency of the incident light, that means on increasing the frequency of the incident light, energy of the photon is increasing. Energy of the incident light is increasing. If energy of incident light is increasing, imagine we are increasing the energy to 100 joules. Now the incident energy is 100 joules, right? On increasing the energy, will anything happen to work function? Work function is still the same, 50 joules. Work function is still the same. I'm increasing the frequency of the incident light. I'm increasing the energy of the incident light. By increasing the energy of the incident light, nothing will happen to work function, right? It is a characteristic of the metal. Where you will see the chains? Initially, the kinetic energy was the kinetic energy of the emitted electron. That was 30 joules. But if this is made 100 joules, will the kinetic energy of photoelectron be 30 joules now or 50 joules? That will be 50 joules. 100 minus this value, that will be 50 joules. So, in short, can I say something like this? On increasing the frequency of the incident light, kinetic energy of the photoelectron, does it increase or decrease? It increases. Kinetic energy of the photoelectron, it increases. Okay? Can I say something like that? Absolutely. Now let's try to make a graph between kinetic energy and frequency of the incident light. This is kinetic energy of the photoelectron. This is frequency of the incident light. Now what will be the nature of the graph? Try to understand. See guys, from this particular equation, you can say kinetic energy maximum is equal to h nu minus h nu naught. Agreed? We have to make a curve between this particular term and a nu over here. Now, kinetic energy you are plotting along y-axis. This frequency of the incident light you are plotting along x-axis. This h is going to be your m. This particular whole term is going to be your c. The sign here is minus. This is equal to y is equal to mx minus c. Y is equal to mx minus c. It's going to be a straight line. Y is equal to mx minus c. It's going to be a straight line. But this straight line won't be passing through the origin. It will start down the origin because of this negative intercept. Right? Because the sign of intercept is minus. So it is going to be a straight line, but this straight line won't be passing through the origin. It will start down the origin. This was the origin here. Right? The distance from the origin to the point from where the curve starts. The distance from the origin to the point from where the curve starts. That means this particular distance I'm talking about. What do we call this distance as? This is called as intercept. Intercept is c, and c value over here is h nu naught. So this term is h nu naught over here. Right? If I ask you the slope of this curve, slope means m, and m value here is h. So slope of this particular curve is simply h. Right? Agreed? Agreed, guys? So what is happening basically? On increasing the frequency of the incident light, the kinetic energy of the photoelectron, that is increasing. The speed with which the photoelectron moves, that increases. I believe it's clear to everyone. Now, my dear students, there are few things. There are few things which you need to know. Let me tell you, one photon is enough to knock out one electron. One photon is enough to knock out one electron. Two photons cannot eject one electron. Two photons cannot knock out one electron. One photon will only knock out one electron. That is why this photoelectric effect is also called as one photon. This is also called as one photon, one electron emission. This is also called as one photon, one electron emission. What it means, why this is important, why this is important. Try to understand. You might think in this way. You might think in this way. Let's say this is the electron. In order to take the electron out, you have to give around 50 joules, right? Now you must be thinking, let's make sure that two photons are incident on this, one carrying 25 joules, one more carrying 25 joules. You might be thinking 25 plus 25 is 50, and that 50 is enough to take this electron out. But my dear students, this is not the case here. One photon will take out one electron. Two photons cannot take two electrons out. One photon, one electron. One electron is going to take one photon. Sorry, one photon is going to take one electron out. Right? Two photons can never take one particular electron out. Okay? Point number one. Point number one. Point number one. Point number two. My dear students, when a photon of a particular frequency strikes the surface of the metal, when a photon of a particular frequency strikes the surface of the metal, the process is all instantaneous. As soon as the photon strikes the metal surface, at that time itself, electron is emitted. There is no time lag. There is no time lag. There is no time lag between the striking of photon and the emission of photoelectron. There will be no time lag. It's not like that the electron is going to strike the metal surface, then it will take some 5 seconds, then the electron will come out, right? It's not like that photon will strike the surface, then it will take 5-10 minutes, and then slowly it will go out. No, it's not that. There's no time lag in between. There's no time lag in between. This is one more important point. Why these points are important? You will get their significance in some time. In some time, you will get their significance. Okay? Now, we will try to understand few more things. Try to understand few more things. If you ask me exactly, what are the conditions which must be satisfied for the photoelectric effect to happen? What are the conditions which should be satisfied? My dear students, the condition is very simple. The condition is very simple. Since you know one electron is enough to take one photon is enough to take electron out, right? Do remember, incident energy has to be greater or equal to the work function. Incident energy has to be greater or equal to the work function. This is the condition which should be satisfied. Then only the electron can be knocked out from the surface of the metal, right? This is the condition, simple condition. The incident energy should be greater or equal to the work function. Number one. Number two, you can make one more condition. Incident energy is basically h nu. So h nu should be greater or equal to h nu naught. What does that mean? That means nu should be greater or equal to nu naught. What is this nu? This is the frequency of the incident light. Frequency of the incident light should be greater or equal to threshold frequency. This is one more condition. Either you talk in terms of energy or you can talk in terms of this particular frequency as well. Frequency of the incident light should be greater or equal to the threshold frequency. Then only the electron will be knocked out. Now one more thing. Frequency is c by lambda. So c by lambda should be greater or equal to c by lambda naught. Right? This lambda naught is c by lambda naught. So c gets cancelled. If you take the reciprocal, you can say lambda should be less or equal to lambda naught. This is one more condition. This is one more condition. This is the wavelength of the incident light. This is the threshold wavelength. Wavelength of the incident light should be less or equal to threshold wavelength. Then only photoelectric effect will happen. Then only electron will be knocked out. Then only electron will be knocked out. Right? Is this clear, people? Clear, guys? Is this clear? Let me know once in the chats quickly. Perfect. So if incident energy is less than work function, if incident energy is less than work function, or incident frequency is less than threshold frequency, no photoelectrons will be emitted. No photoelectric will be observed. But if incident energy is greater than work function, or if incident frequency is greater than threshold frequency, photoelectric effect will be observed. So these are the conditions which you have to remember, either in this format or in this format or in this particular format, right? These are the three formats which we have. So my dear students, if this is clear, can you answer me this question? The work functions of some metals are listed below. The number of metals which will show photoelectric effect when light of 300 nanometers falls on the metal. So the light which is going to fall on the metal, it has got the wavelength of 300 nanometers. So that means, what is the energy of the incident light? It is Hc divided by lambda. Hc I'll be taking as 1240 electron volt nanometer divided by lambda is going to be 300 nanometer, right? So nanometer cancel. So 0000 is going to be 4.1 electron volt. This is the energy of the incident light. This is the energy of incident photon. This is the energy of incident photon. Now you have got lithium. You have got lithium, right? Now, my dear students, imagine if the photon carrying this much of energy, if that is incident on lithium, will photoelectric effect happen? Will it happen? Absolutely it will, because threshold here is less. Minimum this is required, but you are supplying more, right? So here, photoelectric effect will be observed. Here again it's less, it will be observed. Here again it's less, it's observed. Here again it's less, observed. Not here, not here, not here. This was the question asked in your JEE Mains 2 years back. In how many metals photoelectric effect will be observed? So there are 4 metals wherein we can see the photoelectric effect. Yes? Perfect, guys? I believe it's clear. I believe it's clear. Look at one more question. See what the question is. If the work function of a metal is something, its threshold wavelength and maximum kinetic energy. Threshold wavelength and maximum kinetic energy emitted when the radiation of 300 nanometers strikes the metal. So basically what is happening? Let me show it to you. Let me show you the exact scenario. This is the metal surface. Work function of this surface of this metal is 3.1 electron volts, right? Now you have got a light radiation which is incident on the surface. Perfect. Wavelength of the light which is incident on the surface, that is 300 nanometer, right? That is 300 nanometer. Now what is happening? When this light is falling on the surface, electron is emitted. Electron will be emitted with some kinetic energy. We have to first of all calculate that maximum kinetic energy which the electron has. Maximum kinetic energy which the electron has, right? And at the same time, what do we have to calculate? We have to calculate the threshold wavelength as well. The threshold wavelength as well. Lambda naught also is to be calculated. So two things we have to calculate. I believe you can do it easily. My dear students, let's have a look first of all on threshold wavelength. You know your lambda naught work function. It's equal to h nu naught, right? Or you can say it's equal to h c divided by lambda naught. So can't you calculate lambda naught from here? This hc divided by phi naught, right? hc divided by phi naught. You can calculate lambda naught. My dear students, hc value you can take as 12400 electron volt in nanometer, because everywhere it's nanometer. Phi naught is 3.1 electron volts. Electron volt cancelled. Solve it. Get the value of lambda naught, which is your threshold wavelength. So you calculate your threshold wavelength from here. Now threshold wavelength is calculated. Now use the photoelectric equation. Photoelectric equation says that incident energy is equal to phi naught plus maximum kinetic energy possessed by the photoelectron. What do we have to calculate? We have to calculate the maximum kinetic energy, right, of the photoelectron emitted. EI is just going to be hc divided by lambda. This is going to be hc divided by lambda naught plus kinetic energy maximum. Plus kinetic energy maximum. So from here, you can calculate maximum kinetic energy. What is it going to be? hc you will take common. It's going to be 1 divided by lambda minus 1 divided by lambda naught. Or you can say lambda naught minus lambda. Or you can keep it as such. The choice is all yours. Right? Now people, try to understand. Lambda value is given to us. 300 nanometers. Right? Lambda naught we have calculated from here. Lambda naught we have calculated from here in nanometers. hc value will be 1240 electron volt nanometer. When you put all the terms in this particular expression, you'll be getting the answer in terms of electron volts here. So that's going to give you the maximum kinetic energy of the emitted electron. Yes? Right, people? Is it clear to you? Let me know once in the chats quickly. Is it clear? I believe it's clear to you. I believe it's clear to you. Right? Now we're talking about few more things. There is a term called as, or just a second. There is a term called as stopping potential. There's a term called as stopping potential. What is stopping potential all about? This one more term. Stopping potential. My dear students, it is defined as the reverse potential, which is applied to stop the most energetic photoelectron from reaching the anode. What does it mean? What does it mean? Let's have a look. Let's have a look, people. Say, this was your anode and this was your cathode basically. This was your cathode. Perfect. Now light radiation is coming, taking the electron out. Perfect. The electron, it is coming towards anode. Now, my dear students, if I change the polarity of this particular plate, this plate carries positive charge. It is at positive potential. If I change the potential of this anode, changing the potential of this anode means, since it was positive, if I make it negative, can I say the electron which was supposed to come in this direction, that electron will experience the repulsions from this negatively charged plate, right? That electron will experience some repulsions from the negatively charged plate. My dear students, if I keep on increasing the negative potential of this plate, what will happen? The electron which was supposed to come, it will experience more repulsions. I'm continuously increasing the reverse potential of this plate. I'm continuously increasing the reverse potential. I'm continuously increasing the negative potential of this plate. What is going to happen? Can I say there'll be a point, there'll be a time at which the most energetic photon will stop? That will not reach this anode. That reverse voltage, that reverse potential at which the most energetic photon stops, highly energetic photon stops, that reverse voltage is something which you call a stopping potential. That's something which you call a stopping potential. So what is stopping potential? Is it the normal voltage or reverse voltage? You are giving the reverse voltage. See, this was your positively charged plate, but this was at positive potential. Now you are changing its polarity. You are changing its potential. You are making it negative potential, right? Perfect. So you are reversing its polarity, right? You are reversing its polarity. How you'll be reversing its polarity? Maybe you'll be connecting these plates with some other battery, right? Maybe you'll be connecting these plates with some other external battery, but in the reverse format, not in this particular format, in the reverse format. And that battery, its voltage you'll keep on increasing. When you keep on increasing the voltage of that external battery, which is connected to these plates in the reverse form, what will happen? There'll be a time when negative charge will come on this particular plate. On continuously increasing the voltage of that battery, this intensity of negative charge on the plate will keep on increasing. The electrons which were coming in this direction, they will keep on experiencing more and more repulsions. They'll keep on experiencing more and more repulsions. There will be a voltage, there will be a reverse voltage at which the most energetic electron will also stop. And that voltage at which the most energetic electron will stop, that voltage is something which you call as a reverse voltage. Yes? Right, people? Is it clear? Did you get the idea of reverse voltage? I mean the stopping potential which I'm talking about. Stopping potential. So what is a stopping potential basically? What is a stopping potential? Guys, if you still have doubts here, let me make it further clear to you. If you still have doubts here, let me make it further clear to you. See, this was basically your positive plate. This was basically your positive plate, right? This was your positive plate. It was connected with this particular battery. Now imagine, just try to understand in this way. Imagine I'm connecting this with one more external battery, and this is negative terminal now, this is positive. If this is negative, if I keep on increasing the voltage of this particular battery, keep on increasing the voltage of this particular battery, the intensity of negative charge on this plate will increase. The intensity of negative charge on this plate will increase, right? And these electrons, which were supposed to come in this direction, they will experience more repulsions, right? On increasing the voltage of this battery, can I say there will be one voltage at which the most energetic photoelectron will stop. And that voltage at which, that reverse voltage which we are giving, at which the most energetic photoelectron will stop, that reverse voltage is something which you call a stopping potential, right? That's something which you call a stopping potential. Okay, that's called a stopping potential. Right, guys? So what is a stopping potential? It is the reverse voltage which is applied to stop the most energetic photoelectron from reaching anode. Perfect. Now, my dear students, just try to understand. Just try to understand. What would have happened? The electron was coming out from the surface, for example. It had to reach here. It had to reach here. But due to the negative charge, this electron is experiencing repulsions. So when the electron comes out of this particular surface, it's moving. Now the electron is experiencing repulsions from this plate, right? It's experiencing repulsions from this plate. So what is happening to its kinetic energy? Kinetic energy of electron is decreasing. There'll be a point when the electron comes to the rest. When the electron comes to the rest, can I say when the electron comes to the rest, can I say entire kinetic energy of the electron has got converted into its potential energy? When the electron comes at the rest, I'll say entire kinetic energy has got converted into its potential energy. Potential energy is equal to E V naught. E is the charge on the electron, V naught is the stopping potential. Right? As per the work energy theorem, since electron was supposed to move, but it's experiencing repulsions, right? It's experiencing repulsions. So its motion is being distorted by the repulsions. That means its kinetic energy is getting converted into what? Potential energy. When it stops, entire kinetic energy would have got converted into potential energy. Potential energy of the electron is going to be charge on electron multiplied by stopping potential, right? So if maximum kinetic energy of the photoelectron is equal to E V naught, this V naught is the stopping potential. It is not the threshold frequency, right? So from the equation, this was our photoelectric equation. In this particular equation, you can replace this particular term. Instead of K max, you can write EV naught. You can write EV naught. Perfect. You can write EV naught. And my dear students, instead of incident energy, you can write H nu. Instead of phi, you can write H nu naught. And this is EV naught here. This is one more equation from which question can come. One more equation from which question can come. Now, my dear students, try to understand one thing. Just understand it. If you increase the energy of the incident photon, okay, let me keep it simple. If you increase the frequency of the incident photon, that means energy of incident photon will increase, right? And as the energy of incident photon increases, kinetic energy of the photoelectron, that increases. As the kinetic energy of photoelectron increases, what happens to that reverse voltage? Stopping potential. Stopping potential, will it increase or decrease? Stopping potential will automatically increase, right? Because now we have to provide more reverse voltage to stop that high energetic electron. Yes? Right, people? Sophie, that's already taught. You can check mole concept part 3. Go to the playlist. Right, people? I believe it's clear. I believe it's clear, right? Yeah. So on increasing the frequency of the incident light, what happens to the stopping potential? Stopping potential increases. Perfect. And this is the equation which you are going to remember. See guys, let me write the equation again. Incident energy is equal to work function plus kinetic energy maximum, right? Now instead of kinetic energy maximum, what you can write? Instead of kinetic energy maximum, you can write E V naught, where V naught is not the threshold frequency, it's the stopping potential. This is the same photoelectric equation in different format. Right? Now, if you want to make a graph between, this is stopping potential versus incident frequency. What the graph will look like? See guys, it's simple. It's very simple. Look at this particular equation. Can I say from this particular equation, EV naught is equal to H nu minus H nu naught? Absolutely. Can I say V naught is equal to H divided by E nu minus H divided by E nu naught? Absolutely. I'm plotting a graph between stopping potential and frequency of the incident light. This and this. This is plotting along y-axis. This I'm plotting along x-axis. So this automatically becomes your M. This whole term becomes your C. Sign in between is minus. So y is equal to mx minus c. Y is equal to mx minus c. Again, a straight line, but not passing through the origin. It's starting down the origin. This is the origin, for example. It will start from here. So this is the line. This is the graph. The distance from origin till the point from where the curve starts, that's something which you call as intercept. Intercept is denoted by C. C is equal to H nu naught by E. This intercept is equal to H nu naught divided by E. If I talk about the slope of this particular curve means M is equal to H by E. Slope of this particular curve is equal to M and M is equal to H by E. This curve you should also remember from now onwards. Okay. So my dear students, what all things we observed till now? On increasing the frequency of the incident light, kinetic energy of the photoelectron increases, stopping potential also increases. Right? Look at this particular question. Light of wavelength 400 nanometers is incident on metal with work function 2.3 electron volts. Calculate the stopping potential. V naught. Basic equation you know. Incident energy is equal to phi naught plus Ke max. Instead of Ke max, you can write EV naught. V naught you have to calculate. That's it. Now, incident energy is equal to Hc divided by lambda is equal to this particular term already you know. This is 2.3 electron volts, right? Plus E V naught, right guys? Now Hc, what is Hc? 124, it is in nanometers, right? So 1240 electron volt nanometer divided by lambda. How much is lambda? Lambda is 400 nanometer is equal to 2.3 electron volt plus electron V naught. Perfect guys. Perfect. Now see what all things I'll be cancelling here. So nanometer, first of all cancelled. Cancelled. This E, in short, cancelled. So what do I get? I get V naught is equal to V naught is equal to. This particular term will be how much? This will be approximately 3, right? This will be 3.1. So it's going to be 3.1 minus 2.3 volts, right? So V naught is equal to 0.8 volt. What is meant by this 0.8 volt? This is that reverse voltage. This is that reverse voltage which has to be kept. Then only the highest energetic electron will stop, that won't reach the anode. I believe it's clear. I believe it's clear. Right? Now, my dear students, there are a few more things. There are just 2 to 3 things more in photoelectric effect. Do you know what is intensity of light? How do you define the intensity of the light? How do you define the intensity of the light? Intensity is defined as energy incident per unit area per unit time. Energy incident per unit area per unit time. That defines the intensity of the radiations, of the light basically, of the source basically, right? So what is intensity? Intensity is denoted by I. It is equal to energy which is incident on what? On a unit area of the surface per unit time. In a unit time, right? Now, imagine that the source is emitting radiations, light radiations. So energy which the light radiations will have, it will be equal to simply NHC divided by lambda, NHC divided by lambda, right? NHC divided by lambda multiplied by what? Multiplied by area of cross section, right? Multiplied by what? Multiplied by time. So this is the formula, first of all, by means of which you can calculate intensity, or you can write in terms of frequency as well. It is NH. C divided by lambda is your nu, right? This is A multiplied by T. So energy incident per unit area per unit time. That defines what? That defines your intensity. So if you look at this particular expression, your I, intensity is equal to NH nu divided by A multiplied by T. Intensity of the light, intensity of the radiation, right? Intensity of the source basically. Intensity of the source. This N represents number of photons which the source sends. H is constant. Mu is the frequency of the light which the source sends, right? My dear students, try to understand. If you keep frequency constant, can I say at that point of time, intensity is directly proportional to number of photons emitted? Absolutely, intensity is directly proportional to number of photons emitted. It's evident. Intensity, if I keep the frequency constant, I'll say intensity that is directly proportional to number of photons. So, more the photons emitted by the source, more is the intensity basically. Right? More is the intensity. So, I would say more the photons sent by the source, more is the intensity basically. Agreed? More is the intensity. Right? Perfect. Intensity, it depends on number of photons emitted by the source. More the photons emitted by the source, more is the intensity of the light. In short. Yeah? Okay, one more thing. My dear students, try to understand one simple thing. If you have to measure the photocurrent, how do you get the photocurrent? I is equal to Q by T. Q is the charge which goes to the anode in the form of electrons. T is the time. This charge, you already know it's Q. Q is equal to Ne. N is the charge on electron. N is the number of electrons which goes towards the anode. T is the time taken. This is the formula by means of which you can calculate the photocurrent as well, right? Well, we have got nothing to do with this. Leave it aside. But here are some graphs. Which you have to understand. My dear students, both kinetic energy and stopping potential of photoelectrons varies with the frequency of the incident light. Something which we have discussed. If you increase the frequency of the incident light, kinetic energy of the photoelectrons increase, due to which stopping potential also increase. So both increases. These two graphs which we have discussed already. right? Let's have a look on few more things. Now, what happens to the kinetic energy of photoelectrons upon changing the intensity of the light? Imagine you're increasing the intensity of the light. My dear students, when you increase the intensity of the light, that means you are increasing, that means number of photons emitted are increasing. Number of photons emitted are increasing. Nothing is happening to the energy of photons. Nothing is happening to the energy of photons. If you increase the intensity of the light, that means you are increasing the number of photons emitted, right? But nothing is happening to the energy of light. It's same. Since you know one photon is enough to knock out one electron. Since you know one photon is enough to knock out one electron. If you increase the energy of the incident, if you increase the intensity of the light, that means more photons are incident on the metal surface. One photon is enough to take out one electron. If more photons are incident on the metal surface, can I say more electrons will emit? If more electrons emit, that means more charge will go towards anode. That means more will be the photocurrent. More will be the photocurrent. Right? More is the photocurrent. Is this clear? Is this clear, guys? Right? So, I can simply generalize one statement. If you increase the intensity of the light, photocurrent increases. Photocurrent increases. Yeah? When you increase the intensity of the light, I'll simply say photocurrent will increase. Photoelectric current will increase. Okay, tell me one thing. When you increase the intensity of light, will anything happen to the kinetic energy of the photoelectron? Nothing will happen to the kinetic energy of the photoelectron. Nothing will happen to the stopping potential. Right? Nothing will happen to the stopping potential. Okay? I believe this is clear. So on increase the intensity, the kinetic energy of the photoelectrons, it remains unchanged. It remains unchanged. Let me quickly summarize few points. Right? So my dear students, the first point. If you increase the frequency of the incident light, that means you are increasing the energy of the incident light. What will happen due to that? Due to that, kinetic energy of the photoelectron will increase. Due to that, stopping potential will also increase. My dear students, this Bohr's atomic model you study in your class 12 physics as well. So this is one of the important topics of this particular chapter from which questions are frequently asked, right? So take this particular topic very, very, very seriously. And whatever questions I'll be showing here, take all the questions very seriously. Okay? Perfect, guys. So first thing, let me show you exactly the postulates of this particular Bohr's theory. The main important points of this particular Bohr's theory. Number one, my dear students, this Bohr's atomic model, it is applicable to single electron species. Now you must be thinking, what are single electron species? As per their name is concerned, single electron species are the ones which just contain one electron. For example, if you talk about hydrogen, its atomic number is 1, right? My dear students, in one atom of hydrogen, you will find only one electron. And that species which just contains one electron, that's something which you will be calling as single electron species. So hydrogen, it is a single electron species, right? Number one. Number two, if I talk about helium, its atomic number is 2. Helium, its atomic number is 2. That means one atom of helium, it contains 2 electrons. One atom of helium, it contains 2 electrons. My dear students, if you take one electron out from here, this helium, it gets converted into He positive. Now, if I ask you how many electrons are present in He positive, you'll say only 1 electron. So, if I ask you helium or helium positive, among these two, which one is a single electron species? You'll say it is He positive, which is your single electron species, my dear student, right? And at the same time, for example, you talk about lithium. its atomic number is 3. One atom of lithium contains 3 electrons. One atom of lithium contains 3 electrons. If you take 2 electrons out, it gets converted into lithium dipositive, and this particular lithium dipositive, it just contains 1 electron. So lithium dipositive is again your single electron species, right? So single electron species are the ones which just contains 1 electron. And this particular Bohr's theory, this particular Bohr's model, it is only and only applicable to single electron species like hydrogen, like He positive, like lithium dipositive, right? Now, my dear students, as per Bohr's atomic model is concerned, atom contains equal number of protons and electrons. As per the Bohr's atomic model is concerned, what Bohr said atom basically, it contains equal number of protons and electrons. Due to which, if the atom is containing equal number of protons and equal number of electrons, that is the reason why your atom is basically electrically neutral, right? That's the reason why your atom is basically electrically neutral. So atom consists of equal number of protons and neutrons, and therefore atom is considered to be electrically neutral. This was the second point which you have to remember. Okay. Talking about the third point. This is also something which every one of you would be knowing. This is basic stuff which I'm sure majority of you guys will be already knowing. Yeah. What is this particular point? As per this particular third point, as per the Bohr's atomic model is concerned, electrons, they are revolving. Electrons are revolving around the nucleus in the circular paths. And these circular paths in which the electrons are revolving, these circular paths, they have got a fixed radius, right? And my dear students, the circular paths in which the electron revolves, which have got a fixed radius, he called them as the shells or orbits, right? He called them the shells as, or you can call them as orbits. So shell concept, orbit concept, it was given by Bohr basically. Bohr introduced the concept of orbit. He introduced the concept of shell. And what is this orbit? What is this shell? It is the circular path in which the electron continuously keeps on revolving around the nucleus. And this particular circular path, it has got the fixed, it has got the constant radius. And the circular path in which electron moves, in which electron revolves, right, which has got the fixed radius, you call these circular paths as the orbits, or you call it as shells, right? And my dear students, let's say this is the nucleus of an atom. Let's say this is the nucleus of an atom, which consists of protons, right? Inside the nucleus, what do we have? You have got protons. Now, for example, this is the first circular path which I'm showing. Let's say this is the second circular path. Similarly, there'll be a lot of circular paths here, right? Perfect. Let's assume this is one of the circular paths in which electron will be continuously revolving. Perfect. You'll be calling this particular circular path, which has got a fixed radius, you'll be calling it as K shell, right? The second one is called as L. This is called as M, and this is called as N. I'm sure this is again something which you all must be knowing already, right? So electron, it keeps on revolving around the nucleus, and the circular paths, those circular paths, they have got fixed radius, and those circular paths are what you call as shells or orbits. And my dear students, these shells, the first shell is your K shell, L, M, N, etc., etc. Okay, that's it. That's it. This was one more point. Now, talking about something interesting here. Talking about something interesting. Have a look. Just a second. See. Look at this particular point. Look at this particular point. This is important. My dear students, imagine this is the atom over here. Imagine this is the atom over here. Okay. Now, first of all, I'm assuming that the atomic number of this particular atom is Z. Z is the atomic number. Z is the atomic number of the atom of some element, right? If the atomic number is Z, what does that mean? That means this particular atom contains Z number of protons. You know, whatever is the atomic number of an element, same is the number of protons present in one atom of an element, right? That's something Again, you'll be knowing. I'm assuming that I have got an atom of some element whose atomic number is Z. That means it will contain how many protons? It will contain Z protons. As simple as that, right? Now, my dear students, let's assume that the charge present on one proton, let's assume that is E, and the sign will be positive. Let's assume that the charge present on one proton is E. If charge on one proton is E, how many protons do we have in this atom? We have got Z protons. Charge on one proton is E. Charge on two protons will be 2 times E. 3 protons, 3 times E. Z protons will be Z times E. So charge which these Z protons have, it's going to be Z times E, right? With the sign positive. Perfect. So what is the ZE? It is the charge which the Z number of protons will have. My dear students, entire positive charge in the atom, that is concentrated in the nucleus. So this positive charge which the atom contains, it will be present in the nucleus. So the nucleus of the atom will contain the charge Ze. I hope this is clear. Now, for example, this is the electron here which is revolving in this particular shell. The electron is revolving around this. The electron is revolving, right, in this circular orbit over here. Let's assume that. What is the charge present on electron? Charge on electron, magnitude wise, it is E, but the sign will be negative. The charge on electron, magnitude wise, it's going to be E, but the sign is going to be minus over here. Perfect. Now you must be knowing one simple thing. My dear students, for any object to revolve in the circular path, the object must experience centripetal force, due to which the object will keep on revolving in the circular path. I believe this is something you already know. For example, let's say I've got an object. If the object has to move in the circular path, definitely there should be one force experienced by this object, right? And that force, its direction has to be towards the center. And this force, by means of which, the force which is directed towards the center, by means of which the object moves in the circular path, what do you call this force as? You call this as centripetal force. The force which the object experiences, by means of which this object revolves in the circular path, right? This force is something which you call a centripetal force. And I'm sure you must be knowing centripetal force is nothing, it is mv squared divided by r. M is the mass of the object, v is the velocity with which the object moves, and r is the radius over here, right? Now, my dear students, if you understand, since the electron is revolving around the nucleus in the circular path, I told you for any object to revolve in the circular path, it must experience a force called as centripetal force. Then only the object will revolve in the circular path. Yes? Right? Then only the electron revolves in the circular path. Okay? So, what is the point here? Just a second, guys. Just a second, have a look. Since I'm telling you, this electron, it's revolving around the nucleus in the circular path. So, I would say this electron will only revolve in the circular path if this electron will be experiencing a force whose direction which will be directed towards the center. And that force is something which you call a centripetal force, right? Electron will only revolve in the circular path if the electron experiences a force directed towards center, which will make the electron to revolve in the circular path. Now the point is, what is the cause of the centripetal force? Who is going to provide the centripetal force to the electron, right? Who is going to provide the centripetal force to the electron? My dear students, since electron carries the negative charge, nucleus carries the positive charge, positive and negative, there will be electrostatic force of attraction between the nucleus and the electron. So basically, it is the nucleus which is going to attract the electron towards itself, basically. It is the nucleus which is holding this electron. It is the nucleus which is providing the necessary centripetal force in the form of electrostatic force of attraction. So I must say, the necessary centripetal force which is required for an electron to move in a circular path is provided by the nucleus in the form of electrostatic force of attraction. In the form of electrostatic force of attraction. So electrostatic force of attraction is the one which is providing the necessary centripetal force, which makes the electron to move in the circular path, right? Now guys, centripetal force, that is mv square divided by r. M is the mass of electron, velocity of electron, radius of the orbit in which electron is moving. What is electrostatic force of attraction? Electrostatic force of attraction is K Q1 Q2 divided by r square. K Q1 Q2 divided by r square. So my dear students, from here, you are going to get one equation. mv square by r is equal to K, I'm writing as such. What is Q1? Let's assume Q1 is the charge inside the nucleus. That is Ze. What is Q2? Q2 is the charge present on the electron. That is E divided by r square, right? So finally, you are getting one important equation here, which I'll be frequently using, right? One important equation you'll be getting. And the equation is something like this. mv square divided by r is equal to K Ze square divided by r square. This is one important equation, which I'll frequently use while I'll be deriving certain results afterwards in the today's session only, right? So in short, for an electron to revolve in the circular path, the electron must experience a force directed towards center, which is what you call a centripetal force. Now, it is the electrostatic force of attraction between the nucleus and the electron, which is providing the necessary centripetal force to the electron, and then only this electron is revolving in the circular path, right? Right, people? Perfect. Jerusha, yes, almost. Perfect. This was one more point as far as the Bohr's atomic model is concerned. Look at this particular point. Look at this particular point. This is one more important point, right? As far as the Bohr's model is concerned. So what is this particular point all about? Have a look, guys. Understand properly what I'm going to say. As per the Bohr's atomic model, out of the infinite orbits, out of the infinite orbits, electron can only be present in those orbits. Electron will only be present in those orbits in which its orbital angular momentum is an integral multiple of h upon 2 pi. What does it mean? First of all, you should know what is meant by angular momentum. I'm sure linear momentum every one of you would be knowing, right? For example, you have got the particle whose mass is m. The particle is moving with velocity v. The particle is moving with the velocity v. And I'm assuming that the particle is moving in a straight line. If the particle is moving in the straight line, I would say the particle is undergoing translational motion right now. The particle is showing the translational motion, right? My dear students, whenever an object, whenever a particle having certain mass, moving with certain velocity, right, in a straight line, I would say this particle whose mass is m, whose velocity is v, this particle has got some linear momentum associated with it. And that linear momentum associated with the particle is equal to the product of mass and the velocity. The product of mass of the particle and the velocity with which it moves. The product of mass of the particle and the velocity with which it moves. That is something which you call as linear momentum, basically, right? That's what you call as linear momentum. But what is angular momentum? What is angular momentum? My dear students, if you see any object moving in the circular path, let's say I've got one object. This is the object whose mass is m, right? It is moving with some velocity v. If I ask you what is the direction of velocity at this particular point of time, if the motion is anticlockwise, draw the tangent at this particular point. This is going to give you the direction of velocity. And definitely, let's assume this object is following the circular path. So it has got some radius as well. So my dear students, whenever you see an object which has got certain mass, moving with certain velocity, right, in the circular path, there will be one more term which will be associated with this particle. The way linear momentum is associated with this particle. In the similar way, if the object moves in the circular path, there will be angular momentum associated with this particle. And that angular momentum is equal to m multiplied by v multiplied by r, right? Basically, in physics, you study it in detail. It's basically r cross p, right? You get its direction, etc., etc. It is a vector quantity. I'm not going to talk about those things, right? Whatever I need here, I'm going to talk about that only. So whenever you see an object moving in a circular path, right? Whenever the object has got certain mass, certain velocity, moving in a circular path, there will be angular momentum associated with the particle. And angular momentum, which is associated with the particle, is the product of mass, velocity, and radius of the particle. As simple as that, right? Now, my dear students, try to understand a few more things. Try to understand a few more things. See, guys. See, guys, what exactly I'm going to talk about. What Bohr exactly said. What just happened here? A second, guys. What Bohr exactly said? Bohr said out of the infinite orbits, let's say this is the nucleus. Around the nucleus, you'll find some infinite orbits. Around the nucleus, as per Bohr, there will be infinite orbits, my dear students. Right? There will be infinite orbits. What Bohr said, out of infinite orbits, can the electron be present in any orbit over here? If I ask you, can the electron be present in any orbit over here? The answer is no. There are infinite orbits around the nucleus, right? But electron is not going to be present. Electron won't be present in all those infinite orbits. No. Electron will be only present in those orbits wherein the angular momentum of the electron is the integral multiple of h upon 2 pi. See, first of all, angular momentum of an electron is equal to, it can be, h upon 2 pi. I'll write it like this, 2h upon 2 pi. I'll write it like this, 3h upon 2 pi, right? I'll write it like this, 4h upon 2 pi. Perfect. So what exactly I'm doing over here? This is h upon 2 pi. This is 2 times h upon 2 pi basically. This is 3 times h upon 2 pi. This is 4 times h upon 2 pi. Correct? Right? So in general, can I write like this? MVR. MVR is basically equal to NH upon 2 pi. NH upon 2 pi. As per Bohr is concerned, the electron will be only present in those orbits in which the angular momentum will be the integral multiple of h upon 2 pi. What does that mean? See, these are integral multiple of h upon 2 pi. These are the integral multiples of h upon 2 pi. Correct? Right? So electron can be present, electron can be present in the orbit in which angular momentum will be h upon 2 pi, 2h upon 2 pi, 3h upon 2 pi, 4h upon 2 pi. But you will never see an electron in that orbit. You will never see an electron in that orbit in which, for example, angular momentum will be equal to 1.1 h upon 2 pi, 1.5 h upon 2 pi, right? 1.7 h upon 2 pi. These are not the integral multiples of h upon 2 pi, right? My dear students, let's assume this is shell number 1, n value is 1, right? This is shell number 2, n value is 2. This is shell number 3, for example. This is shell number 4. Similarly, there are infinite orbits, right? So if I ask you, if the electron is present in the first shell, what about its angular momentum? What about its angular momentum? MVR. It's going to be h upon 2 pi. It's basically nh upon 2 pi, but put the value of n as 1, so it's going to be h upon 2 pi. If the electron is present in the second shell, its angular momentum is 2h upon 2 pi. If it is in third shell, it's going to be 3h upon 2 pi, right? So electron will be only present in those orbits in which the angular momentum remains the integral multiple of h upon 2 pi. You will never find electron in that orbit in which the angular momentum will be 1.25 h upon 2 pi, right? Nothing like that. Basically, there will be more orbits in between them, right? There will be more orbits in between them. For example, over here, if the electron is present here, its angular momentum will be h upon 2 pi. Let's say if the electron, which is not possible, if the electron was present here, right? Its angular momentum would have been 1.1, for example, 1.1 h upon 2 pi, then 1.2, 1.3, 1.4. But electron, it will be always there in that orbit in which the angular momentum of the electron remains the integral multiple of h upon 2 pi. I believe this is clear to everyone. Yes? Did you get this particular point? Right, people? Did you get this particular point? Say yes or no in the chats quickly. Quickly, say yes or no. Perfect. Now we have got one more point, one more important one. These are the points which you have to remember. Then accordingly, you will see the application part in some time, right? But remember few points first. See guys, as per Bohr's atomic model is concerned, see what we are talking about, Bohr's atomic model, the way Thomson gave one model which was failed afterwards, the way Rutherford gave the nuclear model which was again failed. In the similar way, Bohr also gave one model, right? And what Bohr suggested in this particular model, Bohr said electron when revolving around the nucleus, when electron revolves around the nucleus, it neither loses nor gains energy. When electron revolves around the nucleus, the electron neither loses nor gains energy, right? Perfect. If the electron neither loses nor gains energy, I'll say the electron will continuously revolve in its circular path, right? If the electron would have been losing energy continuously, then what would have happened? The radius of the circular path would have decreased eventually, and eventually electron would have fallen into the nucleus. But that's not the case here. As per Bohr's atomic model is concerned, the electron, when it revolves around the nucleus, it neither loses nor it gains energy, right? It neither loses nor it gains energy. And therefore, the orbits in which electron moves, right? The orbits in which electron moves, in a particular orbit, electron will be having a particular value of energy, right? That's the reason why you call these Bohr's orbits as the stationary orbits, right? Why do we call them as the stationary orbits? Because when the electron is present in some shell, in some orbit, it neither loses energy nor it gains energy. Its energy is constant, it's fixed, it's constant, it's not going to change, right? That's why the orbit in which the electron moves, you call them as the stationary orbits, because in those orbits, electron neither loses nor it gains energy. As simple as that, right? As simple as that. Now guys, slowly we are moving into the actual stuff. This is all the theoretical part, right? Slowly we are moving into the actual stuff. Look at this particular statement. My dear students, as per Bohr, when the electron moves from lower energy state, right? When the electron moves from lower energy state to higher energy state, lower shell to higher shell. When the electron moves from lower energy state to higher energy state, energy is absorbed by the electron. This is important. When you see electron moving from lower energy state to higher energy state, that means when you see this electron exciting, when the electron moves from lower energy state to higher energy state, it absorbs energy. It absorbs energy in the form of radiation. Now the point is, how much energy is absorbed by the electron in order to move from lower energy state to higher energy state? My dear students, let's assume that energy of electron in the first shell is E1, energy of electron in the second shell is E2, for example, energy of electron in the third shell is, for example, E3. Now here, the electron is going from E1 to E3. The electron is going from E1 to E3. The electron is going from lower energy state to higher energy state. When the electron goes from lower to higher, it is going to absorb energy. Now how much energy will be absorbed by the electron? Whatever will be the energy gap between these two shells, whatever is the energy gap between these two shells, if electron gets the same amount of energy, the electron is going to excite from 1 to 3, right? So first of all, if I ask you, what is the energy gap between first and third? Energy gap between first and third will be represented by delta E, and that delta E, which is the energy gap, which is equal to E3 minus E1. E3 minus E1. This is the energy gap. This is the energy gap between first and third shells. If the electron has to go from 1 to 3, the electron has to absorb this much amount of energy, then only it will go from 1 to 3. Now, my dear students, the electron will be absorbing energy in the form of radiation, basically. Imagine if we are providing this much of energy to this electron in the form of radiation, right? It is going to excite from 1 to 3. So this much amount of energy is provided in the form of radiation, basically, in the form of light, you can consider, in the form of light, right? So this much energy we are providing in the form of light. And energy possessed by light is basically your h nu, or you can call it as hc divided by lambda, right? You can call it as hc divided by lambda. My dear students, from this particular equation, what can we conclude? See, the electron is going from lower energy state to higher energy state. It has to absorb energy. How much? The difference between the energies of these two shells. This much energy has to be absorbed by the electron in the form of radiation. The radiation which must be incident on electron, that radiation definitely will be having some wavelength, right? That radiation definitely will be having some of the wavelength, right? And that wavelength which the radiation has, that is represented by lambda. So I'm representing lambda absorbed. This is the wavelength of the radiation absorbed by the electron, right? What was the value of, what was the energy possessed by that radiation? That was E3 minus E1, right? Then only electron moved from first to third. Point number one. Point number two. My dear students, when the electron moves from higher energy state to lower energy state, when the electron moves from higher energy state to lower energy state, for example, now the electron is moving from higher energy state to lower energy state. For example, third to one. Electron is moving from higher to lower. When the electron moves from higher to lower, it is going to emit energy. Over here, the electron was absorbing energy. How much? E3 minus E1. Now the electron is coming back from 3 to 1. Whatever amount of energy electron had absorbed during this transition, same amount of energy electron is going to emit if it comes from 3 to 1. Right? If it comes from 3 to 1. Perfect. So over here, I will say energy is absorbed, and here energy is emitted. Energy is emitted in the form of radiation only. In the form of radiations only. Right? Is this point clear? Now, if you ask me, how much energy is released here? Electron is moving from 3 to 1. How much energy is released? Again, whatever is the difference between these two energy states, the difference between the energy gap between these two will be, electron is going from 3 to 1. 3 to 1. This is initial state, this is final. Final minus initial. It's going to be now, delta E is going to be now E1 minus E3. Final minus initial. Right? Perfect. E1 minus E3. Energy is emitted by the electron in the form of radiation, in the form of Hc divided by lambda. Now, this lambda, is it going to be lambda absorbed or lambda emitted now? It's going to be lambda emitted now. I hope this particular point is also clear to you. Right? I hope this particular point is clear to you. My dear students, if I ask you what will be the difference between these two? What will be the difference between these two? Difference will be only in the sign. Over here, E1 minus E3 value will come out to be negative. Over here, E3 minus E1 value will come out to be positive. This negative sign indicates that energy is emitted by the electron in the form of radiation. This negative sign, the difference will be only in the sign. This negative sign indicates that energy is emitted by the electron, and this positive sign will indicate that energy is absorbed by the electron in the form of radiation. I believe it's clear to everyone, right? Clear, people? Yes? So whatever amount of energy electron had absorbed in going from 1 to 3, when the electron comes back from 3 to 1, same amount of energy electron is going to release, right? So magnitude wise, both these values will be same, right? This E3 minus E1, this E1 minus E3. Magnitude wise, both are same. Only the difference is in sign. In one case, it's going to be positive. In another case, it's going to be negative. That's it, right? And this negative sign, it signifies that energy is emitted by the electron in the form of radiation. Positive sign indicates that energy is absorbed by the electron. Let me write it over here. The significance of positive and negative. See, this value you will get as positive. Positive sign signifies that energy is absorbed by the electron during the transition, right? Or just let me write it till here only. Similarly, negative sign is going to indicate that energy is released. Energy is released by the electron. And now it's evident when energy is released by the electron, when it makes a transition from higher to lower, right? I believe this point is clear to everyone. Now, my dear students, let's come to our actual stuff now. That is application of Bohr's theory. So, let me mark the heading over here as formulae related to Bohr's theory. all the formulas which are related to Bohr's theory, right? All the things which are related to Bohr's theory. The first thing we are going to calculate the radius of an orbit, in which the electron moves. We are going to calculate that, right? Radius of an orbit in which the electron moves, right? Or let me make it like this. I'll say radius of nth Bohr's orbit. Radius of nth Bohr's orbit. This is the first point which we are going to calculate here. Radius of nth Bohr's orbit. Now, how exactly you guys are going to get the radius of nth Bohr's orbit? That's important. Understand? Guys, ionization energy is different. Leave it. I'm not going to talk about that. Right? I'll be talking about ionization energy, excitation energy, etc., in some time. Right? See, guys. First of all, in order to get the radius of the orbit, for example, let me show you one thing. Let's say this is the nucleus, right? Let's say electron is revolving around the nucleus. Let's say this is the electron here, for example. Electron is revolving around the nucleus. Now, I'm assuming the shell number of this orbit, the shell number in which the electron is moving. Let's say that is n. I want you guys to calculate. I want you to calculate the radius of this nth Bohr's orbit. This is nth Bohr's orbit, right? This is shell number n. That's why I'm calling this as nth orbit. I want you guys to calculate the radius of nth Bohr's orbit. This particular radius I want you guys to calculate. How exactly you're going to calculate? See, first of all, already we have discussed one equation, if you remember. mv square divided by r is equal to k ze square divided by r square. This is one equation which we have discussed already, right? Already we have discussed. So one of the r gets cancelled. So you can write it like this. mv square is equal to k. This is ze square divided by r. Perfect. There is one more equation which we have discussed. What was that? That was mvr is equal to nh upon 2 pi. Correct? My dear students, can I eliminate v from here? V will be equal to nh upon 2 pi. nh upon 2 pi. And it's going to be m multiplied by r. Perfect. I've eliminated v from here. Okay. Since I've eliminated v from here, this is the main equation. These are the two main equations, this one and this one, right? Since what we have done, we have eliminated v from here. Now I'm going to introduce v in this particular equation. So it's going to be m, v square. V square means it's going to be n square h square divided by, it's going to be 4 pi square, m square and r square, right? It is equal to k ze square divided by r, right? Perfect. Now, let's exactly see what all parameters will get cancelled out. So this m and one of the m gets cancelled out, number one, right? One of the r gets cancelled out, right? Is there any other thing? I don't see something like that. So my dear students, from here, I'll be getting the r value. This r I'll take here, right? So r value is simply going to be n square h square divided by n square h square. It's going to be 4 pi square m multiplied by k multiplied by z multiplied by e square. So which radius I'm calculating right now? I'm calculating the radius of nth orbit. I'm calling this orbit as nth orbit. I want to calculate its radius. So radius of nth orbit is equal to n square h square divided by 4 pi square m k z e square. Now, my dear students, if you properly analyze things, have a look what exactly we are going to do. See, first of all, what is n? N is the orbit number in which the electron is moving. It can be 1, 2, 3, 4, right? H is Planck's constant. 4 is constant, pi is constant, m is constant, k is constant, e is constant. What is z? Z is the atomic number of the atom of an element which we are talking about, right? So I would say radius of nth Bohr's orbit will be equal to, since all these are constants except n and z. So instead of all these constants, I'm writing r naught, n square divided by z. This is one basic result which you are going to remember from now onwards to calculate the radius of the Bohr's orbit, right? Let me first of all tell you this r naught value is equal to 0.529 angstroms. R naught value is 0.529 angstroms. Now, my dear students, you can clearly understand things. See, radius of the orbit is directly proportional to orbit number. More the orbit number, it's evident, more the orbit number, more will be the radius of that orbit, right? More the orbit number, that means more will be the radius of the orbit. Simple. Radius and Z inversely proportional. More the Z value, more the atomic number. More the atomic number means more will be the protons in the nucleus. More protons means more positive charge in the nucleus. More positive charge in the nucleus means the nucleus is going to attract the electrons more towards itself. What will happen to the radius of the Bohr's orbit? It will decrease. Right? All these things are evident. You know them. Okay? Now, people, since you got to know radius of nth Bohr's orbit, it's directly proportional to n square, inversely proportional to z. By chance, if you are supposed to compare the radius of two Bohr's orbits of two different atoms. Let's say you've got two different atoms, right? You have to compare the radius of two Bohr's orbits in two different atoms. How you are going to compare? It's going to be R1 divided by R2 will be equal to N1 square divided by N2 square multiplied by Z2 divided by Z1. This is how you guys are going to compare, right? This is how you guys are going to compare. I believe it's clear to everyone, right? Right, people? Now, first of all, if you ask me, can we make any graphs related to radius? Can we make any graphs related to radius? Absolutely, yes. Why not? We can plot a lot of graphs related to radius. Have a look, guys. Understand. This is your general equation. This is your general equation. Case number one. Case number one. If, for example, you are keeping n as constant. Let's say n is constant. If n is constant, that automatically tells you n square is constant. That automatically tells you n square is constant, right? So first of all, if n is equal to constant, keeping n is equal to constant, can you plot a graph? Can you plot a graph between radius of nth Bohr's orbit, and z? Similarly, keeping n constant, can you plot a graph between radius of nth Bohr's orbit and 1 upon z? You should be able to do it. You should be able to plot these graphs. See, guys, already we know radius of nth Bohr's orbit, it's equal to r naught n square divided by z, right? Rn and z, they are inversely proportional. Whenever you have to plot a graph between two variables which are inversely proportional to each other, the nature of the graph has to be hyperbola. So it's going to be rectangular hyperbola, right? It's going to be rectangular hyperbola. You know it. Perfect. Similarly, you can write the same equation like this. Rn is equal to r naught n square separately, 1 upon z separately. Rn you are plotting along y-axis, 1 by z you are plotting along x-axis. This term becomes your slope. So y is equal to mx form. Y is equal to mx form. Y is equal to mx is a straight line. If it is a straight line passing through origin, that means its slope. Its slope is m, and m value here comes out to be r naught n square. Right? Right, people? Simple? Isn't? Isn't it very simple? So, first of all, what did we do? We made two graphs over here, keeping n constant. Now, two more graphs can be formed. My dear students, since I kept n constant, by the way, I could have kept z constant as well. Absolutely, I could have kept z constant. Keeping z constant, can we plot a graph between radius of nth Bohr's orbit versus n, or radius of nth Bohr's orbit versus n square, keeping z constant? First of all, what is our general formula? Radius of nth Bohr's orbit is equal to r naught n square divided by z. I'm keeping z constant right now. R naught is already constant, right? So you can write as Rn is equal to r naught divided by z multiplied by n square. Now look at the first curve. Radius of nth Bohr's orbit you are plotting along y-axis. This is something which you are plotting along x-axis. So this term you are plotting along y-axis. N you are plotting along x-axis. So instead of n you are going to write x. This is x square. This is the constant k, for example. Y is equal to kx square. What is the nature of the curve for the equation y is equal to kx square? It's parabola opening upwards, right? It's parabola opening upwards. This is the first curve. Similarly, my dear students, look at the second curve. This is something you are plotting along y-axis. This is something which you are plotting along x-axis. So instead of this particular term, you are going to write y, right? Instead of n square, Instead of this particular n square, you are going to write x, and this whole term becomes your m. Y is equal to mx is absolutely going to be a straight line passing through origin, and its slope, slope means m. Slope is nothing, it's r naught divided by z. So these are certain graphs which you can make over here, right? These are certain graphs which you can make over here. Perfect? Clear? So I believe you got to know how the radius of nth Bohr's orbit was calculated. That was our first point of discussion. Now similarly, my dear students, since we got to know how to calculate the radius of a Bohr's orbit in which electron is moving, now the point is, how do we calculate the velocity with which the electron moves? How do we calculate the velocity in which the electron moves in a particular orbit? So I'm marking the heading as velocity of the electron in the nth Bohr's orbit. Velocity of the electron in the nth Bohr's orbit. So velocity of electron in the nth Bohr's orbit is represented by Vn. How do we calculate this particular term? Let's try to understand. See, when electron will be revolving around the nucleus, it will be having some velocity, right? How do we get that velocity? First thing, you know one of the equations, mv square divided by r is equal to a ze square divided by r square. This is one of our main equation. Second equation, mvr is equal to nh upon 2 pi, right? So, my dear students, can I eliminate r from here? Absolutely. R can be nh upon 2 pi multiplied by mv. Perfect. So first of all, one of the r gets cancelled. You get something like this. mv square is equal to k ze square divided by, this is r here, right? Instead of r, you can write nh divided by 2 pi mv. That 2 pi mv will come in the numerator. I believe it's clear, right? Perfect. So one of the v and one of the v gets cancelled out. So you can eliminate v from here. This m and this m gets cancelled out. So v will be equal to, it's going to be 2 k ze square multiplied by pi divided by nh. Since we are calculating the velocity of the electron in the nth Bohr's orbit, right? And I got one of the important results here. So my dear students, try to understand few things. Over here in the numerator there is z. In the denominator there is n. Rest all the terms are constants. You can multiply, divide everything, and finally, what you'll observe, you'll get one result. Result is something like this. Velocity of the electron in the nth Bohr's orbit. Instead of all the constants, I'll be writing v naught multiplied by z divided by n. This is the result by means of which you can calculate the velocity of the electron in the nth Bohr's orbit. Velocity of the electron in the nth Bohr's orbit, right? Now, people, this v naught value, do remember this v naught, it's a constant whose value is 2.18 into 10 raised power 6 meter per second, right? V naught is a constant over here. Now, imagine. Velocity of the electron, it is directly proportional to z, inversely proportional to n. So more the n value, more the orbit number, that means far the electron from the nucleus, less is going to be its velocity with which it's moving, right? So v and n, they're inversely proportional. So if the electron goes far from the nucleus, as the electron keeps on going far from the nucleus, right, the velocity with which the electron moves, that will be decreasing, right? As the electron will be closer to the nucleus, the electron will be moving with more velocity. As the electron keeps on going far from the nucleus, the velocity with which the electron moves, it will keep on decreasing, right? Simple. Similarly, Z, atomic number. More the atomic number, more the velocity. Why? More the atomic number means more the protons. More the protons means more the positive charge. More the positive charge means more the force of attraction between electron and the nucleus. More force of attraction means nucleus will be attracting electron more towards itself, due to which electron will come closer. If electron is coming closer, that automatically tells you velocity will increase. As simple as that. Now, people, if I ask you, you have got two atoms, you have got two hydrogen-like species, right? You have got two hydrogen-like species. Electron is revolving in both hydrogen-like species. You have to compare the velocity of electrons moving in those two Bohr's orbits in two different atoms. How do you do that? It's simple. You'll write V1 divided by V2. It has to be equal to Z1 divided by Z2 multiplied by N2 divided by N1. This is how you compare the velocities of electrons moving in two different Bohr's orbits of two different hydrogen-like species. Simple. Now, if you ask me, can we make certain graphs here? Can we make certain graphs here? The answer is, I'll never say no, right? We can make. Let's see what all curves we can make here. See guys, first thing, keeping what constant? Keeping Z constant, for example. I'm keeping Z constant. I'm keeping Z constant here. If I keep Z constant, I'm going to make two curves. First curve is velocity of the electron in the nth Bohr's orbit versus n. The second curve is velocity of the electron in the nth Bohr's orbit versus 1 by n. These are the two graphs which I'm making here. Now you tell me the nature of the graphs. So first of all, velocity and n, directly or inversely, they are inversely proportional. Whenever you have to make a curve between two variables which are inversely proportional to each other, the nature of the curve is going to be rectangular, hyperbola. This has to be the hyperbola here, right? Similarly, second one, you know, your velocity of nth Bohr's orbit is equal to V0 you are writing as such, Z you are writing as such, 1 by n as such. Vn you are plotting along y-axis. 1 by n you are plotting along x-axis. So instead of Vn you'll write y. Instead of this 1 by n, you'll write x. This whole term becomes your m. Y is equal to mx. Y is equal to mx means straight line. If it's a straight line, what about its slope? Slope is going to be m basically, which is V0 multiplied by z. Now if you ask me, are there only two curves which we can make? No, we can make one more curve. Yes, we can make one more curve. If I write the second thing, keeping n constant. If I keep n constant and want to plot a graph, between velocity, keeping n constant, I'm going to make a graph between velocity and z. You know, Vn is equal to V0 divided by n multiplied by z. This Vn you are plotting along y-axis, z you are plotting along x-axis. So instead of this you'll write y, instead of this you'll write x. This whole term becomes your m. So y is equal to mx, has to be a straight line. If you ask me about its slope is going to be V0 divided by n. Clear? Is it clear, people? Is it clear? So this is how we calculate the velocities, right? This is how we calculate the velocity of electrons in moving in different Bohr's orbits. The third application. I hope you got the first two applications. The first application was calculation of radius of the nth Bohr's orbit. Second was calculation of the velocity with the electron moves. Third is calculation of time period. How do we define the time period? Time period of the electron in the nth Bohr's orbit. How do you define it? Time taken to complete one revolution. That's it. Right? Right, people? Simple. Time taken to complete one revolution. Time taken to complete one revolution is something which you call as time period. Now guys, try to understand how it's calculated. See, first of all, you know, speed is equal distance divided by time, and therefore time has to be equal distance divided by speed. Time has to be equal distance divided by speed. You know it. Imagine the electron is moving in this circular path. This is the nucleus, right? This is the nucleus. This is, for example, the electron here. Let's say the orbit number of this particular orbit is n. Let's assume the radius of this particular orbit is Rn. Rn is the radius of this particular orbit, right? So, if I ask you how to calculate time period of this particular electron right now in the nth Bohr's orbit. This is your nth Bohr's orbit, nth Bohr's orbit. It can be anything, 1, 2, 3, 4, whatever, right? Nth Bohr's orbit. How do we calculate time period? What is time period? Time taken to complete one revolution. Time taken to complete one revolution. The time taken to complete one revolution is called as time period of the electron here, right? So it has to be equal. Distance covered by the electron. Can you tell me what is the distance covered by the electron in order to cover one revolution? Simple circumference. It is 2 pi and the radius of the orbit, radius of the nth Bohr's orbit, divided by speed with which the electron moves. Velocity of the electron in which the electron moves. With which the electron moves. That's it. Right? So time period of the electron in the nth Bohr's orbit is equal to 2 pi, you are writing as such. What is Rn? What is Rn? Rn is basically R naught n square divided by z. You know it. What is Vn? It is V naught multiplied by z divided by n. If I put the value of all the constants here, what I'll be getting? I'll be getting time period of the electron in the nth Bohr's orbit is T naught. T naught. It becomes n cube divided by z square. N cube divided by z square. What is the value of this T naught? T naught value is 1.5 into 10 raised power minus 15 seconds. Is it 10 raised power minus 15 or minus 16? Let me check. Let me cross verify. Just a second. Just a second, guys. It is 10 raised power. 10 raised power minus 16. Sorry, yeah. It is 10 raised power minus 16. 1.5 into 10 raised power minus 16 is here. Okay. This is how you calculate the time period of the electron. Perfect. Now, guys, if I ask you something like this, calculate the, if I ask you, is it possible to compare the time periods of two electrons moving in two different orbits in two different, hydrogen-like species? Absolutely, you can do that. Time period is directly proportional to n cube, inversely proportional to z square. So, T1 divided by T2 has to be equal n1 cube, n2 cube multiplied by z2 square divided by z1 square, right? And my dear students, if you want to plot any graph, you can easily plot the graphs. You can easily plot the graphs here, right? You can easily plot the graph. So this was how do we calculate the time period of the electron. If I ask you, how do we calculate the frequency? If you got the time period, you can easily calculate the frequency, right? Frequency of the electron in the nth Bohr's orbit. What is frequency? As you know it, it's inverse of time period, 1 by t. Right? If you can calculate time period, that automatically tells me that you can calculate frequency as well, which is 1 by time period. Right? 1 by time period of electron in the nth orbit. It is 1 divided by T naught n cube upon z square. Or in general, I can say frequency of the electron in the nth Bohr's orbit, it's directly proportional to z square, inversely proportional to n cube. Simple. Or if you want to calculate the exact value, you can use this expression, right? Now, people, if you need to compare the frequencies of two electrons moving in two different Bohr's orbits, of two hydrogen-like species, it has to be z1 square divided by z2 square multiplied by n2 cube. This is n1 cube. This is how you are going to compare. The time periods of two electrons. Right? Perfectly done? Perfecto. Perfectly done and dusted. Tell me the answer of this question quickly. Tell me the answer of this question quickly. Tell me the answer of this question. See, guys, it's a very simple and basic question. I'm damn sure you can easily solve it. Calculate the radius ratio of second orbit of He positive, and third orbit of Be tripositive. So these are two hydrogen-like species which are given to us, single electron species, right? First of all, calculate the radius ratio of second orbit of He positive. So we are given with second orbit of He positive, right? Atomic number of helium is hydrogen helium 2. Perfect. Let's assume its radius is R1. And third orbit of B tri-positive, hydrogen helium lithium beryllium, atomic number 4. Its radius B it as R2. So we have to get the radius ratio of, we have to get the value of R1 divided by R2, right? R1 divided by R2 is N1 square divided by N2 square. This is Z2 divided by Z1. Simple. N1 square, 2 ka square is 4. N2 square, 3 ka square is 9. Z2 divided by Z1. Z2 is 4 and Z1 is 2, right? So this is 2, 1. This is 2. This is 4 to Z, 8 is to 9. So 8 is to 9 is the radius ratio here. Simple, nothing to do here. Isn't it simple? Isn't it simple, guys? And you will be getting these simple questions only here, right? These simple questions only you'll be getting here. I believe it's clear. Look at this one. Look at this one. Look at this one. If the velocity of the electron in the first orbit of hydrogen atom is there, is talking about the velocity of the electron in the first orbit. In the first orbit of hydrogen atom is V. Velocity of the electron in the first orbit of hydrogen atom is V. What is the atomic number of hydrogen? It's 1. What will be the velocity of the electron in the third orbit of Li positive? There is Li positive given. In the third orbit, he is saying. In the third orbit, its atomic number. How much will be that? Hydrogen, helium, lithium. 3, right? What about its velocity? V2 we have to calculate. Already I've told you, I've already mentioned how do we compare the velocities of the electrons, right? You know, V1 divided by V2. It was basically Vn used to be equal to V naught Z by N. So it has to be Z1 divided by Z2 multiplied by N2 divided by N1. That's it. V1 value is V. V2 you have to calculate. Z1 by Z2. So 1 by 3 multiplied by N2 divided by N1. This is 3. So 3 cancel. So V is equal to V2. So you got the V2 value. It's coming out to be V. Isn't it simple? Isn't it simple, people? Done? In an atom, 2 electrons move around the nucleus in the circular paths of radius r and 4r. Perfect. The ratio of time taken by them to complete one revolution. Simple. Can you solve this question? In an atom, 2 electrons move around the nucleus in the circular paths of radius r and 4r. Perfect. The ratio of the time taken by them to complete one revolution is. Can you solve this? Say yes or no in the chats. Say yes or no in the chats. Quickly, people. Quickly. You can do it, right? This is your homework question. You are going to let me know its answer in the comment section at the end of the session, right? So till now we were doing the discussion related to radius, velocity, time period, and frequency. But do tell me its answer in the comment section, okay? Now there comes one more important thing. Now, guys, I'm not going to derive a lot of things. I'm just going to give you the results and let's see exactly how do we apply them. Let's see exactly how do we apply them, okay? See, guys, understand. Energy of the electron in the Bohr's orbit. Directly, I'm giving you the results. If you want its derivation is also there, but I don't feel like derivation is of any use here. It will just take a lot of time to derive all those things. The way we derived radius, velocity, time period, right? Leave this part aside and I shall be giving you the results and we shall be trying to apply those results. Try to apply those results. First of all, let's assume that. Just a second, guys. Can you hear me? Can you hear me? Can you hear me? There was one mic issue. Can you hear me? Yes or no? Can you hear me? Physics class will happen at 7, not now. He'll take it 7, I've told him. All right, all clear. One more hour, guys. One more hour. Energy of the electron in the Bohr's orbit. See, for example, I've got an atom. This is the nucleus of the atom. And let's assume that atomic number of the atom of the element is Z. Z is the atomic number. This is the electron here, which is revolving around the nucleus, for example. The electron is revolving around the nucleus. Since the electron is revolving, electron is in motion. If the electron is in motion, can I say there will be definitely some kinetic energy associated with the electron? Absolutely, there will be some kinetic energy associated with the electron. Now, similarly, when the electron will be revolving, the nucleus will be attracting the electron towards itself, right? When the electron was here, nucleus will be attracting. When the electron was here, nucleus will be attracting. When the electron will be here, nucleus will be attracting. So there is force of interaction between nucleus and electron. And due to interaction, interaction gives rise to what? Interaction gives rise to potential energy. Interaction gives rise to potential energy, right? And similarly, if I ask you what about the total energy possessed by the electron in the nth Bohr's orbit, you will say it is the sum of kinetic energy possessed by the electron and the potential energy possessed by the electron. This is something which is evident, right? Kinetic energy is due to what? Is due to the motion, since revolving. Due to the interactions, potential energy arises in the system, and total energy will be the sum of kinetic and potential, right? Now, guys, let me give the direct results. Direct results I'm giving you, okay? Let me first of all tell you total energy possessed by the electron in the nth Bohr's orbit, which is represented by E. Total energy possessed by the electron in the nth Bohr's orbit. It is equal to minus 13.6 Z square divided by N square electron volts. Total energy possessed by the electron. Kinetic energy possessed by the electron in the nth Bohr's orbit. This is equal to plus 13.6 Z square divided by N square electron volts. Potential energy in the nth Bohr's orbit. It is equal to minus 27.2 Z square divided by N square electron volt. These are three results which I would want every one of you to remember directly. This is the total energy possessed by the electron. This is the total energy possessed by the electron in the nth Bohr's orbit. Kinetic energy possessed by the electron in the nth Bohr's orbit. Potential energy of the system in the nth Bohr's orbit. Okay, perfect. Now, guys, one more thing. Well, first of all, from these particular results, you can directly relate them, right? You can relate them as well. See, this is minus, this is plus. Magnitude-wise, they are same. You can say total energy possessed by the electron in the nth Bohr's orbit, right? It is equal to minus times. It's equal to minus times the kinetic energy possessed by the electron in the nth Bohr's orbit, right? Which will be equal to what? Which will be equal to. Look at this particular result. Look at this particular result, guys. If you look at this particular result, I'll say potential energy is equal. I can write this result like this. 2 I'll write outside. Then I'll write minus 13.6 Z square divided by N square. Right? What is this particular term? This is total energy. So potential energy is basically equal to 2 times the total energy. Right? Minus 13.6 Z square by N square. That's the total energy. So potential energy is equal to 2 times the total energy. Or you can say total energy is equal to potential energy divided by 2. So total energy is equal to potential energy divided by 2. Right? Do remember this particular result as well. This is the total energy possessed by the electron in the nth Bohr's orbit. It is equal to minus times the kinetic energy, which is equal to potential energy divided by 2. Do remember this particular format as well. Okay? And it's simple. And my dear students, at the same time, whenever you will have to compare the energies of electrons in the two Bohr's orbits, total energies possessed by the electrons in the Bohr's orbits, how you are going to do it? E1 divided by E2 is equal to Z1 square. This is Z2 square multiplied by n2 square divided by n1 square, right? If they ask you to compare you the energies of two Bohr's orbits, energies of electrons moving in two different Bohr's orbits, then this is the result by means of which you can compare the energies. Okay? Right? All clear till here? Now, people, it's time to apply the same thing. It's time to apply the same thing. Right? Time to apply the same thing. Let's try to apply all these things. Let's try to apply all these things. Right? But before applying all these things, tell me just one thing. Tell me just one thing. Total energy possessed by the electron in any Bohr's orbit, it is inversely proportional to n. So first of all, you can make different types of curves here. Let's first of all make certain graphs related to total energy. Graphs related to total energy possessed by the electron in the nth Bohr's orbit. What is your result? The result to calculate total energy in the nth Bohr's orbit is equal to minus 13.6 Z square divided by n square electron volts. Right? Now, my dear students, one by one we are going to make the graphs. First one, if for example I'm keeping Z constant. If I'm keeping Z constant. If Z is constant. If Z is constant, that automatically is telling you Z square is constant. That automatically is telling you Z square is constant. So at constant Z square, let me plot a graph. Let me plot a graph between En versus n square. Number one. Second, between En versus 1 by n square. You can make these curves. Absolutely, you can do that. First of all, have a look. You know the equation. Energy of the electron in the nth Bohr's orbit is equal to minus 13.6 Z square, and this is 1 upon n square. So first of all, E and n square, they are inversely proportional. They are inversely proportional, absolutely. My dear students, they are inversely proportional. So if you want to plot a curve between En and n square, since they are inversely proportional, the nature of the curve is rectangular hyperbola. The graph has to be like this, right? It has to be like this. But there is a negative sign here. If there is a negative sign, that means what you will have to do, you will have to make the same graph, but in this particular quadrant. You will have to take the reflection of this particular graph. This is going to be the nature of the graph. Right? Hyperbola, you are making in this particular region. This is n square. And hyperbola you are making in this particular region. I hope this is clear. Second, En versus 1 by n square. En versus 1 by n square. You know, it can be written as minus 13.6 Z square multiplied by 1 upon n square. So my dear students, En right now you are plotting along y-axis. 1 by n square you are plotting along x-axis. So this term has to be your m. So y is equal to mx. Y is equal to mx. But there is a minus here. Y is equal to minus mx. So the graph which was supposed to be like this, it won't be like this. It won't be like this. It will be like this, right? Perfect. The graph will be like this because there's a negative sign. Perfect, because there's a negative sign. Okay, I hope this is also clear. Similarly, my dear students, if I do one more thing, if I keep n constant, keeping n constant, right? Keeping n constant. Let's try to make a graph between energy versus Z square. Similarly, one more graph between energy and Z. What do you think is the nature of the curve? If n is constant, that means n square is constant. You know it. If n is constant, that means n square is constant. Now, energy you are plotting along y-axis. Z square you are plotting along x-axis. So instead of Z square, you are going to write x. This is y, this is x, and this whole term is minus m. Y is equal to minus mx. Y is equal to minus mx. This is the graph. This is the graph, guys. Right? Y is equal to minus mx. Perfect. This is the graph here. y is equal to minus mx. Perfect. Now similarly, En versus Z. En versus Z. Tell me one thing. En versus Z. This is y. Z you are plotting along x-axis. So instead of Z you'll write x. So this is x ka square. Y is equal to x ka square. Y is equal to x square is like this. But there is a negative sign. It has to be like this. Only what you are doing, you are just taking the reflection of the graph about your x-axis. Perfect. So these are your graphs which can be asked related to your energy. I hope again it's clear to everyone. Is it? If it is clear, tell me one more thing. If it is clear, tell me one more thing. My dear students, this is the total energy possessed by the electron, right? Since total energy, it is inversely proportional to n. What does that mean? Does that mean on increasing n, E decreases? Does that mean on increasing n, E decreases? The answer is no, because there's a minus sign here. There's a minus sign here. See, it's evident, guys. It's very much evident. If you increase n, this particular term, if you increase n, that means you are increasing n square. And when you are increasing n square, that means z square divided by n square term. This whole term you are decreasing. If you are decreasing this term, that means this term you are decreasing. Which term? 13.6 z square divided by n square. This term you are decreasing. And if you are decreasing this term, multiplying with minus, that means this whole term will increase. And if this whole term will increase, what does that mean? That means energy of the electron in the nth Bohr's orbit will increase. Right? So as the n increases, energy of the electron in the nth Bohr's orbit increases. What does that mean? As the n increases, that means as the electron keeps on going far, as the n increases, as the electron keeps on going far, its total energy keeps on increasing. Right? Right, people? Is it clear? Is it clear, people? Let me know. Safari 76. Sir, you are not having the same energy. Do you want me to shout? With experience, you lower down the voice. You focus on the words which you speak, right? With inexperience, you shout. Okay? So maybe at that time, years back, I had some lesser experience. That's why I used shout in the class and all, right? People, is it clear? Is it clear, guys? So this particular statement you have to remember. As the value of n increases, the total energy of the electron, it will increase. So as the electron keeps on going far from the nucleus, energy of the electron will keep on increasing. Now, people, there are a lot of things which we have to discuss now related to this energy. Have a look. I'm going to talk about particularly the hydrogen atom. In case of hydrogen atom, atomic number Z, that's 1. For hydrogen, Z is equal to 1. You know it, right? Now we'll try to understand what exactly I'm going to do. I'm going to make you understand some basic things, right? Some basic things I'm going to understand. I'll make you understand. I won't be able to make them parallel. So you'll imagine these are parallel, right? You'll imagine these are parallel. You'll imagine these are parallel. Okay. I'm going to discuss about what? I'm going to discuss about the hydrogen atom, right? My dear students, since I'm talking about the hydrogen atom, let me call this as n is equal to 1. Let me call this as n is equal to 1. Let me call this as n is equal to 2 for hydrogen, n is equal to 3 for hydrogen, n is equal to 4 for hydrogen. This is n is equal to infinite for hydrogen. There are infinite orbits, you know it, right? Yeah. Now we will try to understand few things. Few things you have to understand. Let me first of all tell you this n is equal to 1. This is something which you call as ground state for hydrogen. This is the ground state of hydrogen. This is called as first excited state of hydrogen. First excited state of hydrogen. This is the second excited state of hydrogen. This is the third excited state of hydrogen. This is the third excited state of hydrogen. Okay. Imagine the electron is present in shell number 1. Imagine electron is present in shell number 1. If I ask you what is the energy, what is the total energy carried by this electron when present in shell number 1? Since you know total energy possessed by the electron in the nth Bohr's orbit, it's equal to minus 13.6 z square divided by n square. Since electron is present in first shell, n is 1, z is already 1. So energy of the electron in the first shell is minus 13.6 electron volts. Because this term, they are 1. When the electron reaches shell number 2, what is the energy possessed by the electron? Minus 13.6, z is 1. Divided by n is 2, 2 ka square is 4. So minus 13.6 divided by 4. Minus 13.6 divided by 4, which comes out to be minus 3.4 electron volts. Right? When the electron reaches the third shell, energy carried by the electron in the third shell is equal to, put n is equal to 3, 3 ka square is 9. So minus 13.6 divided by 9 will be minus 1.85 electron volts. Right? When the electron is in fourth shell, energy possessed by the electron, this is 4 ka square, that is 16. So minus 13.6 divided by 16 comes out to be, I believe, minus 0.8 something. Let me check it. Minus 0.85. Minus 0.85. And this particular term, it is minus 1.50, sorry. Minus 1.50 electron volts. Correct? Now tell me one thing. If the electron is in this particular shell, n is equal to infinity. If you put n as infinity here, division by infinity is 0. So energy possessed by the electron in the infinite energy state, that is 0. So first of all, let me make you understand what is this infinite energy state. Can actually electron be present at infinity? What does it mean? What does it mean? My dear students, try to understand. When the electron is in first shell, it is under the influence of the nucleus. Second shell, electron is under the influence of the nucleus. Third shell, electron is under the influence of the nucleus. That means nucleus is attracting electron. Fourth shell, electron is still under the influence of the nucleus. But electron is going far. Distance between nucleus and electron is increasing. If distance is increasing, force of attraction is decreasing. If electron keeps on going far, force of attraction is decreasing. There will be a stage when the electron will be out of the influence of the nucleus. When electron won't be attracting this, when the nucleus won't be attracting this electron further. Right? As the electron keeps on going far, the force of attraction decreases between the nucleus and the electron. The force of attraction decreases. Electron is going far. The force of attraction decreases. Now electron has reached at a point at which electron is not under the influence of the nucleus. The electron has come out of the influence of the nucleus. Now there is no attraction on electron from the nucleus. And when electron reaches at that point, we say electron has reached at the infinite energy state. Right? Right, people? Is this clear to everyone? Quickly, my dear students. Let me know this particular thing in the chats. Quickly, if it is clear. Right? So, whenever from now onwards, I'll say the electron is at infinite energy state. What does it mean? It means the electron is out of the influence of the nucleus. Okay. Perfect. So, my dear students, one more thing. The sign here is negative. Negative. As you see, as the electron is going far from the nucleus, energy is increasing. First, it was minus 13.6. Now, it is minus 3.4. Now, it's minus 1.5, minus 0.8. So, energy of the electron is increasing as the electron goes far, which I told you already. As the n increases, energy increases. The maximum value of energy of the electron is at infinite energy state. That is 0. Right? Now, you must be thinking, energy cannot be negative. Energy cannot be negative. So why this sign? Why this sign of negative? My dear students, let me tell you, the negative sign signifies that the electron is under the influence of the nucleus. The electron is under the influence of the nucleus. Right? Right, people? Negative sign signifies that the electron is under the influence of the nucleus. Perfect. Now tell me one thing. If I ask you what is the difference, what is the energy gap between these two shells? What is the energy gap between these two shells? Energy of the first shell is minus 13.6, second is minus 3.4. So energy gap between first and second, delta E, which is E2 minus E1. How much that will be? How much that will be? E2 minus E1. So minus 3.4 minus 13.6, right? The value comes out to be how much? This will be 2, right? This will be 2, this will be 0, this will be 1. 10.2 electron volts. So what is this 10.2 electron volts? It is the energy gap between the first and the second shell, right? And I hope you got to know how I calculate this energy gap. So energy gap between first and the second shell, that is 10.2 electron volts. Energy gap between second and third, 1.89 electron volts. It is simply E3 minus E2, right? Energy gap between first and third, E3 minus E1, this much. Energy gap between first and fourth, this much. Perfect. My dear students, if you understand one thing, the energy gap between first and the second shell was 10.2 electron volts. The energy gap between second and third, it has decreased. The energy gap between third and fourth, it will further decrease. Fourth and fifth, it will further decrease. So energy gap between the two consecutive shells, or I will say the energy gap between the successive shells, it keeps on decreasing. It keeps on decreasing, right? It keeps on decreasing. I believe it's clear to everyone. Right, people? Is it clear? Say yes or no in the chats. So as the number of shells increase, the energy gap between the successive levels, that decreases. Do remember this particular point as well. I hope this is clear to everyone. Right? Perfect. Now, my dear students, same scenario. Whatever I showed for hydrogen atom. If you will be having a hydrogen-like atom, imagine you'll be having a hydrogen-like atom. Hydrogen-like. Hydrogen-like means there will be some atomic number, right? This is the diagram for the hydrogen-like atom. The energy of the electron in the first shell will be minus 13.6. Z square, N is 1, right? You cannot neglect Z in the formula. Perfect. You cannot neglect Z in the formula, right? Because you have got hydrogen-like, like He positive. You cannot neglect Z there. Z is not 1. For example, Be tri-positive, Z is not 1. So this is the energy in general. This is the energy possessed by the electron in the first orbit of hydrogen-like atom. Second orbit, third orbit, fourth orbit, and here will be infinite energy state. Perfect, infinite energy state. Now, my dear students, here the difference between the first two. The magnitude-wise, everywhere, everything is same. Magnitude-wise, everything is same. It is just, you have to add Z square with every value. You have to add Z square with every value, right? This was 10.2. Here it's 10.2 Z square. Here it was minus 13.6 electron volts. And here is minus 13.6 Z square. So you have to add Z square everywhere. Perfect. I believe this is clear to every one of you. And my dear students, if I ask you one more thing, I've told you one important thing. When the electron makes a transition from lower energy state to higher energy state, lower to higher, what is going to happen to electron? Lower to higher, it's going to absorb energy. Imagine the electron has to go from 1 to 2, lower to higher. The electron has to absorb energy. How much? This much amount of energy electron has to absorb. And if the electron comes back from 2 to 1, the electron is going to emit energy. How much? This energy gap, same energy gap. This much amount of energy electron will emit now in the form of radiation, in the form of photon, which will be having some wavelength, some frequency, right? Clear, people? For example, the electron has to go from 1 to 3. The electron has to go from 1 to 3, lower to higher. Lower to higher. Energy is absorbed by the electron. How much energy is absorbed by the electron? Whatever is the energy gap between these two shells. Same amount of energy electron has to absorb, then only it will go from 1 to 3. Now, if the same electron is coming back from 3 to 1, higher to lower, it will emit energy. How much? The same amount of energy it will emit in the form of radiation, in the form of photon, which will be definitely having some wavelength, some frequency as well. Right? People, is every single thing clear till here? Is every single thing clear till here? Is every single thing clear till here? Let me teach you a few more things. Let me teach you a few more things, few more important things. Have you heard about something called as ionization energy? I believe yes. How do we define ionization energy here? Ionization energy, it is basically the energy required to remove the electron from the valence shell of the atom. The amount of energy which is required to remove the electron from the valence shell of the atom when the atom is present in isolated gaseous form. Leave that isolated gaseous form aside. You'll get that in periodic classification. But right now, I have to focus on one thing. I have to take the electron out from the valence shell of the atom. I have to take the electron out from the valence shell of the atom. What does that mean? What does that mean? I have to take electron out from the valence shell of the atom. That means we have to take the electron out. Where exactly we have to send the electron? We have to send the electron at a point where the electron won't be under the influence of the nucleus. That actually means the electron is out. Are you getting this part? The electron has to be removed from the valence shell of the atom, right? Electron has to be removed. That means the electron has to be out of the influence of the nucleus. When can the electron out of the influence of the nucleus? When we send the electron infinite energy state, right? When we send the electron to the infinite energy state, I believe you are understanding me properly, right? Now we will try to understand. Since if I talk about hydrogen atom, I'll make it clear with time. Just wait for it. If I talk about hydrogen atom contains just one electron, and that one electron will be present in the first shell. So if you ask me like this, you have got the hydrogen atom. It just has got one electron. It just has got one electron in it, right? That one electron is in its first shell. Now I have to take electron out from the atom. So I have to take electron out of the influence of the nucleus. That means I have to send the electron to what? Infinite energy state. I have to send the electron to infinite energy state, right? I have to send the electron to infinite energy state. When electron reaches infinity, it is not going to be under the influence of the nucleus then. That means the electron has been taken out from the atom. Okay? So my dear students, try to understand one thing. If I have to take the electron out from the influence of the nucleus, in case of hydrogen atom, that means the transition has to be from 1 to infinity. The electron has to go from 1 to infinity in case of hydrogen, right? If the electron has to go from 1 to infinity, imagine this is 1 and this is infinite energy state in case of hydrogen. In case of hydrogen, the electron was here. Now we have to send electron from here to here. That means, are we sending the electron from lower to higher? Yes, lower to higher. Whenever electron makes a transition from low energy state to higher energy state, it's going to absorb energy. Absolutely. How much? How much energy it has to absorb? The amount of energy absorbed is something which I call as ionization energy. The amount of energy absorbed, right, to make this transition from 1 to infinite. That's something which I call as ionization energy of hydrogen, which has to be, this was initial state, this final state. So final minus initial. So it's E infinity minus E1, right? So delta E, which is the energy gap between these two shells. This much amount of energy we are supplying. And the amount of energy which we are supplying to take the electron out, that's called as ionization energy, is equal to E infinity is 0 minus E1 is minus 13.6 Z square by N square. Z square by N square. Z for hydrogen is 1. N for hydrogen also is 1. So this is simply this much, which comes out to be 13.6 electron volts. So my dear students, if you particularly talk about electron in case of hydrogen, if you want to define the ionization energy of hydrogen, what does that mean? That means you have to take the electron out from shell number 1 and you have to send it to infinity. And in order to send the electron from 1 to infinity, this much amount of energy has to be absorbed by the electron in the form of photons. Right? In the form of photons. Perfect. Agreed? Aligned with this? Now understand one more thing. If you remember, energy of the electron in the first orbit of the hydrogen atom was minus 13.6 electron volts. This was the energy of the electron possessed, energy possessed by the electron in the first orbit of hydrogen. That was minus 13.6 electron volts. Ionization energy of the electron is 13.6 electron volts. Can you relate these two terms? Absolutely, you can relate these two terms. You can say ionization energy of hydrogen atom, right, is equal to minus times the energy of electron, or let me write it like this, minus times energy of first Bohr's orbit. First Bohr's orbit. In case of what? In case of hydrogen, right? Or in general, you can write it like this: ionization energy of hydrogen, it has to be equal to what? It has to be equal to minus times E1. Perfect. This is also one important statement. This is also one important statement. Similarly, guys, imagine you have got hydrogen-like atom. Imagine you have got hydrogen-like atom, right? Single electron species, whose atomic number is Z, right? Now, for example, it is a single electron species. There is only one electron. That one electron will be present in first shell. Now, imagine you have to take the electron out. That means, again, you have to make the transition from n is equal to 1, n is equal to infinity. Right? Perfect. So, imagine that this is n is equal to 1, and this is, for example, n is equal to infinity. This is your hydrogen-like atom whose atomic number is Z. The electron was present here. Now, you have to send it to infinity. You have to send it to infinity. The electron again has to go from lower to higher, lower to higher, lower to higher. Energy has to be absorbed. How much? Difference in the energy gap. Difference in the energy gap. So, energy gap is represented by delta E, which is going to be E infinite minus E1 here, right? And this energy gap I am supplying. So, the amount of energy supplied to take the electron out from the valence shell, that's ionization energy. So, E infinity is 0 minus E1 is minus 13.6 Z square divided by N square. N is 1 here, right? Perfect. So, I'll say ionization energy is equal. It is equal to plus 13.6 Z square. So, for hydrogen-like species, ionization energy is plus 13.6 Z square. For hydrogen-like species, ionization energy is 13.6 Z square. Matlab, this much amount of energy is required to take the electron out from the valence shell, right? Now, my dear students, if you remember, there was one thing. This was for hydrogen-like species. What is the energy possessed by the electron in the first shell of hydrogen-like species? That is minus 13.6 Z square. That is minus 13.6 Z square. What does that mean? What does that mean? That means ionization energy of hydrogen-like species. Ionization energy of hydrogen-like species is equal to minus times the energy possessed by the electron in the first orbit of what? Of the hydrogen-like species. So sometimes they'll directly give you the energy of the electron in the first orbit, and they'll ask you what is the ionization energy. You just have to reverse the sign. That's it. Nothing else. I believe it's clear to everyone. I believe this is clear to everyone. I believe all these things are clear to everyone. Okay? Right? For hydrogen, ionization energy for hydrogen or hydrogen-like is 13.6 Z square, electron volt per atom. Electron volt per atom. Or if you want to convert electron volt per atom into kilojoules per mole. So do remember, 1 electron volt per atom is going to be 96 kilojoules per mole. This you'll use in the problems while doing the conversion. Right? Rest everything is same. Rest everything is same. Now guys, there is something called as binding energy. These are very basic terminologies. There is something called as binding energy. How do we define the term binding energy? Binding energy is simply defined as the energy required to remove the electron from a given energy state. What was ionization energy? When you were defining the ionization energy, the electron was to be taken out from the valence shell. But here, electron, when you define the binding energy, electron can be taken out from any shell. From any shell. What does that mean? Have a look. Let's say this is the nucleus. These are some shells. These are some shells. And this is, for example, n is equal to infinity. This is equal to n is equal to infinity. For example, electrons. Some of the electron is present here, for example. Right? This is the electron here. Let's call this as N1. Let's call this as N2. Right? The amount of energy which is required to take the electron out from a given energy shell, from the given energy state. This is some random energy state from which I have to take the electron out. I have to take the electron out means, right now the electron is under the influence of the nucleus. I have to send this electron to infinity. Then only it will be out of the influence of the nucleus. Right? How much will energy, is energy going to be absorbed by the electron or emitted? Lower to higher. Lower to higher. Energy is absorbed. Right? How much energy is absorbed? Whatever is the energy gap between these two, same amount of energy electron has to absorb. Right? And whatever amount of energy is absorbed by the electron, right? Whatever amount of energy is absorbed by the electron, right? To be removed from a given energy state. That is something which you call as binding energy. That is something which you call as binding energy. It has to be the difference between the two. It has to be E infinite minus E n1. E infinite is 0. What is E n1? That is minus 13.6 z square divided by n1 square. Z square divided by n1 square. Right? So the resulting value comes out to be 13.6 z square divided by n1 square. What is this n1? n1 is the shell from which we are taking the electron out. n1 is the shell from which we are taking the electron out. Okay, so binding energy, it's always equal to minus 13.6 z square divided by n1 square. Now tell me one thing. Can binding energy and ionization energy be equal sometimes? Ionization energy was 13.6 z square. Binding energy is 13.6 z square divided by n1 square or n square, you can say. N is the shell number from which you are taking the electron out. Can ionization energy and binding energy be equal? Yes, they can be equal. When? They can be equal when n is equal to 1. When n is equal to 1. If n is equal to 1, binding energy and ionization energy, they'll be equal. Right? Binding energy can be equal to ionization energy when you are taking the electron out from n is equal to 1. Perfect? So do remember this particular thing as well. Similarly, there is something called as, you would have come across this particular term, excitation energy. Excitation energy. For example, you have to take the electron, you have to make the transition. Let's say electron has to make a transition from lower energy state to higher energy state. Let's say this is the energy state N1. This is the energy state N2. This is the lower energy state. This is the higher energy state. Right? The electron has to make a transition from lower energy state to higher energy state. Energy has to be absorbed. Whatever amount of energy is required to excite an electron, whatever amount of energy is required to excite an electron from lower energy state to higher energy state, that amount of energy absorbed is something which you call as excitation energy. So what is excitation energy? What is excitation energy? Excitation energy is the amount of energy which is required to excite the electron from lower energy state to higher energy state. Now, if you want to excite the electron from lower to higher, energy has to be absorbed by the electron. How much? Whatever is going to be the difference, whatever is going to be the energy gap between these two shells, same amount of energy you have to give to the electron, it will excite from N1 to N2, right? So how much is the energy gap? Final minus initial, it's going to be En2 minus En1. En2 minus En1. So excitation energy is basically the energy gap, which is this much, right? So I would say excitation energy result will be equal. This is minus 13.6 z square divided by n1 square minus. This is minus 13.6 z square divided by n2 square. Sorry, this was n2 square and this is going to be n1 square. Perfect. So from this particular result, you are going to get the result for calculation of excitation energy. It has to be 13.6 z square you are taking common. It's going to be 1 upon n1 square minus 1 upon n2 square, right? This is the formula by means of which you can calculate the excitation energy of the electron. The amount of energy which is required to excite the electron from low energy state to the higher energy state. Perfect, people? So I believe all these three results are absolutely clear to you. I believe all these three results are absolutely clear to you. Can you solve this question? Can you solve this question? Can you solve this question? The question says the radius of two Bohr's orbits of hydrogen atom. The radius of two Bohr's orbits of hydrogen atom. R1 divided by R2, right? It is equal to 4 divided by 9 for hydrogen. The energy difference between them may be. He's using the term may be. E1 by E2 you have to calculate, right? Since we are talking about two energy states of hydrogen. We are talking about two energy states of hydrogen. That means we have got one atom. So Z will get cancelled. So R1 is basically R0 n square by Z. It was supposed to be like this. R0 and 1 square divided by Z1. R2 was R0 and 2 square divided by Z2. It is equal to 4 divided by 9. But since the atom is same, it is just in the same atom, they are talking about two different shells, right? So Z1, Z2 is same. Hydrogen, R0, R0 cancelled. So N1 divided by N2 ka square is equal to 4 by 9, which has to be 2 divided by 3 basically, right? 2 divided by 3. So if N1 by N2 is 2 by 3, that means N1 is 2x, N2 is 3x. That means N1 is 2x and N2 is 3x. So N1, if x is equal to 1, that means 2, this will be 3. If x is equal to, for example, 2, this has to be 4, this has to be 6. If x is equal to 3, this has to be 6, this has to be 9, right? Perfect. Now we have to calculate the energy difference between them. That's why he's writing maybe, because you have no idea which of the pairs he's talking about, right? Maybe he's asking. The energy difference between them may be. Let's talk about this particular one. Let's talk about this particular one. Let's say electrons are present in 2 and 3, right? 2 and 3 of the hydrogen. In the second one, what is the energy? Minus 3.4 electron volts in case of hydrogen. In the third one, it's going to be minus 1.5 electron volts. Perfect. Minus 1.5 electron volts. Right, guys? So what do we have to calculate? The energy difference between them. Calculate the energy difference. Final minus initial. Final minus initial. How much this value will be? How much this value will be? Solve it. It's going to be 1.89, right? It's going to be 1.89. So A is the answer of the question. It may be this. It may be this. You can check the rest of the options as well. You can check the rest of the options for the other things as well. I believe you can solve these questions. Can you solve this one, guys? The energy of the electron in the first Bohr's orbit of hydrogen atom is 13.6. The possible values of energy of the excited state of electron in the Bohr's orbit of... Guys, this is something which you can solve, right? I believe you can solve this question as well. It's simple. I don't want to do this question. Look at this one. The ionization energy for hydrogen atom in the ground state is x kilojoules, right? The energy of the electron to jump from second to third orbit will be. Can you solve this one? Look at, these are basic questions. These are very basic questions. These are very basic questions. As per the question, the ionization energy of the hydrogen atom. The ionization energy of the hydrogen atom is how much? X kilojoules. If ionization energy of the hydrogen atom is x kilojoules, that means energy of the electron in the first orbit of hydrogen will be minus x kilojoules. That will be minus x kilojoules. Correct? That will be minus x kilojoules. What is energy formula? Minus 13.6 n square by z square. But guys, can't you solve this one? Is it required? Do you really want me to solve this question? I hope you got the idea. Can you solve this one? Same procedure it is. Say yes or no once in the chat. Quickly, everyone. So mark this also as the homework question. Because it's basic, guys. It's basic. Same concept I'll be using. You know, ionization energy is equal to minus times the energy of the electron in the first orbit. I'll be getting that, then second, then third, etc., etc. Easily you will calculate this one. The potential energy of the electron present in the ground state of B tripositive ion is. don't look at the option, right? By looking at the option, you might think this question is tough or something, but it's not tough, guys. It's easy. So let me show this one because maybe you'll get frightened after seeing the options. So we have got B dry positive, right? And he's asking about the ground state of B dry positive, the potential energy. Potential energy. Do you remember one of the results to calculate potential energy? It is equal to minus K Q1 Q2 divided by R, right? This potential energy formula you would have studied. For example, this is the nucleus of the atom whose atomic number is Z. So what is the charge present inside this nucleus, which is Q1? That will be Z times E. This is electron whose charge is here E, right? I'm just talking about the magnitude of the charges. Now guys, have a look. U is equal to minus K. Q1 is going to be ZE, Q2 is going to be E, so it is ZE square divided by R. Now this K, you know, it is 1 upon 4 pi epsilon naught. This is ZE square divided by R, right? Since he is talking about beryllium, hydrogen, helium, lithium, beryllium, or beryllium Z value is 4. 4 gets cancelled. So it is E square divided by pi epsilon naught R with the sign minus. Is there any option like that? Right? Do not get frightened with the options. These are very simple and basic questions, guys. These are very simple and basic questions. Look at this particular question. See what the question says. Radiation corresponding to transition from N is equal to 4 to N is equal to 2 in hydrogen falls on the metal of work function 2.5 electron volts. Maximum kinetic energy of the photoelectron. It's again a simple question only. Imagine you have got the hydrogen atom. This is N is equal to 4 for hydrogen. And imagine this is N is equal to 2 for hydrogen. The electron is moving from 4 to 2. The electron is making a transition from higher to lower energy state. Perfect. So it is going to emit energy. So first of all, tell me how much energy it will be emitting. How much energy it will be emitting. The difference between the two, the energy gap which you'll be getting from here. Let's first of all calculate energy possessed by the electron in the second Bohr's orbit. You know, E is nothing. E is just minus 13.6 Z square divided by N square. So it has to be minus 13.6. Z is 1. N ka square. So 2 ka square is 4. So it is minus 3.4 electron volts. So here it is minus 3.4 electron volts. Energy of the electron here, it's going to be minus 13.6 divided by N square. 4 ka square is 16. Which will come out to be minus 1.5 electron volt. Perfect. Now, calculate the energy gap. Energy gap is final minus initial. Initial is 1.5. So how much it will be? It will be, I think, minus 1.89 electron volts approximately. Right? How much is it going to be? Minus 1.89 electron volts. This minus signifies that energy is emitted by the electron when it's making a transition. So if I ask you how much energy is being emitted here, how much energy is being emitted by the electron? 1.89. Guys, you can see the calculation afterwards, right? The electron is going from 4 to 2. 4 to 2. Look at this particular diagram. The electron is going from 4 to 2. The electron is going from 4 to 2, right? The electron is going from 4 to 2. 4 to 2, right? Oh, sorry. This was E4 was minus 0.85. I have done a mistake. That was minus 0.85. I wrote minus 1.5. Sorry. That was, let me check it again. E4 is minus 0.85. Minus 0.85. So E4 was, sorry, this was minus 0.85 electron volts, right? All the calculation is wrong, right? Okay, so the electron was, first of all, N is equal to 4, from N is equal to 4 to N is equal to 2, right? The electron will be going from 4 to 2, so that means the electron will be emitting energy. How much energy electron will be emitting? Delta E, right? Final minus initial. Final is minus 3.4. Initial is minus 0.85, right? Now do the calculation. 3.40 minus 0.85. How much that is? 10 minus 5, 5. This is 5, so 2.55 electron volts. And the sign minus, so 2.55 electron volts. Correct? Now try to understand. This minus sign signifies that energy is emitted. How much energy is emitted? 2.55 electron volts of energy is emitted. Now, whatever energy is emitted by the electron while making the transition, that that amount of energy is falling on the metal. This much amount of energy, these 2.55 electron volts, it is falling on the metal, whose work function is given to us, whose work function is 2.5 electron volts, whose work function is 2.5 electron volts, right? So how much is the incident energy? Incident energy is 2.55 electron volts. How much is the work function? 2.5 electron volts. You know, incident energy is equal to work function plus kinetic energy maximum. So from here, you can easily calculate maximum kinetic energy, right? So maximum kinetic energy has to be equal. This is 2.55 minus 2.5, which comes out to be 0.05 electron volts. So this is the maximum kinetic energy with which the photoelectron will be moving in electron volts. But you do not have to calculate the answer in electron volts. You have to calculate it in joules. And you know, 1 electron volt is 1.6 into 10 raised power minus 19. As simple as that. So multiplying the last thing by 1.6 into 10 raised power minus 19, you'll be getting the answer in joules. Is every single thing clear? My dear students, this particular term spectrum, I'm sure all of you would have come across this particular term spectrum. Let's exactly get to know what the spectrum is all about and what all things we have to remember in this particular spectrum. My dear students, spectrum is defined as, the collection of radiations of different wavelength on a photographic plate. On a photographic plate. The collection of radiations of different wavelengths on a photographic plate. What is meant by it? How can we understand this particular term? Let's have a look, people. Let's have a look. For example, just to make you understand, let's say I'm taking a prism over here. Let's say this is the prism which I'm taking over here, right? My dear students, let's assume that I have got a white light. Which is incident on this prism. This is your white light, for example. This is the white light which is incident on the prism. Now, what this prism is exactly going to do? This prism is going to split this white light into 7 different colors. You know that? This prism is going to split the white light into 7 different colors. Perfect. 1, 2, 3, 4, 5, 6, and let's call this as 7. This prism is going to split the white light into 7 different colors. And I'm sure you all know what colors these are exactly, right? This is your, for example, violet, indigo, B, G, Y, O, and R. Perfect. This prism is going to split the white light into 7 different colors, right? Or I can say it like this. The prism is going to split this white light into 7 different wavelengths. These are 7 colors basically, and every color has got a particular wavelength over here. Red will have a particular wavelength, right? Orange will have a particular wavelength. Yellow will have the particular wavelength. Every color over here, every radiation over here has got a particular wavelength basically. Now, my dear students, imagine that I have kept a photographic plate over here. This is a photographic plate which is dark in color, right? It is dark basically. It's a photographic plate. Now, my dear students, what exactly you are going to see on the photographic plate? When the white light passes through the prism is going to split it into the 7 different colors, 7 different wavelengths, and over here on the prism, right here you will see a red spot. Right here you will see orange spot. You will see yellow spot here. Here you will see green spot. Here you will see blue spot. Here you will see indigo spot. And here you will see the violet spot, right? So can I say I got the radiations of different wavelengths on this photographic plate? Absolutely, I got the radiations of different wavelengths on this photographic plate. And my dear students, what is a spectrum basically? What is a spectrum? It is the collection of radiations of different wavelengths on a photographic plate. So over here, I had taken a photographic plate, and on the photographic plate, what did I get? I got the collection of radiations over here, which have got a different wavelength. And let me tell you, the collection of let me tell you, the collection of radiations of different wavelengths on the photographic plate. This collection is something which you call a spectrum. Or in simpler words, in very simple words, if I need to explain spectrum, if I need to define spectrum, spectrum is basically the image that is getting formed on the photographic plate, right? In simpler words, just to make you understand. Yeah, it is basically the image which is formed on the photographic plate when the radiations of different wavelength, they fall on this particular plate over here. I hope you got the idea of what the spectrum is. So what is the spectrum? It is the collection of radiations of different wavelengths on the photographic plate, or in simpler words, the image that gets formed on the photographic plate. That's it, right? My dear students, just tell me one thing. Will this photographic plate right now, will it look colored? Absolutely, this photographic plate will look colored to us, right? Because over here, there will be a red spot, orange spot, yellow spot will be here, green spot will be here. So this photographic plate, it will look colored to us basically. If you look at this photographic plate, it will look colored to you, right? Why? Because the radiations of different wavelengths have fallen on this photographic plate, right? And the image which has got formed on the photographic plate, that's something which you call a spectrum basically, okay? Now people, the spectrum which we are talking about, the spectrum, the collection of radiations of different wavelengths on the photographic plate, that's what you call a spectrum. Now people, this spectrum, we are going to classify into two types. The spectrum, I'm going to classify into two types. One is called as absorption spectrum. One is called as absorption spectrum, and another one is called as emission spectrum. Now, what this absorption and emission spectrum exactly is all about. Let's try to understand this in detailed format, right? First thing, my dear students, absorption spectrum, let me tell you, absorption spectrum, it corresponds to the absorption of light. It corresponds to the absorption. It corresponds to the absorption of a radiation, I'll say. Absorption of a radiation. And this particular emission spectrum which we are going to discuss, it corresponds to emission of radiation. It corresponds to emission of radiations. Now, what it means exactly? How can we understand this? Let's try to say exactly. See guys, for example, I have got a source of white light. Let's say I've got a source of white light, which is emitting basically white light. So in short, let's say this is the white light coming from here. This is the white light coming from here. This is the white light coming towards this particular direction. Now, my dear students, imagine that I have taken a container, and this particular container, imagine that it contains a solution over here. Imagine that it contains a solution over here. Perfect. Now, my dear students, what exactly is going to happen when this white light is going to pass through the solution, right? When white light is going to pass through the solution. After that, the white light which is coming out of the solution, I'm going to make it fall on the prism. I'm going to make it fall on the prism. So what exactly is going to happen? The white light which is coming out of the solution, right? When it will be incident on the prism is going to split this white light into different colors. And over here, what exactly I'm keeping? I'm keeping a photographic plate over here, which is basically dark right now, okay? Now, for example, I'm assuming one thing. Understand. Since this white light, it consists of 7 different wavelengths. Right? This white light, it consists of 7 different wavelengths. Correct? 7 different wavelengths. Now, let's assume that when this white light goes into the solution, let's assume that out of 7 different wavelengths, let's assume the solution absorbs 2 of the wavelengths. Let's assume that the solution which I've taken in the container, it absorbs 2 of the wavelengths. It absorbs 2 of the wavelengths. So first of all, how many wavelengths we had in the beginning? 7, right? V, I, B, G, Y, O, R, right? For example, I'm assuming this particular solution is absorbing your blue radiation and green radiation. Let's assume that. Let's assume this particular solution, it's absorbing blue and green. Perfect. Now imagine if there were 7 different wavelengths in the white light. Now the white light passes through the solution absorbs 2 of the wavelengths. Now, my dear students, the light which comes out of the solution, how many wavelengths it will contain? It will contain 5 wavelengths. It will contain 5 wavelengths basically, right? Now, this particular light which is coming out of the solution, which contains 5 wavelengths, I'm making this light incident on this particular prism. Now, what this prism is going to do? It is going to split this light into how many colors? It's going to split it into 5 colors now, because there are only 5 wavelengths. But what is exactly happening? Try to understand. So what exactly is going to happen? Let's say this is your, just a second. Okay. So this light which is going into the prism is going to split this light into different colors. One is going to be violet, V-I, B, G, Y, O, R. This is what prism was supposed to do. My dear students, this is your violet, right? When this particular radiation falls on the photographic plate, when this particular wavelength falls on the photographic plate, what you'll observe? You'll observe a violet spot over here. Similarly, this was supposed to be your indigo. When it falls on the photographic plate, you will get a indigo color over here, right? Over here, it was supposed to be blue. But blue is absorbed by the solution, right? So basically, blue was supposed to be here somewhere. But instead of blue, you will find a dark spot, because blue is already absorbed by the solution, right? So this is VIB. Now, this was supposed to be green. But green is already absorbed by the solution, right? So on the photographic plate, there'll be one more dark spot. It was supposed to be green spot here, but it's going to be dark because green is already absorbed with the solution. Perfect. So this is VIBG. This is Y, yellow. This is orange, and this is red. So basically, over here you'll find a yellow spot. Over here you'll find the orange spot. Over here you'll find the red spot. Perfect. If you look at the photographic plate over here, this is violet spot, indigo, dark spot, yellow, orange, red. My dear students, can I say on the photographic plate, I got dark spots on the colored background? Absolutely, I got dark spots on the colored background. So first point which you are going to remember over here, in case of your absorption spectrum, you get dark spots on the colored background. Now the point is, why do we get these dark spots on the colored background? That is your question. My dear students, what happened exactly when this white light goes into the solution, right? The solution absorbs 2 of the radiations. One is blue, one is green. The solution absorbs 2 of the wavelengths, blue and green. Now, my dear students, solution consists of atoms basically, right? And in the atoms, what do we have? We have got electrons. What is this blue and green basically? These are the radiations which will be having certain energy. So I must say the atoms in the solution, they are going to absorb these 2 energies. They are going to absorb the blue radiation, green radiation. They are going to absorb this blue wavelength, green wavelength, right? They are going to absorb these 2 energies over here. And my dear students, you know, when energy is absorbed by the atom, what happens? Electron moves from low energy state to higher energy state. So basically, these are the wavelengths which are basically absorbed by the electrons in the atoms of this particular solution. So these wavelengths are absorbed by the electrons in the atoms. And you know, when electron absorbs energy, what it does? It moves from low energy state to higher energy state. So can I say these two wavelengths are used for the excitation of electron? Yes. Can I say these two wavelengths are used for the excitation of electron? Perfect. So these two energies have been absorbed by the electrons in the atom. So what has happened? When the electron absorbs energy, it moves from low energy state to higher energy state. So these two wavelengths have been used for the excitation of electrons in the atoms. Right? That's the reason why you got dark spots over here. It was supposed to be blue and green, but it won't be blue and green here. These will be dark spots here. Perfect. So whenever you see such kind of the spectrum where you have dark spots on the colored background, this photographic plate, the image formed on the photographic plate right now, which consists of dark spots on the colored background, this is something which you call as the absorption spectrum. I hope you got the idea of what this absorption spectrum is all about. Now, let's talk about the emission spectrum. My dear students, emission spectrum, it corresponds to emission of radiations. Right? It corresponds to emission of radiations. Now, for example, let me write one statement over here. I'll say a source of light. Let me write it like this. A source emits the light. Which falls on the prism. Which falls on the prism, gets splitted into different wavelengths. What does this particular statement mean? Before talking about this particular thing, let me tell you, your source of radiation, it can be anything. It can be bulb. Your source of radiation can be bulb. It can be sun, right? It can be your excited atom. So the source of radiation, first of all, it can be your bulb, it can be sun, it can be excited atom. Now try to understand it like this. Let me erase this part. Try to understand like this. Let me make it very simple for you. My dear students, over here, if I talk about the atoms, can I say atom has absorbed blue and green, due to which what has happened? The electrons in the atom, they have got excited. Absolutely, they have got excited. Now you must be knowing electron in the higher energy state, it is considered to be very less stable. Electron in the higher energy state, it resides only there for 10 raised power minus 8 seconds. When the electron goes from lower energy state to the higher energy state, because of the absorption of energy, the electron in the higher energy state, it just resides there for 10 raised power minus 8 seconds. Because electron in the higher energy state, it's considered to be unstable. So what will happen? No doubt, the electron absorbed the wavelengths over here. It got excited. But in the excited state, electron is very unstable. So it is going to jump back. Now, my dear students, when the electron jumps back from the higher energy state to the lower energy state in the excited atom, when the electron makes a transition from high energy state to lower energy state, can I say it's going to emit the radiations? Right? It's going to emit the radiations. Now, my dear students, let me tell you, it is going to emit the same radiations which it had absorbed over here. So if I ask you now in case of emission spectrum on the photographic plate, will you see all the 7 wavelengths? Will you see 5 wavelengths? Or will you see just 2 wavelengths? You will just see 2 wavelengths. Which all wavelengths? The wavelengths which the atoms absorbed over here, right? One is going to be your blue, and one is going to be your green. Perfect. So over here, if you look, this is a blue colored spot. This is a green colored spot, for example. Can I say on the dark background we are seeing the colored lines, right? I can say in emission spectrum, what happens? What do we get? We get colored lines or we get colored spots. We get colored spots on the dark background. We get colored spots on the dark background. And my dear students, whenever you see this kind of the image, whenever you see this kind of the image on the photographic plate, wherein on the dark background you have got colored spots, this particular image, this particular spectrum, which corresponds to emission of light, this is something which you call as emission spectrum. This is something which you call as emission spectrum. Perfect. So first of all, what happened? This solution absorbed two of the wavelengths, right? By means of which electrons got excited. Electron in the excited state is considered to be unstable. It just resides there for only 10 raised power minus 8 seconds. So it jumps back from higher to lower. It's going to emit the same radiations which it had absorbed, right? And those two wavelengths I'm showing over here on the photographic plate. Yes? Perfect. So what did we observe on the photographic plate? We observed colored spots on the dark background. Whenever you see such kind of the image on the photographic plate, wherein you have colored spots on the dark background, this particular spectrum, this particular collection of radiations of different wavelengths, this is something which corresponds to emission spectrum. Right? Perfect. This is something which corresponds to emission spectrum. And my dear students, first absorption happened, right? Electrons got excited. Then the excited electron came back. It emitted radiation. First absorption took place. Then emission took place. That is the reason why you call absorption and emission spectrum as, that's why you call absorption and emission spectrum as photonegative of each other. You call them as photonegative of each other. You call them as photonegative of each other. I hope this particular scenario till here is clear to you. Let me know in the chats quickly. Let me know in the chats quickly, people. Every one of you. Every one of you. Absolutely. JEE students can also watch it. No issues. I hope you got the clear-cut idea of the absorption and emission spectrum, right? Which you would have come across many a times. Okay? Perfect, people. Say yes or no in the chats quickly. Everyone. Everyone. So in absorption spectrum, you get dark lines on the colored background. In emission spectrum, you get colored lines on the dark background. Now, this emission spectrum, we are further going to classify into two types. One is called as continuous spectrum. In case of continuous spectrum, you cannot differentiate the colors on the photographic plate like your rainbow. Like your rainbow. Can you differentiate all the 7 colors in the rainbow? No, you cannot differentiate. The colors are merged into each other. Let's say this is a photographic plate. The colors are merged into each other, right? You cannot differentiate the colors over here. Whenever you see this kind of the spectrum, whenever you see such kind of the emission spectrum, in which you cannot differentiate the colors, you call this particular spectrum as the continuous spectrum. You call this particular spectrum as the continuous spectrum. Second is discontinuous. In the discontinuous spectrum, the colors can be differentiated, right? That means on the photographic plate, in case of discontinuous spectrum, you can differentiate different colors. But in case of continuous spectrum, on the photographic plate, you cannot differentiate the different colors. They'll be merged into each other, right? Now, this discontinuous spectrum, it is further of two types. One is band spectra, one is the line spectra. In case of band spectra, what do you observe? You get a band of colors. For example, this is a red band from here to here. Let's assume. Let's say this is the red band from here to here. Let's say this is green band from here to here. You get band of colors in case of the band spectra. In case of line spectra, you get discrete lines. You get discrete colors over here. You get discrete colors over here on the photographic plate. Perfect. I believe all these things are absolutely clear to you. Now, people, if this general definition of spectra is clear to you, let's try to understand the actual stuff from which the questions are asked. And what do we call that as? We call that as hydrogen spectrum. But before that, do remember these two particular points. They can be asked. Do remember these. Yes, I'll be covering GOC as well. Just wait for that. Do remember, my dear students, band spectrum is formed by the molecules. Molecules are going to form the band spectrum. And line spectrum, it is formed by the atoms. And when it comes to your hydrogen, hydrogen shows emission, discontinuous, and line spectrum. Do remember these. They can be also asked, right? Now we are going to move into our actual topic. What is our actual topic basically? That is your hydrogen spectrum. Okay, that's your hydrogen spectrum. I want you guys to read these 3 lines over here. Let's see what they exactly say. The electron in the hydrogen atom, when gets excited to the higher energy levels, stays there for 10 raised power minus 8 seconds, falls back to the ground state, right? During which it emits radiation of different wavelengths, which are obtained as colored lines in the spectrum. Now, what it exactly means? Let's try to understand this a bit more in detailed format. Try to understand, people, what I'm going to say, because this is something which is very, very, very important. So first of all, I'm going to make you explain the hydrogen spectrum. From this hydrogen spectrum, a lot of questions are asked. A lot of different types of questions are asked, and you need to understand this properly. Have a look now. Let's say this is N is equal to 1 of hydrogen. Let's say this is N is equal to 1. This is the ground state of hydrogen. N is equal to 1, ground state of hydrogen. Let's assume over here, this is N is equal to 2 of hydrogen. Let's assume this is N is equal to 2 of hydrogen. Okay. Let's assume here you have got N is equal to 3 for hydrogen. N is equal to 3 for hydrogen. Similarly, my dear students, let's say this is N is equal to 4. This is N is equal to 4 for the hydrogen atom. Similarly, let's say you have got N is equal to 5. Let's say this is N is equal to 5 for hydrogen atom. N is equal to 5. Similarly, let's say this is N is equal to 6. Let's say this N is equal to 6 for hydrogen. N is equal to 6. And my dear students, as you all must be knowing, somewhere will be N is equal to infinity. Somewhere here, it's going to be N is equal to infinity. Perfect. Now try to understand what I'm going to say. N is equal to 1 is called as ground state of hydrogen. Ground state. N is equal to 2 is something which you call as first excited state of hydrogen. N is equal to 3 is called as second excited state of hydrogen. This will be third excited state of hydrogen, fourth excited state, fifth excited state, etc. etc. Right? Now, people, if I particularly talk about hydrogen atom, in the hydrogen atom, there is 1 electron. There is 1 electron. Let's assume that 1 electron was here. Assume that 1 electron was here. For example, this electron, it absorbed some energy. Let's assume that this electron, which is there in the N is equal to 1 of hydrogen, assume that it absorbs some energy. And you know, when electron absorbs energy, it goes into higher energy states. But in the higher energy states, electron is considered to be very less stable, right? It just resides there for 10 raised power minus 8 seconds. And my dear students, when the electron goes from low energy state to higher energy state, in higher energy states, it only resides for 10 raised power minus 8 seconds. Then the electron again jumps back. It again jumps back. And you know, when electron makes a transition from higher energy state to lower energy state, it is going to emit energy in the form of radiation. It is going to emit energy in the form of radiation. That radiation will be having a particular wavelength, right? That radiation will be having a particular wavelength. Now, my dear students, do remember one simple thing. Do remember, when the electron makes a transition, from higher energy states to shell number 1. When the electron makes a transition from higher energy states to shell number 1. When the electron makes a transition from higher energy states to shell number 1, we get a series of radiations over here. And this particular series of radiations which we get when electron makes a transition from higher to lower, this particular series of radiation you call as the Lyman series. And my dear students, let me tell you, whatever radiations we get in Lyman series, these radiations, they fall into ultraviolet region. Anyways, I'm going to talk about that more in detail in some time. So from now onwards, whenever I'll be talking about the Lyman series, in Lyman series, what do we get? We get a series of radiations when the electron makes a transition from higher energy states to shell number 1, right? Perfect. So if I ask you what is the ground state in case of Lyman series? In case of Lyman series, your ground state, which is represented by N1, your ground state is 1, right? And your higher energy states, which I'm representing with N2, it can be 2, it can be 3, it can be 4, it can be infinity. Perfect. So this series of lines we got over here, that's your Lyman series, number 1. Number 2, when the electron makes a transition from higher energy state to shell number 2, when the electron makes a transition from higher energy states to shell number 2, again we get series of radiations. And those series of radiations which we got when the electron makes a transition from higher energy state to shell number 2, you call this series of radiations as the Balmer series. In case of Balmer series, your ground state, in case of Balmer series, the electron finally reached back to shell number 2. So the lower energy state in case of Balmer series is 2, and the higher energy state in the Balmer series, it can be 3, it can be 4, it can be 5, dash, dash, right? Similarly, when the electron makes a transition from higher energy state to shell number 3, you get a series of radiations over here, right? Perfect. This particular series you call as Lyman-Balmer. This is what you call as Paschen series. And in case of Paschen series, the lower energy state is 3 and your higher energy state, it is 4, 5, it can be 6, it can be infinite, etc., etc. Okay. Let me tell you one more thing. As I told you in the beginning, whatever radiations we got in Lyman series, they fall in ultraviolet region. In case of Balmer series, whatever radiations we'll be getting, they'll fall into visible region. That means when these radiations fall on the photographic plate, you can see them. They fall into visible spectrum. You can see them, right? You can see them with your eyes. Ultraviolet we cannot see, right? Visible we can see. Perfect, right? And whatever series of lines, whatever series of radiations we got in Paschen, right? They fall in, this is ultraviolet, UV, this is infrared. They fall in infrared region. Similarly, there are few more series of lines which you have to remember. What are those? When the electron makes a transition from higher energy state to shell number 4, where you get a series of lines, you call them as, this was Lyman, Balmer, Paschen, this is called as bracket. This is something which you call as bracket series, in which the lower energy state is 4 and the higher energy state can be 5, it can be 6, it can be 7, etc., etc. And at the end, when the electron makes a transition from where to where? From higher energy state to shell number 5. Okay, you get a series of lines again, which you call as Pfund series. PFUND, Pfund series, right? And in case of Pfund series, the ground state, the lower energy state in case of Pfund series is 5, and the higher energy states will be, it can be 6, it can be 7, it can be 8, etc., etc. Similarly, when the electron makes a transition from higher energy state to shell number 6, like this. Again, you get a series of lines, and those series of lines you call as Humphrey series. You call that as Humphrey series. In case of Humphrey series, the lower energy state, which I'm representing the N1, that is 6, and higher energy state can be your 7, it can be 8, right, till infinity. Perfect. Now, this particular series falls in, all the radiations in Lyman series, they fall in ultraviolet, these fall in visible, these fall in infrared, right? Bracket also falls in infrared, Pfund also falls in infrared, Humphrey also falls in infrared. Do you remember all these things? Right? What I'm trying to say over here is this particular line. Just a second. Lyman series. In case of Lyman series, the lower energy state is 1. Higher energy state can be 2, 3, 4. And all the radiations which you get over here, when the electron makes a transition from higher to n is equal to 1, all these radiations, they fall in ultraviolet, right? Balmer series radiations, they fall in visible. Paschen series, infrared. Bracket series, infrared. Pfund series, you can call this also as infra, or you can say far infrared. Similarly, Humphrey series, you can also call this as far infrared, right? So do remember this particular scenario. Question has been asked once in your NEET examination from this particular table. The question was, in case of Balmer series falls in what? It falls in visible spectrum. This was once asked in your NEET examination. Balmer series falls in visible spectrum. Do remember this particular scenario. Now people, let's analyze this particular diagram more. Let's analyze this particular diagram more. There are few terminologies which I would want you guys to remember. What are those terminologies? My dear students, if you analyze the Lyman series, this particular line over here, this particular line, I will be calling this as this particular line over here. I'll be calling it either as H alpha line, H alpha, or I will be calling it as first line of Lyman series. I'll be calling it as first line of Lyman series, or you can call it as H alpha line. Similarly, this particular line from 2 to 1, this is something which I call as, this particular line is something which I call as second line of Lyman series, or you can call it as H beta line. You can call it as H beta line, right? Similarly, this particular line over here, this particular line in the Lyman series, you will be calling it as third line of Lyman. You'll be calling it as third line, or you'll be calling it as H gamma line. Similarly, fourth line, fifth line, etc., etc., right? Similarly, my dear students, if you look at the Balmer series, this line you'll be calling as, this particular line, you'll be calling it as first line of Balmer, second line of Balmer, third line of Balmer, fourth line of Balmer, first line of Paschen, second line of Paschen, third line of Paschen, fourth line of Paschen, first line of bracket, second line of bracket, third line of bracket, first line of Fund, second line of Fund, first line of Humphrey, similarly second line of Humphrey. First line is also called as H alpha line, second line is also called as H beta line. First line is called as H alpha, second line is called as H beta. Perfect. I hope till here every single thing is clear. Now, my dear students, there are some very important things which we have to discuss now. See, understand it like this. If I talk about Lyman series, electron can make a transition from 2 to 1. It can make a transition from 3 to 1, 4 to 1, 5 to 1. And you know, when the electron makes the transition from higher energy state to lower energy state, it emits energy in the form of radiation. That radiation will be having some frequency. That radiation will be having some wavelength, right? How do we calculate? How do we calculate the wavelength, the frequency, the wave number of the radiation which is emitted or absorbed, during the transition of the electrons? How do we do that? That's important, guys. For that purpose, what I'll be doing, I'll be introducing a result. I'll be introducing a formula which is called as a Rydberg's formula. I'm going to introduce a result over here. I'm going to introduce a formula over here, that is the Rydberg's formula. I'm not going to derive it. I'll just give this formula and show how it's to be applied in the questions. This Rydberg's formula, why it's used? Why am I going to give you this result? I'll say this formula is used to calculate wavelength, frequency, wave number of what? Of the radiation emitted by the electron when it makes a transition from higher energy state to lower energy state, or absorbed by the electron when it makes a transition from lower to higher, right? So for that particular purpose, I'm going to introduce the Rydberg formula. And Rydberg's formula says that your wave number, what is wave number? That is inverse of your wavelength, is equal to, this is R, Rydberg's constant, Z square. Z represents your atomic number of the atom, right? 1 upon N1 square minus 1 upon N2 square. Now you must be thinking what this N1 and N2 is all about. Let me tell you, N1, be careful with this. N1 always represents your lower energy state, and N2, it always represents your higher energy state. And my dear students, for calculation purpose, do remember 1 divided by Rydberg's constant, 1 by R value for calculation purpose will be always taken as 911.5 angstroms. Just to reduce the calculations, you are going to take the value of 1 by R as 911.5 angstroms. Right? Right, people? Now try to understand why I gave you this particular formula. In order to get the wavelength, in order to get the frequency, in order to get the wave number of the radiation which is emitted or absorbed during the transition, either from higher to lower or from lower to higher, right? Now, people, let's have a look exactly how this particular result is used. Let's first of all try to analyze your Lyman series. Let's first of all try to analyze your Lyman series. Let's try to analyze your Lyman series. In case of Lyman series, you already know electron makes a transition from a higher energy state to shell number 1. Now, my dear students, the first point in Lyman series, if I talk about the first line of Lyman, which is also called as H alpha line, just tell me one thing. In case of first line of Lyman, the transition will be from where to where? Just tell me that. First line of Lyman. First line of Lyman means the transition will be from 2 to 1. The transition will be from 2 to 1, right? Electron will move from 2 to 1 in the first line of Lyman. Now, which one is lower energy state? 1. I should be calling this as N1. Which one is higher energy state? 2. I should be calling this as N2. Now, we know when the electron makes a transition from higher to lower, it emits energy in the form of radiation. That radiation has got some wavelength. Let's calculate the wavelength of the radiation which is emitted. So I'll be using the Rydberg's formula. 1 divided by lambda is equal to R Z square. I'm talking about hydrogen. Z is 1. 1 upon N1 square minus 1 upon N2 square. This is 1 divided by lambda is equal to R. This is going to be 4 minus 1, 3. 3 divided by 4 exactly, right? Or you can take the reciprocal. So lambda is going to be 4 divided by 3 multiplied by 1 by R. And you all must be knowing 1 by R is nothing. That is 911.5, right? And this is going to be the wavelength of the radiation emitted during the first line in angstroms. Is it clear? Is it clear, people? I believe it's clear, right? I believe it's clear. If I talk about the second line of Lyman, you should be able to solve it again. If I talk about the second line of Lyman, second line of Lyman. In second line of Lyman, what exactly happens? In second line of Lyman series, the electron makes a transition from 3 to 1. Now, this is the lower energy state, N1. This is the higher energy state, N2. When the electron makes a transition from 3 to 1, again, it's going to emit radiation, which will be having some wavelength. Let's calculate the wavelength. 1 by lambda is equal to R. Z square, Z is 1. 1 upon N1 square minus 1 upon N2 square. So this is going to be simply 1 divided by lambda is equal to R. And it's going to be 8 divided by 9, right? Take the reciprocal. So lambda has to be 9 divided by 8 multiplied by 1 by R. And my dear students, this is 9 by 8. 1 by R value is 911.5 angstroms, right? Just solve it, get the answer exactly in angstroms, right? I believe it's clear. There is one more term here. What is that term? My dear students, in Lyman series only, I'm going to introduce one more term. That's called as series limit. In Lyman series. Series limit in Lyman. Series limit is also called as shortest wavelength. Sometimes they'll ask you directly, calculate the shortest wavelength in Lyman. Sometimes they'll ask you, calculate the series limit in Lyman. Both the things are same. Now, series limit or shortest wavelength in Lyman. First of all, you must be knowing now your delta E. Delta E is the energy gap between two shells, right? Energy gap between two shells. That is inversely proportional to lambda basically. Delta E is equal to hc by lambda, right? Delta E is equal to hc divided by lambda. Now your energy gap and lambda, they are directly or inversely proportional. What do I have to calculate? I have to calculate the shortest wavelength. For the wavelength to be shortest, energy gap between the shells should be maximum. For lambda to be minimum, for lambda to be shortest, delta E, it has to be maximum. Now tell me, in the Lyman series, what is the maximum energy gap? Should I take the transition from 2 to 1, 3 to 1, 4 to 1, 5 to 1, or infinity to 1? Tell me that. So in case of the series limit in Lyman series, I will have to take the transition from infinity to 1. Then only the energy gap will be maximum. And when the energy gap is maximum, that means your wavelength emitted will be minimum. That minimum wavelength, shortest wavelength is what you call a series limit. As simple as that, right? Now, this is your lower energy state. This is your higher energy state. And you know when the electron makes a transition from higher to lower, it's going to emit radiation, which has got some wavelength. So 1 divided by lambda is equal to R. Z is 1 for hydrogen, 1 upon N1 square minus 1 upon N2 square, right? So it's going to be 1 divided by R is equal, 1 divided by lambda is equal to R. 1 by infinity is 0 basically, right? So take the reciprocal, lambda will be 1 divided by R. 1 by R, you already know that's 911.5 angstroms. So this is the minimum wavelength which will be emitted in case of Lyman series, right? This is the minimum wavelength. This wavelength in case of Lyman series is also called as series limit of Lyman. Series limit of Lyman, right? I believe you can easily solve all these things from now onwards. Yes? Similarly, guys, let's say you have got the Balmer series. Can you calculate all these things for the Balmer series again? You should be able to. Can't you calculate all these things for the Balmer series again? My dear students, you should be able to. First, what is that? I'm talking about H alpha line of Balmer. H alpha line means first line of Balmer. H alpha line means first line of Balmer. First line of Balmer, right? First line of Balmer. In case of Balmer series, electron makes a transition from higher energy states to shell number 2, right? Now, I'm asking about first line of Balmer. First line of Balmer means the electron is making a transition from 3 to 2. This is the lower energy state. This is the higher energy state, right? So the electron is making a transition from 3 to 2. It's going to emit radiation, which will be having some wavelength. So 1 by lambda is equal to R. Z square, that's 1 square. 1 upon N1 square, 2 ka square is 4, minus 3 ka square is 9. So 1 divided by lambda is equal to R. 9 minus 4 is 5, divided by 36. Take the reciprocal, lambda is equal to 36 divided by 5, multiplied by 1 by R, that's 911.5. And this value is going to be in angstroms. Done and dusted? Done and dusted? Now, if I ask you about the series limit, in Balmer, or I'll be calling this as shortest wavelength, lambda minimum, right? I'll be calling it as lambda minimum. This was your lambda minimum, by the way, right? This was your lambda minimum. This was your lambda minimum in Lyman. Now, lambda minimum in Balmer. For the wavelength to be minimum, energy gap has to be maximum. In Balmer series, when do you see the maximum? In which transition you see the maximum energy gap? In which transition you see the maximum energy gap? In Balmer, it's going to be again infinity to 2. This is your N1 value. This is your N2 value. Now, 1 divided by lambda minimum in Balmer is going to be R. Z square is 1. 1 upon N1 square minus 1 upon infinity ka square, right? So 1 divided by lambda minimum is equal to R, and it's just going to be 1 by 4 because 1 by infinity is 0. So lambda minimum in case of Balmer is going to be 4 multiplied by 1 by R, that is 911.5, and the answer is going to be angstroms. So this is the series limit in case of Balmer series. This is the series limit of the Balmer. This is the series limit of the Balmer, right? This is the series limit of the Balmer. I believe it's clear. I believe it's clear. Right, people? I believe it's clear. Okay, tell me one more thing. If I talk about Lyman series again, since I told you in case of Lyman series, I showed you how to calculate lambda minimum. If I ask you, calculate lambda maximum in Lyman series. Calculate lambda maximum in Lyman series. For lambda to be maximum, delta E has to be minimum. For lambda to be maximum, delta E has to be minimum. Now in Lyman series, delta E has to be minimum. Look at the Lyman series. Where do you see the delta E minimum? Delta E minimum in Lyman series is when the transition is from 2 to 1. So transition from 2 to 1 basically. I have to consider transition from 2 to 1. And here I have considered the transition from 2 to 1. So should I be calling this wavelength as minimum or maximum? This wavelength is going to be the maximum wavelength, right? It's going to be the maximum wavelength. It's going to be the maximum wavelength, lambda maximum in Lyman, right? Similarly, if I ask you lambda maximum in Balmer, just tell me the transition. Lambda maximum in Balmer. Energy gap has to be minimum in Balmer. When is the energy gap minimum in Balmer? When the electron makes a transition from 3 to 2. And that 3 to 2 we have already analyzed here. So this is lambda maximum in Balmer. Right? This is lambda maximum in Balmer. Perfect. Clear, guys? So I hope these sort of questions you can easily solve from now onwards. Perfect. Look at the first question. Can you solve this? Can you solve this question? Calculate the wavelength of H alpha line of Balmer series. We have done this question. We have calculated this wavelength. Series limit in Lyman series. We have solved this question. We have solved this question too. The third one, H beta line of Paschen. H beta line of Paschen. Lyman, Balmer, Paschen. So N1 has to be 3, right? First line will be 4 to 3. First line will be 4 to 3. Second line will be 5 to 3. Second line is called as H beta line. H beta line. So the transition has to be from 5 to 3. Now we can use the formula, get the answer, 1 by lambda, right? Perfect. So these sort of questions you should be able to solve easily from now on. Look at this one. Look at this particular question. Look at this particular question. What transition in hydrogen spectrum? What transition in hydrogen spectrum would have the same wavelength as the Balmer transition? As the Balmer transition. As the Balmer transition. N is equal to 4 to N is equal to 2 of He positive spectrum. What exactly it means? Try to understand. For example, this is the hydrogen atom. This is your He positive ion. One is hydrogen, one is He positive. Perfect. In case of He positive, you know the atomic number. You know the atomic number. First of all, hydrogen atomic number is 1, right? And helium atomic number, you already know, that's 2. Perfect. In case of helium, the electron makes a transition from 4 to 2. The electron makes a transition from 4 to 2. Perfect. When the electron will be making a transition from 4 to 2, it's going to emit some wavelength. It's going to emit some wavelength, right? Which I call as lambda over here. Perfect. Now, as per the question, what should be the transition in case of hydrogen? What should be the transition in case of hydrogen? Such that the electron is going to emit the same wavelength as was emitted by He positive. That's the question. Perfect. What I'll be doing exactly? I'll be using Rydberg's formula for this hydrogen as well as for this one, for this He positive. It's going to be 1 divided by lambda is equal to R, Z square, 1 square, 1 upon N1 square, minus 1 upon N2 square. Now, my dear students, I'm calling this as equation number 1. I'm calling this equation number 1. Use the Rydberg's formula for this particular transition as well. So it's 1 divided by lambda is equal to R, Z square. So 2 ka square is 4. 1 upon N1 square. N1 square minus 1 upon N2 square. N2 square. So this you can write like this. 1 by lambda is equal to R, right? This is going to be 4 cancel. So 1 by 1. Or you can write 1 by 1 ka square minus 4. This 4 ones are 4 fours are. So this is 1 by 4, which can be written as 1 by 2 ka square. My dear students, if you compare both these two equations, what you will analyze here? Compare both these equations. What you are going to understand? See, lambda emitted here as well as lambda emitted here. That should be the same. So LHS side in both the equations is same. If LHS side in both the equations is same, that means RHS side in both the equations should be same too, right? So on comparing these two equations, look at this N1. Look at this N1. So you got to know your N1 is basically 1 in hydrogen and your N2 over here, N2 has to be 2. N2 has to be 2. So in case of hydrogen atom, the transition should be from 2 to 1. The transition should be from 2 to 1. Then the electron is going to emit the same wavelength as was emitted by He positive when the electron made a transition from 4 to 2. I believe it's clear to everyone. Yes? Say yes or no in the chats. Say yes or no in the chats quickly. Calculation of maximum spectral lines. Calculation of maximum spectral lines when the electron makes a transition. Calculation of maximum spectral lines. And this particular result which I'm going to give you, it's for large number of atoms. It is for large number of atoms. Try to understand what exactly I'm going to talk about. For example, guys, just to make you understand, let's say this n is equal to 1. Let's say this n is equal to 2. Let's say this n is equal to 3, right? This n is equal to 3. For example, the electron is present in n is equal to 3. N is equal to 3. And it has to come to 1 exactly. So the transition, for example, is from 3 to 1. The electron has to come from 3 to 1. The electron has to come from 3 to 1. If I ask you how many possible ways are there by means of which electron can come from 3 to 1. See, first way, electron can directly come from 3 to 1, right? So the transition can be 3 to 1 directly. And when the electron makes a transition from 3 to 1, it's going to emit a radiation, right? That radiation I'm represented by a line, by a spectral line. Perfect. Are there other ways too? Yes, there are other ways too. Electron will first come from 3 to 2. When the electron comes from 3 to 2, one spectral line emitted. Then from 2 to 1, then from 2 to 1, one more spectral line emitted. So how many total spectral lines are emitted when the electron makes a transition from 3 to 1? How many total spectral lines emitted when the electron makes a transition from 3 to 1? 3 spectral lines in total are emitted. 3 spectral lines in total are emitted, right? But you're not going to use this approach always. Like one by one, you will check all the possibilities. I'll directly give you one result which you are going to remember from now on, people. What is that result? Have a look. Calculation of maximum spectral lines. Maximum spectral lines. It is N2 minus N1. N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. This is how you are going to calculate the maximum spectral lines emitted when the electron makes a transition from higher energy state to lower energy state. For example, imagine that the electron is making a transition from 6 to 1. 6 to 1. So this is your higher energy state N2. This is your lower energy state N1. So if I ask you how many spectral lines, number of spectral lines emitted right now, number of spectral lines observed right now is equal to N2 minus N1. 6 minus 1, that's 5. N2 minus N1, that's 5. N2 minus N1, that's 5. 5 plus 1, 6 divided by 2. So how many? 15 maximum spectral lines will be observed. You'll observe 15 maximum spectral lines. Now, my dear students, if I ask you out of these 15 spectral lines, out of these 15 radiations which are emitted, how many spectral lines will fall in Lyman? How many spectral lines will fall in Balmer? How many spectral lines will fall in Paschen? Right? If I ask you something like that, do remember number of spectral lines. Number of spectral lines falling into a particular region, falling into a particular series, I'll say, falling into a particular series is always equal to higher energy state minus ground state of that particular series which you are talking about. What does that mean? Electron right now is making a transition from 6 to 1. So how many spectral lines are observed? 15. 15 spectral lines are emitted. 15 radiations are emitted, which have got different wavelengths, right? Out of these 15 radiations, how many radiations will fall in Lyman if I ask you? How many radiations will fall into Lyman? What you'll say? Number of spectral lines which fall into Lyman category. It has to be equal to. It has to be equal to N2. That is the higher energy state, which right now is 6, minus ground state of Lyman. Ground state of Lyman is 1. So out of 15 spectral lines, there'll be 5 spectral lines which will fall into the category of Lyman. Similarly, how many will fall into the category of Balmer? Higher energy state minus ground state of Balmer is 2, right? How many spectral lines out of the 15 spectral lines? How many will fall into Paschen? Higher energy state minus ground state of Paschen, 3, right? Lyman, Balmer, Paschen. Then comes your bracket. Then comes your bracket. It's going to be higher energy state minus ground state of bracket. That's 4. That's 2. Similarly, fund. Fund will be 1. There'll be 1 spectral line which you'll observe in the fund series as well. Now, if you add them up, 5 plus 4 plus 3 plus 2 plus 1, 5, 4, 9, 9, 3, 12, 12, 2, 14, 14 plus 1, 15. So in total, how many spectral lines are observed? In total, 15 spectral lines are observed, out of which 5 will fall in Lyman, 4 will fall in Balmer, 3 will fall in Paschen, 2 will fall in bracket, and 1 will fall into the fund. Right, people? This particular question can be asked too. Do remember. Do remember, people. Do remember. Do remember. Look at this particular question. Try to solve this. Try to solve this. Hydrogen atom in ground state is excited by monochromatic radiation of wavelength lambda. Right? Hydrogen atom in ground state. Hydrogen atom is in ground state. Okay. See, this is the ground state of hydrogen. This is the ground state of hydrogen. Hydrogen is present in the ground state. It is excited by a monochromatic light. A monochromatic light is falling on this electron, right? Whose wavelength is lambda. Perfect. When this monochromatic light falls on this electron, the electron excites. It goes to higher energy state. It goes to N2. The electron reaches N2, for example. Electron reaches N2. Perfect. On coming back to the ground state. Now, since you know when the electron makes a transition to higher energy state, at higher energy state, electron is very unstable. So it jumps back. Now the electron is jumping back. And when the electron is jumping back, how many different spectral lines are observed? 15 spectral lines are observed. Calculate lambda. We have to calculate this lambda, which was absorbed by the electron. How exactly you're going to do it? See guys, maximum number of spectral lines obtained are 15, right? These are the maximum spectral lines obtained. Perfect. Maximum spectral lines obtained, 15. Now people, maximum spectral lines obtained is N2 minus N1. N1 is 1. N2 minus N1. This is N2 minus N1. This is N2 minus N1 plus 1 divided by 2. Correct? So this one got cancelled. 15 to 30. So 30 is equal to N2 ka square minus N2. So you are getting a quadratic here. N2 square minus N2 minus 30 is equal to 0. You got a quadratic equation. You got one quadratic equation. I hope all of you know how to solve a quadratic equation. I hope you know that, right? So when you solve this quadratic equation, you'll be getting two values of N2. One you'll be getting 6, one you'll be getting minus 5. Minus 5 cannot be the value. It has to be 6. That means the electron has gone from 1 to 6. The electron has gone from 1 to 6. And now the electron is coming back from 6 to 1. Now the electron is coming back from 6 to 1. What we have to calculate? We have to calculate the wavelength. Whatever wavelength electron had absorbed in the beginning, so that it could go from 1 to 6. When it jumps back from 6 to 1, it's going to emit the same wavelength. It is going to emit the same wavelength, right? So I'm going to assume that the transition is from 6 to 1. Perfect. The transition is from 6 to 1. So calculate the wavelength emitted. 1 by lambda is equal to R. Hydrogen, Z is 1. 1 upon N1 square minus 1 upon N2 square. Perfect. So 1 divided by lambda is equal to R. This is going to be 35 divided by 36. So take the reciprocal. So lambda emitted is equal to 36 divided by 35 multiplied by 1 by R is 911.5, and the answer is going to be angstroms. So this much wavelength is emitted by the electron when it makes a transition from 6 to 1. That means same wavelength it would have absorbed too when it would have made the transition from 1 to 6. Simple? Simple, people? Right? I believe this sort of a question you can easily solve from now on. Okay. Look at this. What this question says. Electron in the hydrogen atom jumps from some higher level up to third energy level. Electron jumps from higher level to third energy level. The electron jumps from higher level to third energy level, right? How many spectral lines are observed? If 6 spectral lines are possible for the transition, find the initial position of electron. See, electron is right now at N2. Perfect. It is the initial position. Now the electron has to jump to 3. How many spectral lines? How many spectral lines are possible? 6. Find the initial position. We have to get the value of N2. It's again simple. So how many maximum spectral lines? 6 is equal to N2 minus N1. This is N2 minus N1 plus 1 divided by 2. Solve this equation, get the value of N2. That was the initial position of the electron. You can easily solve it. Nothing to look at this. Okay. Look at this particular equation. In hydrogen atom, electron makes a transition. In hydrogen atom, electron makes a transition. Okay, from where to where? From fourth excited state. Guys, be careful with the terminologies. From fourth excited state. Fourth excited state. Fourth excited state is n is equal to 5. N is equal to 5. Up to second state. Up to second state. So the transition is from 5 to 2. The transition is from 5 to 2. Okay, the transition is from 5 to 2. So this is your N1 and this is your N2. Then 10 different spectral lines are observed. 6 different number of lines belonging to Balmer, number of lines belonging to Paschen. Okay. So first of all, let's calculate the total number of spectral lines. Total number of spectral lines will be equal to N2 minus N1. This is going to be N2 minus N1 plus 1 divided by 2. This value is going to be 3. This value is going to be 3 plus 1. 4 divided by 2. 4, 3, 12 divided by 2. 6. So in total, 6 spectral lines. 6 different spectral lines are observed, right? Now, out of 6, how many will fall into Balmer? How many will fall into Balmer? So, number of spectral lines which will fall into Balmer. How do we calculate that? It is equal to higher energy state minus ground state of Balmer. What is the higher energy state? Higher energy state here is 5 minus ground state of Balmer, Lyman-Balmer, it's 2. So, 5 minus 2 is 3. So, 3 spectral lines will belong to Balmer. 3 spectral lines will belong to Balmer. Similarly, how many spectral lines will belong to Paschen? Higher energy state minus ground state of Paschen, Lyman-Balmer Paschen. So 5 minus 3, 2. Number of lines belonging to Paschen, that's 2. So B, C as well as D. That's correct. That is correct. Let me know once in the chats if all the things are clear till here. Quickly. Quickly, guys. Quickly, people. Again, one simple question. I believe you can easily solve this question, right? Correct? From spectrum, this is your homework question, right? And you are going to let me know its answer in the comment section of the video at the end, in the comment section. Perfect, guys? Is it clear? All the things are clear till here? So this was your detailed hydrogen spectrum. I believe if any question is asked from hydrogen spectrum, you should be able to solve that question on your own. You should be able to solve that question. Will you be? Can you solve the question? Are you sure about that? Guys, say yes or no in the chats quickly. We don't have much of a time here. Quickly, everyone. Zainab, you just increase your settings. I think there is something wrong in your settings of this video. Say quickly in the chats if it is clear to everyone, guys. GOC will be also done, I've told you. Next week, Monday, you'll have GOC session. I'm asking, is it clear to everyone? Everything is sorted? Say yes or no in the chats quickly. I think you don't want to continue with this session, yeah? Should I end the stream then? I think you've studied atomic structure. So there is one topic, this is one more important topic, that is de Broglie's hypothesis. Let's exactly get to know. what this de Broglie's hypothesis is all about. Let's exactly get to know what this de Broglie's hypothesis exactly is all about. My dear students, this de Broglie's hypothesis, what does it explain first of all? It explains the dual nature of matter. It explains the dual nature of matter. See, first of all, if I talk about light, you already know light has got duality. Light has got duality. Light has got dual nature. What is meant by that? What is meant by that? See, just to make you understand, if you know, light, it shows certain phenomenon. It shows certain phenomenon. For example, reflection, for example, refraction, for example, diffraction. There are many phenomena shown by the light. There are many phenomena shown by the light. Now, some of the phenomena of light are explained by considering light to have particle nature, and some of the phenomena of the light are explained by considering light to have the wave nature. So there are many phenomena shown by light, out of which some of the phenomena are explained by considering the light to have wave nature, and some of the phenomena are explained by considering light to have the particle nature, right? So in short, I can say light has got duality basically, right? Light has got dual nature, particle nature as well as wave nature, particle nature as well as wave nature, right? What Heisenberg said? Heisenberg said it is not only about the light. Whatever exists in the universe, every single thing shows the duality. Whatever matter we have, be it electron, be it proton, be it photon, whatever matter we have around us, every single thing has got the duality. Every single thing shows particle nature as well as wave nature. This is the hypothesis as per de Broglie is concerned. This is the hypothesis as per de Broglie is concerned. De Broglie said whatever matter is there in the universe, every single thing, be it electron, be it proton, be it photon also, right? Every single thing has got duality. Every single thing has got particle nature as well as wave nature, right? Let me make it a little more simple for you. What de Broglie exactly said. Let's say this is the particle. This is the object, for example. This is a small object whose mass is m. Let's assume that this small object is moving with velocity v. This small object is moving with velocity v. If this object has mass m, velocity v, so this object carries some momentum p, which is equal to m into v. This object, it carries linear momentum, right? It carries linear momentum. Perfect. Now, my dear students, what this de Broglie said, whenever you have got an object having certain mass moving with certain velocity, right? Moving with certain velocity, apart from its particle nature, there will be a wave associated with this particular object. There will be a wave associated with this particular object. And the wave which is associated with the object, you either call it as a matter wave, or you call it simply as de Broglie's wave. You simply call it as de Broglie's wave. For example, this is the marker, for example, right? This marker has got some mass, it has got some velocity. This marker has got some mass. It is moving with some velocity. It is moving with some velocity, right? So it has got mass, it has got velocity. It has got linear momentum. Linear momentum is the characteristic of a particle. Linear momentum is the characteristic of a particle, right? Now, as per de Broglie, if this marker is moving, with the marker, there will be a wave associated with it. And that wave is something which he called as de Broglie's wave. That wave is something which he called as de Broglie's wave. Perfect. That wave is something which he called as de Broglie's wave. Right? That wave is something which he called as de Broglie's wave. Now, the point is very simple. If there is a wave associated with every particle, that means this wave will have got certain wavelength, and that wavelength associated with the de Broglie's wave, that is represented by lambda. And as per de Broglie's concerned, wavelength of the de Broglie's wave, which is associated with the object moving with some velocity, it is inversely proportional to the linear momentum carried by the object. It is inversely proportional to the linear momentum carried with the object, right? It is inversely proportional to the linear momentum carried with the object. What is lambda here? It is this is something which you call as de Broglie's wavelength. This is something which you call as de Broglie's wavelength, right? De Broglie's wavelength of the de Broglie's wave, which is associated with the particle which is moving with some velocity v. What is p? What is p? P is something which we call as linear momentum. P represents linear momentum of the object which was moving, right? So he related both the things. This lambda, it is the characteristic of wave. This linear momentum, it is the characteristic of particle. So he related both the things. He related both the things for the object, right? He told your de Broglie's wavelength, that's inversely proportional to the linear momentum. Now guys, have a look. If I remove the proportionality sign, you're going to get the constant h divided by p. H divided by p. This is one of the equation which you are going to remember from now onwards, right? Similarly, what is p basically? P is the product of mass and velocity. P is the product of mass and velocity. So this one more result to calculate de Broglie's wavelength of an object, right? Perfect. Now, my dear students, let's try to understand one more thing. See, if I talk about this particular object, right? It has got mass, it has got velocity. Perfect, it's moving. There is a de Broglie's wave associated with it. Okay. One more thing. If it has got mass, if it has got velocity, it will be having some kinetic energy as well. And kinetic energy of that particular object is simply half of mv square, right? Half of mv square. If I just do one thing, if I multiply and divide with mass, so this becomes m square in the numerator, in the denominator it will be m. So can I say kinetic energy is equal? This is m multiplied by v ka whole square divided by 2m. Perfect. So it's going to be 2m multiplied by kinetic energy is equal to m multiplied by v is momentum. So this p ka square. So p from here comes out to be under root of 2m multiplied by kinetic energy, right? So in this particular expression, you can say lambda is equal to h upon under root of 2m multiplied by kinetic energy associated with the object which is moving with velocity v. So this is one more result to calculate de Broglie's wavelength in terms of kinetic energy, right? De Broglie's wavelength in terms of momentum, de Broglie's wavelength in terms of kinetic energy. Are there some other results too to calculate de Broglie's wavelength? One more thing, guys, which I forgot to tell you. This de Broglie's wavelength, de Broglie's hypothesis. If I particularly talk about de Broglie's hypothesis, it gives satisfactory results for your microscopic particles. What does that mean? See, I am the macroscopic object, right? I'm the macroscopic object. I've got some mass. I'm moving with certain velocity. I've got some mass. I'm moving with certain velocity. Definitely, there will be a wave associated with me, but the wavelength of that wave will be negligible. That will be negligible. That's why this particular concept, we relate this particular concept normally with the microscopic particle, right? We relate it with the microscopic particles particularly. Okay, why is that? The reason is pretty much simple. I am the macroscopic object. I have got some mass. I'm moving with some certain velocity v. That means there will be a de Broglie's wave associated with me. Absolutely. But the wavelength of that particular wave will be negligible. So you're not going to consider it. Right? Perfect. All right. So till now, what did we calculate? We calculated the de Broglie's wavelength in terms of momentum. We calculated the de Broglie's wavelength in terms of kinetic energy. Now, is there any other result by means of which we can calculate de Broglie's wavelength? Absolutely, there is one more result. Let's have a look exactly what that result is. My dear students, try to understand one simple thing. Imagine that you have got a charged particle. If a charged particle is accelerated, at a potential difference of V volts, as per your work energy theorem, as per your work energy theorem, change in the kinetic energy will be equal to work done by the battery, I'll say, by the source, I'll say. By the source, I'll say. What does it mean exactly? Try to understand what it exactly means. For example, guys, this is a plate. This is one more plate. I'm connecting these two plates with an external battery. Right? With an external battery. Perfect. This plate is connected with the positive terminal, so it carries the positive. This carries the negative. Perfect. Now imagine I've got a charged particle Q. I've got a charged particle over here. Right? I've got a charged particle whose charge is plus Q. Right? Let's assume the battery is turned on right now. I mean, turned on means, sorry. Let's assume that the battery is not connected right now. If the battery is not connected, there are no charges on these plates, and this charged particle is at rest. This charged particle, imagine the battery is not connected right now. The charged particle is at rest, so its initial kinetic energy will be zero. Now, when you turn the battery on, this negatively charged plate is going to attract this positively charged towards itself, right? Initially, the kinetic energy of the particle of the charged particle was zero. Now, since when you turn the battery on, this battery, the negative plate of the battery, it started attracting it towards itself, due to which it attains the kinetic energy, right? It attains the kinetic energy. Now, as per your work energy theorem, change in the kinetic energy of the particle is equal to the work done by the battery. Let's assume the voltage of the battery was V. Change in the kinetic energy is going to be final kinetic energy. Final kinetic energy minus initial. Initial is zero. Is equal to work done by the source. Which is equal to charge multiplied by potential difference. So, if a charged particle is accelerated under certain potential difference, do remember, change in kinetic energy as per work energy theorem has to be equal to maximum work done. So, Ke is equal to Q multiplied by V. That means we are going to get one more result. And the result is lambda, de Broglie's wavelength, is equal to H upon, it was under root of 2m multiplied by kinetic energy. Instead of that, you will write charge on the particle multiplied by voltage at which it is being accelerated. Guys, it's simple. If you will be having a charged particle, if it's accelerated, if the charged particle is moving, definitely there will be a wave associated with it. That wave will be having certain wavelength. How do we calculate that wavelength? Like this, right? Particularly if I talk about electron. For electron, if the electron is accelerated at some potential difference, under some potential difference, at that point, de Broglie's wavelength associated with the electron will be equal to H is constant, mass of electron you know, charge on electron you know, right? It will be equal to 12.27 divided by under root of V, where V is the potential difference at which the electron is accelerated, and this value will be in angstroms. This result is particularly for the electron. Similarly, you can calculate for alpha particle, you can calculate for proton, right? But mainly we'll use this particular result here. Okay, I believe it's clear to everyone. Now people, as I told you, this de Broglie's hypothesis, it suggests that whatever matter is around us, everything has got duality, has got wave nature as well as particle nature. When a particle having certain mass moves with certain velocity, that means it has got some momentum. When this particle moves, right, with the particle, there will be a wave associated with it, right? That wave is something which you call a de Broglie's wave, whose wavelength is lambda. He gave the relation between lambda and P. Lambda is inversely proportional to P, right? Lambda is inversely proportional to P. Perfect. Lambda is inversely proportional to P. And we got all the results by means of which we can calculate the de Broglie's wavelength of a de Broglie's wave which is associated with some object. Right? Okay. Now guys, the wave nature of the matter, was basically, it was explained by this Davison-Germer experiment. There's the experiment which you will study in your class 12 physics, I believe, right? Through that particular experiment, it was believed that matter has got wave nature, right? How exactly? How exactly? Let me show it. Just a glimpse of it. I'm not going to teach this in detail, just for an idea I'll give you. See guys, if you particularly talk about light, light shows a phenomenon that's called as diffraction. That's called as diffraction. That's called as diffraction. Light shows a phenomenon that's called as diffraction, and diffraction is explained by considering light to have the wave nature. It is explained by considering the light to have the wave nature, right? Now, what happens over here in Davison-Germer experiment? My dear students, over here you are going to take a beam of electrons. You are going to take a beam of electrons. This beam of electrons you are going to pass through a slit, right? And over here you have kept a photographic plate, for example. Over here you have kept a photographic plate. When you pass the electron beam through a slit, what you will observe? You will observe these circular patterns. You'll observe these circular patterns on this photographic plate, right? You'll observe these circular patterns on this photographic plate. This phenomenon is something which you call as diffraction, basically. This phenomenon is something which you call as diffraction. This phenomenon is something which you call as diffraction. But this diffraction was shown by light. Diffraction was shown by light, basically. And that diffraction shown by light was explained by considering light to have the wave nature, right? But here did I take a light or electron? I took electron beam. Electron beam also showed diffraction, right? So diffraction shown by electron beam will be also explained by considering this electron to have the wave nature. Yeah? I hope it's clear to everyone. Perfect. That's what I'm telling you over here. The wave nature of the matter was explained, was experimentally proven by this particular experiment, which in detailed format you will study in your class 12 physics. Just the idea of things I gave you here. Perfect. I hope you remember all the results which I gave you. See, these are all the things which I told you. This concept is valid particularly for what? Microscopic particles. Particularly for microscopic. Right? You can apply it to microscopic as well, but you will get the negligible wavelength there. Right? The de Broglie wavelength associated with the macroscopic particle will be negligible. That will be of no use to you. Okay? Even these results were done. If a charged particle is accelerated from rest by applying potential, de Broglie's wavelength associated with the charged particle is calculated like this. And for an electron, lambda is equal to 12.27 divided by under root of V angstroms. This V is not velocity, it is the potential difference at which electron is accelerated. Right? It is the potential difference at which the electron is accelerated. One simple question. Can you let me know in the chats what should be the answer of this question quickly? Quickly, guys. If the kinetic energy of a proton is increased 9 times, the wavelength of the de Broglie's wave associated with it would become simple. Lambda is equal to h upon under root of 2mq multiplied by v. Right? Or instead of qv, let me write kinetic energy. Perfect. Let me call this as lambda 1. Now, as per the question, what we are doing? We are increasing the kinetic energy of the proton 9 times. Right? We are increasing the kinetic energy of the proton 9 times. So instead of Ke, I'm writing 9 times kinetic energy now. Let's assume the de Broglie's wavelength associated now is lambda 2. Right? Calculate lambda 2 divided by lambda 1. Lambda 2 divided by lambda 1. What you'll observe? What you'll observe? You'll observe it as, you'll get it as 1 by 3. Perfect. So lambda 2 comes out to be lambda 1 divided by 3. Perfect. So that is the answer of the question. This is simple. Nothing to do with this, right? If you make this 9 times, there is a root. A root of 9 is 3. So 3 comes out. So it becomes 1 by 3 times of initial wavelength. Right? There is no such big deal here. My dear students, there is one more thing. Now, before solving the other questions, we are going to associate. We are going to associate de Broglie's concept with Bohr's model. We are going to exactly associate your de Broglie's concept with what? with your Bohr's model. Since if I talk about an electron, let's say this is the nucleus, right? This is the electron which is revolving around the nucleus. This is the electron which is revolving around the nucleus, right? Now, electron, as per Bohr's model, electron is a particle. Electron is a particle which is revolving around the nucleus, right? But you know, any particle having certain mass moving with certain velocity, there will be a wave associated with it. There will be a wave associated with it. So when the electron is moving around the nucleus, definitely there will be a wave associated with this particular electron, which is something you call as de Broglie's wave. Perfect. Which is something which you call as de Broglie's wave. Right, guys? Now, my dear students, we are going to derive one very, very, very important result. I'm relating basically de Broglie's concept with Bohr's model. Bohr suggested that the electron is a particle, right? But few minutes back, we got to know every single particle has got wave nature as well. So electron, when it moves around the nucleus, it will be having the wave nature as well, right? It will be having a wave nature as well. Now try to understand few things. See, as per Bohr's theory is concerned, you know MVR is equal to NH upon 2 pi. MVR is equal to NH upon 2 pi. And few minutes back, you got to know lambda is equal to H upon P as well, right? H upon MV as well. Few minutes back, you got to know lambda is equal to H upon MV. This is something which you got to know few minutes back. Okay. My dear students, if I just shuffle this equation like this, I'll take this 2 pi here, I'll write it like this. 2 pi r is equal to N H upon MV, right? So I'll be writing it like this. 2 pi r is equal to N H upon MV is something which you call as lambda. This is one amazing result which you got from here. 2 pi r is equal to N lambda. 2 pi r is equal to N lambda. This particular result explains the wave nature of electron moving around the nucleus. In this result, you got lambda. Lambda is the characteristic of wave. Right? So this particular result explains the wave nature of what? It explains your wave nature of the electron moving around the nucleus. This particular result, 2 pi r is equal to N lambda. Okay, 2 pi r is equal to N lambda. 2 pi r is equal to N lambda. If you try to understand it properly, put the value of N as 1. That means you are talking about first shell. If N is 1, 2 pi r is equal to lambda. Lambda is the wavelength of one complete wave. So when electron, I'm talking about N is equal to 1. Guys, try to understand this particular thing. Have a look. Just a second. Have a look. I'm making you understand this particular result. You know, your 2 pi r is equal to N lambda. If I put the value of N as 1, it becomes 2 pi r is equal to lambda. 2 pi r is equal to lambda. Which shell am I talking about? I'm talking about the first shell. Let's assume this is the first shell. Right? So for the first shell, 2 pi r is equal to N lambda. What is 2 pi r? 2 pi r is the distance. 2 pi r is the distance covered by the electron in one revolution. Right? It is equal to lambda. What is lambda? Lambda is the wavelength of one complete wave. Right? Lambda is the wavelength of one complete wave. Imagine it like this, just to make you understand. Imagine if you open this circle. It becomes a line. If I ask you, what is the length of this particular line? You will say 2 pi r, right? You will say 2 pi r. How many lambdas did I get over here? I got 1 lambda. That means 1 wavelength. Perfect. That means over here, you are going to represent one wave like this. What does it exactly mean? It means that number of waves. In the first shell, you are getting one complete wave. In the second shell, you will get 2 waves. In the third shell, you will get 3 waves. In the fourth shell, you will get 4 waves. So there is one important result over here. Number of waves made by the electron. When the electron revolves around the nucleus, it's always equal to N. If the electron is in first shell, it will make one complete wave. If the electron is in second shell, 2 waves. Third shell, 3 waves. Right? So in the second shell, it's going to be 2 lambda. In the third shell, it's going to be 3 lambda. Fourth shell, 4 lambda. Which categorically says that whatever is the shell number, same is the number of waves made by the electron. Right? Perfect. So from this particular result, what are we concluding? We are concluding the wave nature of the electron revolving around the nucleus will be dominating from this particular thing. When you related your Bohr's theory with the de Broglie's concept, you got to know when the electron revolves around the nucleus, its wave nature predominates. Its wave nature dominates basically. So let's try to see certain questions. Can you solve this particular question? Can you solve this particular question? In the hydrogen atom, if x is the radius of the first Bohr's orbit. So you have got the hydrogen atom whose z is 1, right? Radius of the first Bohr's orbit is x. Perfect. Is x. Right? If the radius of the first Bohr's orbit is x, what does that mean? That means r naught n square divided by z is equal to x. R naught as such, n value is 1, right? Because he's talking about first orbit. Z value for hydrogen 1, so r naught is x. R naught is x, right? You got the value of r naught. Now, de Broglie's wavelength of the electron in the third orbit. De Broglie's wavelength of the electron in the third orbit. When the electron is revolving in the third orbit, what will be its de Broglie's wavelength? Right now, I give you one result. 2 pi r, radius of electron in the third orbit, is equal to n lambda. So it's going to be 3 times lambda, right? 3 times lambda. So it's going to be 2 pi as such. This is going to be r naught n square. N square is 3 square divided by z. Z for hydrogen is 1. It is equal to 3 lambda. So 1 of 3 got cancelled, right? So it's going to be 2 pi. Instead of r naught, you are going to write x. Instead of r naught, you are going to write x, right? This is 3 2s are 6. Perfect. So 6 pi x is equal to lambda. This is the answer of the question. I believe you can solve it. I believe you can solve it. Right? 6 pi x is equal to lambda. Perfect. So guys, I think this much is enough for today. Perfect. Next session is going to be the last session of atomic structure, in which I shall be discussing the Heisenberg and the quantum mechanical part. Right? Your quantum numbers, etc., etc. Okay, I believe this much is enough, and do let me know in the comment section of the video if you actually liked the session or not. See you all in the next session. Next session is going to happen day after tomorrow. Day after tomorrow, we shall start with the Heisenberg's uncertainty principle, and eventually we'll move into the quantum numbers as well. Okay? Hello guys. With this, taking leave. See you in the next session. Do let